Okay. Mhm.
Okay. I've been. So where are we? What are we doing right now? Let me. Because I was just trying out the
Mhm.
different values.
Okay, okay. If you want to share the screen, you can
No,
do
no.
it. Mhm.
Someone's already sharing the screen. Who's sharing?
I'm sharing. I'm sharing.
Okay, okay. Yeah. So let's think about this. Let's look at the matrix first.
Yeah, yeah. Right.
Okay. So we see the first column of the matrix is summing up to 1. Second column
Right.
of the matrix is summing up to 1.
Summing up
Third
to
column
one.
is also summing up to 1.
Summing up to one.
The first two columns are fixed. That is nothing but saying,
Hmm.
those are the probabilities of happy to sad, right? We can
Right,
think about
right.
it like that. Can we write it
Hmm.
down on that? Are we able to edit the third? Yeah. Say this is the probability of happy. Maybe this is just happy.
Yeah, yeah.
Yeah. This is sad.
I
Sorry,
guess we
stressed.
must make a copy and then write something.
No, no. I think if we reload it, it gets back to the state. So it's not like we are changing anything. So it's okay. I tried a few of that also. I tried to change one of the columns also, and I could just reload the page and it got back to the same state. Right? Yeah. Okay. And for now, I don't know, even I'm not sure what the third column means. But if I think about in the 5 people analogy, I mean, the 4 people analogy with the
Hmm.
government, this would be the government, right? I
Or
can't
or
think.
It
or
shows
is
the
this the
initial
input?
proportion,
Yeah, initial
of
proportion,
happiness,
right?
the S naught thing.
Right.
Maybe that's true. That's true. Okay. So say this is the initial proportion of people in the two uh, where they're starting from. You're right. Maybe
Starting point,
that
yeah.
might be true.
Right. So zero. So one
Yeah. So
represents
what we do?
100.
We fix the initial,
Hmm.
and now we run iterations. So running iterations is nothing but changing n. Can you look at the right hand side, the small graph on the right hand side below?
Oh, yeah, yeah, yeah. Just a second.
Yeah. 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 You can see that n knob, right?
Yeah, yeah.
Right. Can you just drag it to 1?
Just a second. Yeah.
Yeah, in the first iteration, does this look very similar to what happens? So,
Okay,
okay,
is this the number of iterations?
yeah, number of iterations. That's what I think it is,
Hmm.
because if you keep going
Right,
the
right,
next
right,
iteration.
right, right, right. So in the first iteration, we are at S1. Okay, it's changing S1. Can you see?
No, no, it's changing that. So the 0, 1, 2, 3 is n. So S of n is being written actually there.
So the value of S is being okay.
Mm-hmm. Keep going, keep
Uh-huh.
going, keep going, keep going,
Right, 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 right.
keep going, keep
Happy.
going.
Okay, yeah. So after a point, it becomes constant. It attains the equilibrium point after a point,
Yeah, I think that.
right?
Yeah.
Yeah.
So that what we are seeing in the Excel sheet, same thing we are seeing here as well.
Mm-hmm. Yeah, but if I think of the third column as init, right? Initial. Okay, so init Anurag here, let's maybe write it as something else. Let's call it initial. Okay, so distribution of people maybe for now,
Starting
but I'm
point
not
or
sure if,
something.
yeah,
Yeah,
not sure if
static
that what
point.
it is. I'm not sure,
Mm-hmm.
right? Because can you X this you have this calculator thing, yeah, you have this keyboard open,
Mm-hmm.
right? Because now look, we have changed our initial proportion,
Right.
but what did we expect? No matter what the initial, yeah.
Correct.
So no matter what the initial proportion, we should eventually
Reach the
reach
same.
to,
Yeah.
is that
the
happening?
final stage should be
Let's see.
same.
Yeah, let's see. I just want to see. This is going down, and it's stopping at 0.6.4, 0.6.4.
And earlier it was.
One thing about D, it was actually a point satisfying x plus y equal to 1 actually. Previously it was 0.3 and 0, which is wrong. Did you change something in the column C?
No, we didn't.
No, there's something wrong with it. That's why.
It should come to 1 and 0, right?
Yeah, it's not coming to 1, 0. Maybe something got changed.
While inserting the H first row,
right,
H,
right,
S,
right,
and D,
right,
we
right,
shifted
right.
everything down. So is that the reason?
No,
Now
no.
it should
The formula
come to-
was wrong in the Excel sheet.
Formula
No
was
worries.
wrong.
Yeah.
Okay. Right. So now it goes to the same. It eventually attains the same level,
Yeah.
right?
Yeah.
No matter where we start from.
Yeah.
So equilibrium point. Yeah, right.
Okay. So can we try to explain this to people who do we want?
Right.
Okay.
Can you share the Zeitboard? Maybe that would be.
I mean, sir is here, so maybe sir would be taking the session today. But anyone who thinks can understand what's happening here, or at least can observe what is happening here, who hasn't maybe was not present in yesterday's session.
Okay, let me see what the. Is this the? No, this is not the one. Yeah, this one. So maybe you can start from here, then we can move to that graph.
Yeah. So is everyone aware of this question? Has everyone gone through this question once? Maybe yesterday or day before yesterday in the 2 days that we've discussed.
I saw some new people as well, so probably some of them haven't seen
Yeah,
this question. So
I want them if they, I mean, it's better if they come out and maybe discuss, right? Or else it will be
Right.
hard for me to, for
Right,
us to like. Even though the yellow matrix has a different proportion.
There's some doubt in the chat. Why is T matrix 1001 initially, even though the yellow matrix has a different proportion?
First of all, what is the T matrix?
Okay.
Yeah, I didn't
T0.
understand that.
Okay, at 0 iteration, what is the
our initial matrix H and S ka, it is just the current iteration,
understood? Right? Understood. So can we go to n is equal to 1?
Yeah.
So what would you expect n is equal to 1 to be? It would be nothing but exactly. Rohit has answered the question as well. But what if I change the distribution? What happens then? What if I do 0.5, 0.5? Can you do 0.5, 0.5? No, don't. No, not there. Let's not change it there. And let's not change it in the Excel sheet as well. Let's change it in that left-hand side, the graph. Let's make it 0.5, 0.5. Somehow, maybe close. Okay. I don't know if you can reach 0.5, 0.5 exactly.
No, we can't reach but this is the closest. This is the closest we can get to 0.5, 0.5.
Yeah. So what is T1?
So our T1 would be 0.8. Oh yeah. So this is our T1.
Okay, what if I take 0.7, 0.3? Will T1 always be the same? I just want to understand. I mean, I hope whatever distribution I take in the first iteration, T1 is 0.8, 0.2. Okay. Does that mean in the after one iteration, this is how the people are distributed? But that's not true, right?
No,
if there was
okay, for
T matrix should
T1
remain same.
T1 it's the same for if we even if we change the starting point, T1 is same.
No, but okay. So I was thinking as okay, T1 is telling me
Hmm.
after one iteration,
Right.
what is the distribution of people, right?
Hmm.
But if I'm starting with say 0.7 and 0.3, the distribution should not be the same as starting with 0.5 and 0.1. So maybe T1
Right.
is not what we think it is, right? So SI represents the distribution of people
Yeah,
after I iterations.
yeah, SI would represent that, right?
Yeah, that makes sense, right? It's just saying how many people are in the stress state,
Hmm.
right? So it's not that okay, S1. Actually, what is
If
S1 telling you?
actually,
That's
what does
basically
T?
your distribution after like so each
So
time
that's
when
the
you
output, right?
yeah,
Output
that's the
after.
output, yeah, iterating it. So when you're moving people from say happy to sad, sad to happy, so after that one complete iteration, whatever is your outputs for happy and stressed, that is S1 probably.
Yeah, I think on the left-hand side of the graph, it was given that S0 is nothing but saying how many people are in left and how many people are in right. Yes, sir. We can start.
Okay, let me stop sharing that.
Okay. So there has been a mixture of many people in the session so far, and I just wanted to tell one uniform advice to all of you. For some people, it was very silly, easy, straightforward. For some people, it is advanced. For some people, it is repetition. But then at the end of the day, it's about seasoning your mind about thinking linearly. And the world has questions which has linearity in them more than non-linearity. And the reason why non-linearity became popular is because we overstudied linearity and we didn't know anything about non-linearity. But then still, when you study non-linearity, you convert that to linearity and then approximate it to linearity and then study them. What do I mean? I only mean the following. Throughout a discussion, one thing that you should not forget is the dot product. Maybe it will help if you can take a pen and paper and then think of dot product for like 2 hours. What is dot product? A comma B into C comma D is AC plus BD. What is this? I know many seasoned people don't understand dot product so well. You should get familiarized with it. It is like driving skill. More you drive, more you realize what is driving. Driving does not mean just give me a second. I will disable the sound that I'm getting because of people joining. Play, join, leave. Okay, perfect. So the idea of dot product requires seasoning, and it's like a driving skill. You can go from what simple driving to Formula One racing, right? So you should achieve that slowly, right? Especially in R2, dot product is straightforward. In our school days, they teach that as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 1, 2, 3, 4, 5. So in our school days, they teach that as angle between two. Let me mute all for a few minutes. Okay. So if you have any questions, raise your hand and I'll unmute you. And then from after the discussion, I'll unmute everyone. Okay. Yeah. So the idea is dot product, and people say that it is the angle between two vectors. But then in n dimensions, we don't understand what is angle, right? And the angle is one of the many meanings that dot product has. And as you know, if you have studied some data sciences or applied linear algebra, you understand that dot product is how a single neuron is defined. The idea of neural network starts with dot products only. The perceptron learning algorithm is about dot products only, right? So dot products are very important. No matter how familiar you are with matrices, you should get sort of realigned with the idea of dot products. Okay. So where is dot products coming? Multiplying two matrices is about dot products. Simultaneous equations are dot products. Look at one equation. Ax plus by is equal to c. You're taking a dot product of a comma b and x comma y. Right? 2x plus 3y. 2 burgers and 3 pizzas. 2b plus 3p is costing you so much. Is dot product of pizza burgers cost and the numbers that you're having. And geometrically, what exactly this signifies? So familiarity with dot product is very, very important. Observe dot products everywhere. What have we done so far? We have looked at matrices inspired by simultaneous equations. Correct? That's all we have done. Take a simultaneous equation, get inspired by creating a matrix out of it. The moment you create matrix, what happens next? You observe something else that is more subtle. What is that observation? That it is a function. Correct? Let me write that down. It's so important that we should make a note of it. Can someone post yesterday's notability link? Today is 7th October 2023. Let me share my screen. Maybe someone can unmute, some co-host can unmute and tell me that you're able to see 7th October 2023 in the shared link. Can you see 7th October, Chetan, in the shared link? You can see. Okay, good. All right. So we saw matrices. And then we asked what is X and Y. There are tons of examples where this appears in real life situation. And we model this as 2, 3, 1, 8 as a matrix. And those of you who think that this is very trivial, why are we discussing this again and again? The problem is this is trivial and we don't understand the extra aspects of it because we lie in 2 cross 2. We don't see what is its consequence in n cross n, right? And seeing this only as a 2 cross 2 matrix doesn't help. You should extrapolate this to n cross n. What does it mean in n cross n? We may have to think, right? So all that we observe here is there's a function f from R2 to R2. Okay. All right. What exactly is this doing? One of the most significant intuitions we had was that when you have any object here, what does function do? Matrix function do? It takes an element of R2 to R2. R2 means 2 dimension. That's all. Okay. And it is defined as, you see, this is an element of R2. This is an element of R2. The question is there something that 2, 3, 1, 8 takes XY so that it becomes 715, which means if this is 715, what is its pre-image? Correct? I'm just reiterating on what we have studied so far. But then we also saw, what is that? We put an image here, right? We put an image here. We put an image here. And then we saw what happened to this image. we observed that the image would either become like this, or sometimes it would become what? It would simply become a straight line passing through origin, right? Or sometimes it would many things were happening to that image, correct? And that was a function which was creating this transition. Now, with this, I end the recapitulation. Whenever we said 1, 2, 3, 4 a matrix, we realized that this is going to this is going to this, correct?
Yes.
That was the major intuition which will apply in the Markov matrix that we are working on right now, and see something really fascinating and unbelievably simple an idea. Okay, so let's see. Just bear with me. What is the story so far? The story so far is matrix as a function, simultaneous equation as a matrix. That function taking from R2 to R2 takes an image and meddles with the image. Okay, and then a matrix is simply converting 1, 0 to 0, 1. Let me open that image thing and show it to you people once, although all of you have seen this. University of Texas, you all know this. Can someone please post the link? I think it's easier for me to post the link. Okay, all of you have seen this. If you haven't, see this once more. One second. Just a minute. I'm sharing the screen. Just a second. Yeah, we all saw this image, right? Remember, what would happen to this image? Change the matrix. 1, 2, 3, 4. And image would become something else. Correct? Now let me carefully change this to 1, 0 and 0, 1. Nothing changes because it's identity matrix. Can someone tell me what happens when I make this okay? X is 0.1 and Y is one second. X is 0.1. Okay. X is 1, Y is 0.1. Okay. Which means 1, 0 is going to 1 and 0.1. And this is 0.1 and 1. What happened? Did you observe? What just happened? Just observe this, guys. We have not discussed symmetric matrices ever. We are now discussing it. What exactly is this? 1.1 and 0.11 moved it slightly like this. Why did it move? You can unmute and discuss. Maybe I'll give you 5 minutes time. Go ahead. What exactly happened on the screen?
It shared, the picture shared.
Not just that, there's a lot that has happened here. Try to unravel everything that you can. Fundamentally, there are many things happening here.
Not just sheer rotation as well.
We can say that
Sir, maybe it is applying that matrix function to every single pixel of the image. It is changing the, I mean, the coordinates of every single pixel in the image as an input in R2 and giving out the new coordinates in as the output in R2, hence shifting the image.
Correct. But what is this symmetric matrix denote?
Yes, sir.
Distortion is also symmetrical.
Hmm?
The distortion which we observed is also symmetrical.
Okay, see, I think you people should, of course, you all are right, but avoid. Let me make it an optimistic statement. Try seeing something that you have not seen in this problem. All of you are telling me something that you know already. Try to understand something that you don't know already.
Sir, the change in both the vectors is symmetrical.
That is something that we all know. I mean, something that is obvious. Okay, two things. Something that is obvious, you should not state. Something that you know already that you should not state. You should do this check to yourself. Of course, I don't know what you know already. Right? Go ahead and discuss for 5 minutes. Just this. There are a lot of things that's happening here, by the way. Just this. Go ahead.
Why does it appear to tilt into like left? Like it goes down in left and up in
So
right.
what we can do is maybe Chetan, you can moderate the session. You can unmute people and they can raise their hand. You can unmute and talk to them. I will mute all for just the time being for the next 1 or 2 minutes.
I'm not the co-host, so I can't unmute people.
I guess I can do that. Fine.
I've made you the co-host. Go on, Nitin. Chetan, unmute yourself. Anyone who wants to talk, raise your hand and Chetan will unmute and you can talk.
Right. Go ahead, Amit.
So I'm thinking, why does the lower left corner goes down and upper left goes up if everything is symmetrical?
Okay. Okay, somebody else is. Yeah, Ashish, go ahead.
I think the image is not passing through the origin.
Image is not passing through the origin. What does that mean? Can you explain?
Like it shifts and like it maybe I'm not sure, but maybe it becomes non-linear. Like I'm not sure.
He is suggesting the plane of image is
Yeah,
not passing through origin.
Yeah, Praneeth, go ahead. You can speak.
Yeah, sorry. Actually, I wrote wrong in the chart box. I think why does the blue and red lines in this image rotate by 45 degrees to the left?
Okay. So, go ahead.
Okay, that was my question.
Okay.
I guess the blue one is perpendicular axis to the plane.
Blue one, perpendicular axis to the plane.
I cannot see the x-axis then. I guess the blue arrow is coming out of the plane and red one is in the plane, maybe.
So the vectors were initially on the axis, right? We saw that the vectors were initially on the axis. So the blue vector was on the y-axis and the red vector was on the x-axis, right? When we change the values, from 0 to 0.1, the vector is changed, and hence we are seeing the distorted shape of the photo, right?
Okay.
This is what I understood. Like I think the first vector was 1 0, right? So 1 0 became 1 times the first 1 0 plus 0.1 times the second 0 1. That's the only thing that came to mind, but it was something that I already know because sir said you have to say something you don't know and something you thought about, but this was something I already know. So this is the only thing that came to my mind. Yeah.
Okay, so
That
some
is
people are saying that it's rotated. If it, can you see if it was rotated, would the images, do you think it would have changed its shape if it rotated?
I think
Can,
it's definitely doing a shear, right?
right. So that means the angle between the two vectors has changed, right? That means it's not 90-degree like it was before.
Hmm.
Yeah, Nathan, go ahead.
A lot of people have raised their hands, Chetan. I think
Yeah,
you
yeah.
should go on.
Sir,
I
one
have,
thing that I would like to highlight is just a question came to my mind. After doing these transformations, will the means the dimensions of the image will remain same or the area that the image covered will remain same?
yeah, good question. So, what do you think is happening? Do you think the you just saw the image change its shape, right? Do you think the length and height of the image has changed? Do you think it has become smaller or bigger as a
In
result of
fact, we
it?
could ask a question that is the area changed for the image? I think the area is not changed.
Even I think it hasn't changed.
Yeah,
what if there is a greater amount of distortion?
would be
Guys,
left
I don't
be
think
seen as
so.
it is changed, but
As
the area is still still the same, I guess.
I think only
Now
the
I also agree
angle.
that maybe the dimensions have changed, but the area is same.
Area is same.
Because because the axes are shifted to different places, like, but area should remain same.
Chetan, Nitin has
Mhm.
raised his hand.
I've unmuted him already.
Oh,
guys,
okay, okay.
am I audible?
Yeah, Nitin, you're audible.
I'm Aditya, by the way.
Sorry. Yeah, go ahead.
Sure. So, as like some people are suggesting for sharing, I don't see a reason because since the matrix is symmetric, so it shouldn't shear, I guess, at all.
Okay. So what will happen? Okay. So I think sir is sharing the
I
same thing.
don't.
Thank you.
Is there any way you can actually associate the metrics with sharing? Like when you know it is rotation by theta, you know it's something like comes about. I don't know the exact one, but it's something comes about like cos theta, sin theta, something like that. Like, is there any way we can come to the like equation, like the metric which you multiply for, say you share by an angle theta, or if you share by a something like that?
So, why I
So
am saying that it wouldn't shear is, so the elements which are below the main diagonal, they're generally the same for symmetric matrices, right? If I am correct. So that would,
Someone new upset.
also one more thing, Chetan, you said that angle between the blue and red vectors have changed. I don't think they have changed. The angle is still 90 degrees itself.
Little less than or less
No,
than 90, right?
just try it on your
I think that the angle has not changed. It is still 90 degree just
Exactly.
because the matrix is symmetric.
Yeah, that would be a reason. But just to visualize it, try putting 0.2 instead of 0.1. Then to the vectors
Okay.
don't change.
Okay, let me see.
The image shrinks this way, but the vectors are perpendicular. Still, the vectors are perpendicular. And yeah, that one of the reasons could be that they are symmetric. The matrix is symmetric. That is why the vectors are still perpendicular. That's yeah.
So how did you verify that the angle has not changed even a small bit?
Like in the figure, it does appear to be like what I felt is that it's
No,
not
Ashik,
exactly
how did you
90.
verify it?
Yeah.
I
Sorry.
tried for 0.2 as well, and the vector is not shifted at all when we refresh the page. Tried for 0.3
Okay, what
once.
are the red and blue vectors? So yeah, so the column vectors, right?
Yeah. Yeah, so try it for 0.5, 0.3, anything. You can see the change in image, but the vectors still remain perpendicular. I mean, just to see, it is illusion when we see in what we are seeing in the screen right now, that it seems that the angle has increased a bit, but yeah, it's not increased at all.
As far as matrices are remaining symmetrical, the angle remains 90 degree, I guess.
Yeah.
Apparently so. But if we are making the matrix unsymmetrical, and that is to say A12 and A21,
yeah, if
are
they
not same.
Then they won't be perpendicular. Yeah.
Axes are not perpendicular. Yes.
Yeah. But as of now, if we consider 0.2, 0.2, 0.5, 0.5, and they are still perpendicular.
Yep, and in case there are cases where this axis is vanishing as well. Like maybe going behind the plane or what, I don't know.
Axis? Which axis?
Which one?
One of the two. For example,
I think
if
that would happen if you put in a negative of the values that we have put in now, because then only like it's coming to the front and back, right?
Let me check.
But I'm not sure we are thinking in the right direction by seeing this, but yeah.
I saw what you said, Ashik. I put in different values and it changes the angle. But as long as it remains symmetric, the angle remains the same. Yeah, you're right.
No,
Yeah,
nothing
the
to do
angle
with
remains
positive,
same
negative.
because maybe I too think now that the red line is within the plane of the image and the blue one is perpendicular. So they will obviously remain at 90 degree.
Perpendicular to which plane? It's an R2 plane. We are not dealing with R3 here, right?
Like the blue vector seems to be perpendicular to the
red
plane of the image, I think.
key
Yeah,
constant.
plane of the image I was talking about.
No, we are dealing with R2 plane. This is
Yeah,
a plane.
I agree that we are dealing with R2 plane.
But then what do you mean by the plane of the image?
Okay,
but
okay.
if we
So I will give you people a small hint or a lead. If you were to be standing in 3,3, what happens to you? You should not calculate. See, putting that 3,3 and then multiplying, and without that, if you can tell me the answer, you have understood. Okay. If you were to be standing in 3,3, what will happen to you? I'm 100% sure many of you will not be able to answer this question.
3.3.
3,3. The point 3,3, where has it moved now after the matrix is applied on it? Basically, I'm saying this matrix times 3, 3. What is the answer? Without calculating AX.
3.3, 3.3.
Huh?
3.3, 3.3.
Sir, it has been decreased to 2.9.
Geometrically.
So geometrically.
Sorry, yeah, 2.9, 2.9.
3 is it?
Now tell me, where is XY going? Geometrically, without computing, you should not see the matrix.
X comma minus Y.
X minus 0.1y and minus 0.1x plus.
No, where is minus coming here?
So no, you
Oh,
asked.
sorry, no, minus 0.1x
3
plus
goes. So
y.
I'm thinking that 3.
Geometrically, where will if I give you if I stand in a point, can you easily push me to my destination?
Farther from
The
origin.
matrix is multiplied on it.
Yes.
More farther from origin.
Huh?
Yeah, I think it's
Farther
sorry,
from
it's
origin.
0.1x.
More
Sorry.
away from origin.
See, that's that's a slightly obvious point because you see the figure is tilting like this, so both parallelogram ban raha hai. But then, do you realize where exactly it's going?
Yeah, sir. XY goes to x plus 0.1y, comma 0.1x plus y.
Yeah, mathematically speaking. But can you have the wisdom to show me if I put any point, Can you tell me where that point goes?
Where
Okay,
is it-
you
is
all
it-
have seen the matrix, right? So let me ask you this question. This is the main wisdom you must achieve at this point of time after so much of discussion. Today's lecture will focus on this part only. Okay, so okay, 1 minute. Let me share my iPad. 1 second. Okay. Okay, so this is my R2 on the image, or let's say whatever. I am somewhere here. If you apply the matrix on me, where will I go?
Sir, is it that the point goes out of the plane of the image?
No, there is no image now. Only this point. Matrix acts on this point. Where will it move the point?
To the left.
A little upward and little to the right for both effects.
Little to the right, little to the up. Can you exactly tell me? There is
0.1 to the-
there is more wisdom to it than just that.
It will go more up because y is high.
It will
Point
go.
X
Correct.
X
It will
goes
go more up.
slightly in the
Why?
direction
Exactly.
of y.
Exactly. Ayati gave us the right answer. Ayati is saying, in other words, it depends on how far away it is from origin, point number 1. Point number 2 is it depends on what is your 1. Correct?
What is your one? What do you mean by?
No, unit scale is always very important.
Correct.
Otherwise, you don't know exactly where, right? Correct. So if you're away from origin, the movement is a lot more than if you're closer to the origin. What's the matrix?
1,0.
In the column, what was it? First column?
1,0.1 and 0.1.
1.
This simply signifies that you are. What was this? What is this point? 0,1, right?
0,1.
This point 1,0.
1,0.
This is becoming 1,0 is becoming 1,0.1. ओके तो क्या हुआ, जो पॉइंट यहां पे था वो थोड़ा बहुत ऊपर आ गया, जो पॉइंट यहां पे था वो थोड़ा बहुत राइट साइड पे आ गया. आपका एक्स एंड वाई एक्सिस 1001 जो आप आई वेक्टर जे वेक्टर आई कैप जे कैप कुछ बोलते थे 12th स्टैंडर्ड में, करेक्ट, समथिंग लाइक दैट यू वुड से, राइट, position vector, unit position vector, blah blah blah, that happened to shift slightly this way. And when you want to buy a house, what language do you speak? What's the price per square feet? That's all, nothing else. You don't talk about kitchen, bathroom, bedroom, etc., etc. You only want to know what is the price per square feet. Based on that, you will estimate the cost of the place. Similarly, the moment you know how your I cap, J cap is shifting, based on that, you can say what is happening to the entire space. I'll again give you people 2 minutes time to discuss. Go ahead. I repeat, what did I say? Look at where your I cap, J cap, what is I cap, J cap, 1, 0 and 0, 1. See where this is going. This is going to 1 minus 1.1. This is going to 0.11, which means that those green dots, blue dots have now become brown dots. Correct?
Yes.
Like we can think of it like the axis actually got shifted by some position, right?
Hmm?
Like both the x and the y axis got shifted by some, like such that that's why the angle between the two vectors remains 90 degree. Like the angle between the unit vectors would be 90 degree, but they shift by some small amount to the, I mean, okay, anti-clockwise.
Those were eigenvectors, not unit vectors. Like
No, I
blue and
only
red.
the mouth of the crocodile is now smaller.
Right.
That's the wisdom. And this is reflected all over, just like how the cost per square foot rather, of your house is enough for you to determine what is the cost of your entire house. If you're planning a 1200 square feet house or a 2400 square feet house or a 4000 square feet house, it doesn't matter. You only need the price per feet. Right? Similarly, if you know exactly what's happening to your unit vectors 0, 1 and 1, 0, you can tell me where this point, this red point is going. Okay, 2 minutes time. Go ahead, discuss.
Has this something to do with the curved space? The Einstein talk about.
I'm not sure, but instead we can conclude that our
One
basis.
important tip that I'll give you people is do not try to, especially when we are doing very, very fundamental stuff, the ABC stuff, avoid the temptation of relating it to something that you know already, because that takes you into a recursive loop of ignorance. Oh, this probably has some connection with B. Oh, B has some connection with C. Oh, C has some connection with D. There was some question in the Discord server today about contours and gradient. It's actually such an easy concept, such a straightforward concept that I keep saying a small rain droplet knows this concept. Right? We don't need a lot of math to understand it. But then when you try to use heavy duty jargons, it becomes very complicated. Try to see it without any heavy duty jargons. Tell me, what does it mean for you? What does this movement mean? With this movement, you tell me, you go and stand on any part of R2, I will tell you how you will move.
So we move towards right top part of our graph, as in the y equals to x equation line. We move in the right and top movement, as in we can safely say that our movement is restricted in this space, as our basis is no more 1, 0 and 0, 1. I mean, sorry to bring in basis, but yes.
Yeah, don't bring in basis. The idea of basis is meaningless in R2 because it's obvious for us. We know what the idea of basis itself is, so obvious that we should not be discussing it unless we are solving a problem involving basis, right? So the idea is very simple. The moment such a point is given, a point is uniquely determined by its x and y axis, right? You see this part, you see this part, and you see this part, correct? When you see these two parts, you will make a note of the x component and the y component, correct? The y component and the x component. And all you will do is you will look at this height and move it by 10%. That's all what you are saying. The height will be 1, but the movement will be 0.1 times that. Correct? Well, let's actually manually type and see. Now is the time where you should actually manually do it. 1, 0.1, 0.1, and 1. When you apply to say x equals 4 and y equals 10, let's say is where the point is. This becomes 4 plus 0.1 times 10, correct? 0.1 times 4 plus 10. Right? I don't want to simplify it any further. Let me just write this down properly. Maybe it's not visible for you people. right? 0.1 times 4. 0.1 times, sorry for my handwriting, 0.1 times 10. It means that you take the 10% of the other component and add that to the existing component of X. The component of X, maybe I made a small mistake when I was saying this very height moves a little by this factor, 10% of this. Correct? And this moves a little this side. And this moves a little this side. Correct? By a factor of this width is maintained, but इस height का 10% ऊपर जाएगा बस. ऐसा हो जाएगा ये 2 points. Let me write those points. The points will become something like this. Correct? All of you with me? Now, this will happen to every single point, which means if you take a small circle here and apply that matrix on this, the circle will simply become
ellipse.
Right? It will get a little compressed. You're physically taking the balloon and then pushing it slightly like this. When a balloon is pushed, its area, its volume doesn't change, you know, right? That's only intuitive. But then here, the area of this little circle will slightly change because you're pushing it a little. Now, straightforward intuition, guys, think about it. Climax point, think about straightforward intuition. When you keep applying matrix again and again to the vector, the crocodile's mouth closes down and the dimension dips. That is what I would like to note here. I will call this my wisdom. Repeated application of this matrix will lead all the points to line up on a straight line. अब इसको कोई भी equation use करके नहीं बात करेगा. You should only talk with intuition. Strict rule. Because equation like you can do a lot of stuff and the intuition gets lost. Only through intuition you must tell me, what does this wisdom statement mean? 5 minutes time.
After squeezing a lot, sir.
Yeah.
Hello.
Pardon?
Yeah.
If we apply again and again, it becomes a straight line.
Yeah, like ellipse becoming compressed.
So it's a straight
Yeah.
line.
I have a question. Can I ask?
Go
Yeah.
ahead.
So if we have a bunch of concurrent circles and we apply this matrix on each of them, will we see a y is equals to x line or some sort of that?
We will get there later. Let's focus. Let's zoom in only on the wisdom part. Just that.
We are transforming it into a straight line.
Coders is all about writing the code. We'll write a code for this and then see also what happens to the image. Okay. Yeah. How many of you understood the wisdom part like completely? You don't have any doubts? Raise your hand. Okay, very less. The rate at which hands are going up means some people are confused still. Go ahead, ask me your share of questions.
Sir, I have one question. This is Ashish.
Yeah, so ensure that the question is around the wisdom statement. Go on.
It shows, it is telling that repeated application of this matrix will lead all the points to line up on a straight line. It's nothing but a linear transformation, right, sir? It's just transforming.
Very strict warning. No linear transformation word should be used.
Okay.
We are only discussing geometry, 7th standard kid syllabus. That's it. Nothing beyond 7th standard. We are not going to go to 8th standard syllabus. Simultaneous equation is in 7th standard. Yeah, perfect. Someone has shared a figure that speaks everything. Okay, go on. What is the wisdom part? Go ahead. More.
What happens if we apply the same matrix on the straight line? Will it widen?
No, I will say, so friends, I'll take your questions later. Okay. In fact, a bunch of students stay back till 3 a.m. discussing only questions. Now let's zoom in on the wisdom part. How many of you understood the wisdom part? Why not others? Okay. All of you can see the screen? Is it visible?
Yes, sir.
Okay. So let me import NumPy. NumPy is a standard matrix related calculator. I will type in my matrix A. What was in the first row of my matrix? Am I right?
1, 0.1. 0.1, 1.
My matrix M will be equal to NumPy mat of A. This is a standard NP. Sorry, I said NumPy as NP. Okay. My M has now become this matrix. First row is 1.1, second row is 0.11, all good, right? And I will take, what was that vector I took 4, 10, right? My vector V is going to be it is in row format. I'll convert that to the column format. Don't break your head much. V equals V transpose I do, and that becomes a column format so that I can multiply my M with V. Is that right? 5 and 10.4, right? I even wrote that down.
Yes.
5 and 10.4 is what we get, correct? So now what I will do, I will apply M on V, and whatever I get, I will apply M on that, and whatever I get, I will apply M on that. Okay, all of you with me?
Yes.
I see what happens to vectors. This instead, I can look at what will happen when M is multiplied with M is multiplied with M 100 times. Okay, this will throw an error. This is wrong Python syntax. I can do double star and 100, which is M to the power of 100. I close my video. You guys discuss what's happening here. Please note, all of you are discussing Markov matrices. That is different for the time being. Here, first column became equal to second column. Why on earth did this happen? On to you people, 5 to 10 minutes. I'm switching off my video and audio so that you guys can discuss. I repeat, 7th standard syllabus only, number 1. Number 2, no questions, please, for the time being. What I wrote on the iPad, what I showed on the program only should be discussed. That is to ensure that we finish something by time. Okay, on to you people. Why is the first column same as second? Put your thumbs down if you are curious but you don't understand it. So go to reactions and put your thumbs down. Not raise your hand. Thumbs down is not here, is it? Okay. Okay, put your thumbs up if you think you're fascinated. You don't know why this is happening, but you would like to know. Raise your hand. Thumbs up or raise your hand. Some reaction. Any reaction. If you are not reacting, it means that you don't care or you know it already. Not the two. Only 10 reactions. Only 13 reactions out of 37. 1/3 only are reacting. Now, I just want to know. See, the reason why I ask people for feedback is because I want to know how many of you are genuinely fascinated. Why is the first column becoming same as second column? This is precisely what I was saying, that it becomes a line. On to you, people. Go on, discuss. I'm sorry, my laying restrictions would have probably stopped you from discussing when I said that 7th standard syllabus only. Otherwise, people will start using, algebraic topology to explain what's happening here. That should be the case. Or use some very hi-fi ML idea, which the person who is asking that question will not understand. So to avoid all those things and to not give others complex, I said restricted. Restricting sometimes helps. Right? I keep giving this example. Boxers train by tying their legs. There's a reason for it. They try punching by tying their legs so that they understand how important footwork is in boxing. So similarly, we cut one part of our knowledge. We keep very basic axioms only in our discussions. Okay, go ahead.
I mean, why you study this?
Sorry, I couldn't hear you.
Okay, is Yeti here? Because she posted a photo in the. Yeah, go ahead.
The only thing that I actually remember, is the ellipse. Like, when you think of it, all the points lying on a circle, and then the points will, when you apply the transformation, it will become an ellipse. And then once you do that, once the ellipse becomes compressed, it will eventually become a line. That was something he discussed earlier. That's what I just remembered, and then I realized that was what I was about to say, and then I realized that it's not that much linked to what we're discussing now because we don't have any constraint on the point.
But whatever is happening to whatever is happening to the circle is becoming the ellipse. That is happening to all the points in R2, right?
Mm.
So if everything was lying at all of 90 degrees, now the crocodile mouth became smaller. Everything is lying within, say, 88 degrees, and then 87, 86, 85, 84, 83, 82, 81, 80, 90. Sorry. Everything maybe 10, 9, 8, 7, 6, 5, 4.
So eventually it becomes zero, I guess.
Right.
Also, two planes are becoming one plane,
How are two planes becoming one plane?
Two vectors
Okay,
are
you can
becoming
think,
one.
yeah, you can think, the crocodile mouth analogy is kind of good. You can think of it eventually closing, and when it closes, when the mouth closes, it becomes a
single entity.
Yeah.
All the points are being
Lie on the line.
transformed to that line.
It's not exactly the line, right? The points are a bit different. Very, very minutely different.
If we make an Yep, Chitu, please go ahead.
Yes. Okay, so the last one, the matrix, whatever given is the input matrix, which was multiplied by 100 times. And it is giving a uniform value so that that matrix is changing that to a line. Is that correct?
What?
My observation correct? Or?
No, see, there was a matrix 1 0.
Yeah, so this is a function matrix, right?
1 0 0 1, fine. Then we
so that matrix is transforming to 6890, something like that, after 100 times of multiplication. Is it correct?
No, 1 0, not 1 0 1. It was 1 0.1.
0.1. Yeah.
Fine.
Yeah, that
that was
matrix
is
is
that was the
changing.
function. That was the function matrix. Yes.
Yeah, that
like
is getting changed to 6890 kind of matrix. Is that correct?
Yeah. So wait, okay, okay, what do you think does it mean to multiply M with M? Okay, okay, what are we doing to V, right? In line number 12, you see Sir has, okay, line number 11, we are applying the matrix or applying the function on vector V once,
Yes.
right? In line number 12, what are we doing?
3
We applied
times.
it
Yeah.
thrice.
But to what? What is the input for each of the matrices? So first time, yeah. Okay, we can also think of, okay, I thought we would go step by step, but you understood it that way itself. So what does it mean to do M power 100? It's just saying, okay, what if I apply this function 100 times? Right?
Yeah, so we are just getting the matrix 100 times, and if we just multiply it with V,
that is
then
like
we will
applying
be
the matrix, the same function to the matrix
function.
100 times. Exactly.
It is kind of composition of function, you know, but the function is same. It is not FOG, it is FOF.
Yeah.
100 times.
So because this is like same values like column things, so
Sorry.
it is returning as a line as the output.
Yes.
What Maria said, it's very close, but it's not becoming a line, right? But will it become okay? Let me not ask questions. Sorry, I shouldn't be asking questions.
No, I also you know used to FOG thing. You know, I was not supposed to trespass 7th standard.
Yeah. But I guess 7th standard logic would be that the crocodile mouth, when it closes, it would become like something close to a line.
Yeah.
Okay. See what Sarah said. You know, if we are going to multiply M 100 times, and then we are going to multiply V, then we are going to get
14 times.
No.
We have, right? It should be close to 14
No,
times.
no. What Sir is doing, that we have applied function 100 times and then remultiplying it. Okay. That was the confusion. Yes. No, not now. That was incomplete actually. Now it is complete that for function is applied 100 times to V, and then we are getting a column, you know, that is we are getting a vector. We are getting a point. So that happens to be 9646.
Yeah, what is the property of that? Compare it with, what is the property of that?
Yeah, so that actually it's like the point is lying on like 45 degree. Earlier the point lies maybe like with respect to y-axis it would be like 30 degree or something, because 4,10, right? So it is like as per the image it is stretching one way more and one way less. The point is going.
Sir has written it down. See, the
Almost
property of where that point is going is that
is it going along the
it's going
diagonal?
on the line. Yeah, it's directly equal to y.
Everyone falls on the
Regardless of whatever symmetric matrix we get, it will lie on the line, right? Okay, no questions.
Let's not.
Yeah, I guess so. Yeah, because it's a symmetric.
Actually, it is point is lying on y equal to, is it like x derivative, x double?
Y
do not go to calculus.
Like, oh, sorry, it's a double quotation. Okay, I was mistaken. Okay.
Yeah, again, so Sir wants to come back to this system, right? So repeated application of this matrix will lead all the points to line up on a straight line. And now we can see why.
We can see that. Not why, but yeah, we can see that happening.
We can see it happen.
Yeah.
As a result of something unit change in the unit thing, that is leading us to
a line y equal to x. Every point after point lies on that line.
Yep. Slowly the image is becoming a straight line along line y is equal to x. With each and every passing step, that 2D things becomes a single straight line.
But I'm now very curious. Why is it happening? We see it's happening, and
See, I guess it has to do with the convergence thing we have been studying since yesterday. We are applying functions and things are converging. Fine. Now, okay, sir is back, I guess.
So I repeat, the wisdom requires only 7 standard syllabus. Okay, the intuition is just this. You have a parallelogram. You have the principal and secondary diagonal of a parallelogram, right? Okay. Someone's coming, the first person who comes reduces the diagonal of the parallelogram, the secondary one. Okay. One of the diagonal. We fix it on one of the diagonal. And the second person who comes reduces it further. Third person who comes reduces that further. This keeps going on. Where will this lead to? This will lead to the parallelogram becoming a straight line. That's all. That's all is the intuition here.
Okay.
Right? Repeated application of a matrix will take you to y equals x only if the matrix is symmetric. Why? Because the crocodile's mouth is closing. This two angles are the same. If you put 1.1 and 0.21, one is closing more, one is closing less. Then the crocodile's mouth will close not at y equals x, but at somewhere else. Making sense, guys? What is the crocodile's mouth here? The top mouth and the bottom mouth is closing at simultaneously by 111%. Then it will meet at y equals x. If the top mouth is closing by 2%, bottom mouth is closing by 1%, it means the top mouth is moving faster, bottom mouth slower. It will lead to a line whose slope is very small. Everything falls on that line. This is a very important wisdom part that we should realize. I hope all of you got it. If not, spend some time on it. Go ahead.
Is it like we are actually compressing it on a very large scale as I can visualize it, and whereas we are stretching it on the other side of the diagonal in a very slow manner?
Yeah, somebody has posted a comment in the chat box like pulling a rubber band. That's a nice analogy for it. That
But that's
eventually
like only applying force on one side. Over here, it's like we are compressing it quite faster, whereas we are stretching it slow.
No.
Somewhat on those lines.
Just imagine like, there is a parallelogram pinned at 0 origin. And just the diagonal opposite to 0, 0, we pick that point and start stretching it. We take that in our hand and start going in directions.
Right.
So eventually what will happen?
Parallelogram
will start collapsing like this.
Right.
And eventually it will become a line. Fine. So it depends if we have started moving along the line y is equal to x, eventually it will collapse along line is y is equal to x. What if we start walking while we are holding that point, we start walking below line y is equal to x? That collapse will happen below the line y is equal to x. Along the line we are going to move from origin, fine. And similarly, if we are going to walk above the line y is equal to x, then that collapse is going to happen above the line y is equal to x if we connect it from the origin. So this is what that is going on. I guess this is what is going to happen.
Go ahead, Ashish. Go ahead, Chitra.
Yeah, Ashish, you say what you're going to say.
Chituraya, you can unmute as well.
I think
Your voice is breaking,
I
Ashish.
Voice is breaking. Voice.
just want to say I think the image is getting transformed from a like from one geometry to another, like from white.
Your voice is breaking, Ashish.
Sorry. Network. So no problem. Sorry, I will write in chat.
Okay, perfect. Yeah, Chituraya, go ahead.
No, so like that the point would be traversing. So all the points lies on the single line. That's
Y
for sure.
equals to X.
That's y equal to x. So if we just again do the matrix multiplication, will the point remains on the same place or will it move again on that line?
See,
What
we are
did you
going
see?
to. The more the number of times we are going to apply the function matrix, the more it is going to get, coincide with the straight line. If it
That's
is, it
fine.
is.
Like
And
once you
also,
got
I
a
think it will move farther from the origin if it is in first and fourth quadrant.
okay, so that means after we got a line also it will be moving. If we just again multiply it with the matrix.
Yeah, I guess is
Yeah.
Yeti here?
Yes.
Yes, every
Yes,
time we
because the
are.
values will always
I
change
agree.
after multiplication.
Is it, I mean, you're saying that after coinciding to y equals to x, it will still change its position.
Yeah.
Yeah,
Yeti,
it
are you
still
here?
changes the position.
Just
It will move farther
Yes,
from the
hi,
origin
I'm
on the
Ram.
same line.
Yeah, it will move just along the line, but still it will move.
Okay.
Yeti, you put a photo in the chat box, right? You showed the vertices moving. So I just wanted to know why did you think that the vertices opposite to the
No,
origin?
so I'll tell you, I just took some random points,
Hmm.
right? So assume, so that's like a solid image which is shown there. So assume that it was just a simple, right, box, a rectangle. So I
Correct.
took some points on the rectangle and I just applied the same matrix, right? That 1.1.
Right.
Right? And that's what it will do to each of those points. I just
Understood.
applied that matrix as it is onto all
Understood.
of them.
Okay. You just saw what was happening after the matrix multiplication, right? And we saw what happens on multiple repeated a matrix multiplication, that it eventually collapses to a line. Okay.
I'm going to post one more image. I just got an intuition of it geometrically.
Yeah,
Just
sure.
thinking about it theoretically.
That would be great.
Yeah, looking at a Yeti's image, somebody just said that if it is the life line is, located in first quadrant or the third quadrant, it is going to move further away from origin. And that appears to be correct. Okay, with every multiplication of the function matrix. Not
Yeah,
to mention function.
our points are eventually lying on y equal to x, right? So the vertices in the second quadrant and the fourth quadrant are going to come closer to origin and eventually lie on the origin, right?
Exactly.
But we are still beating around the bush. We're again and again repeating the same thing, that eventually we can see the points lying on y equal to x. That's it. Is that the thing that we see when a circle was becoming ellipse few days back? Yeah, I guess. Right, guys?
Sorry, what did you say?
So Ankit was asking, is it the thing that we say when a circle was becoming eclipse few days back? So Ankit was referring to that. So
You can say that,
okay, I think
No, that was a different thing. Image.
This which I posted, it's like just my intuition, which is I think
Hmm.
will happen when you repeatedly keep on applying it.
yeah, right, correct. This is what's happening.
So
Yeah,
I
like the
think
crocodile mouth. Yeah, this is really cool.
Right.
The thing is like the other 2 points are not moving towards the origin, but it is moving towards y equal to x line. So because it makes difference, little difference as per the image.
Yeah, like farther in the y equals to x direction. It is already in that. It moves just farther on that line towards the infinity.
The vertices in the first and the third quadrant, right?
First and third would be moving farther away, and second and fourth would be moving towards y equal to x, but it is not actually going to merge with origin. So it is
Origin,
just going
but
to
on y equal
merge,
to x.
coincide with the y equal to x.
Right.
The diagonals of a parallelogram form 90-degree or not? I am forgetting it. I guess in case of a square or rectangle only it makes 90-degree. What is it?
In parallelogram, they do, right? They do
Yeah,
make.
diagonals they intersect at 90-degree, right?
Okay, so if diagonals are going to intersect at 90-degree, then these points, two endpoints, will coincide with origin or not? Has these two things got some relation?
It will
Okay, they don't, right? In parallelogram, they don't intersect at 90-degree. I guess they bisect each other, but they don't intersect. Yeah, they don't intersect at 90 degrees.
Yes, not at 90-degree.
They bisect
No,
each
not.
other. That's it.
Yes.
But why are we discussing that? Why
that
are we
is
discussing?
If Mishnor is asking that the points in second and fourth coordinate, they tend towards 0.
Right. So we're seeing that we're discussing whether the points are, the vertices on the second and the fourth quadrant will eventually lie on origin or just y equal to x at some
But yeah,
point
we
on
know
y
that
equal to x.
no. Why origin? If they are going to lie on origin or not is a very trivial thing. Eventually, they are going to get
Y equal to
stuck on a line. That is what we are seeing
here
here, and that should be our
the
area of concern.
dimension reduction, right? There is a dimension reduction here.
Yeah, if we see that the x point moves by the 10% of y, right? So if y is negative, then x will automatically decrease the coordinate of x of the point. So that is why they are closing to each other, coming close to each other, the vertices of the parallelogram.
Yep, if they are negative.
Getting reduced, such a figure comes, right? The one, yeah, the post.
What happens if the matrix is 3 cross 3? And symmetry.
Interesting question.
It will collapse to a plane.
It
I
should
guess.
reduce to a plane by his yeah.
Actually, it depends on what our figure is, right? If it is a plane there as well, I mean, a parallelogram there, then it will again go to a line, right? And if we have
Yeah, if we have a
So it is saying
Say
that
we
we have
have
got
a cube. Say we have a cube. We have a figure in R3. What do
Then
you think will happen to that figure in R3?
it will become a plane if we have a cube, right?
It will become a square
Huh?
Maybe a
in a
cylinder.
plane.
I'm not.
What about the shape?
I'm not convinced.
Not a
Shouldn't it become a
square.
line there also?
Yeah. That's right. I was saying that I'm not convinced that it will
No,
become a
just
square.
Oh yeah, we move in all the directions, right? I mean,
Right.
Yes, we should compress it in from all
all
the directions, which
yeah.
perpendicular to the.
So
Can we okay, let's do that. What was the okay, let's create a matrix. Let's 3 cross 3.
Are you sharing a screen?
maybe
trying
just
to
imagine
open.
our room, it is in a shape of cuboid, or yes, it is in a shape of cuboid. If we are going to fix a diagonal across our room and start stretching and fix one diagonal to the origin and start stretching it, what will happen?
I think it will become a plane, right?
I guess it will become a plane along the 45-degree.
See,
It will
apart
become a
But
from
plane.
shouldn't the corner of the plane also come towards x is equal to y equal to z?
yeah, apart from the two corners that we are stretching, remaining all the corners will tend
When
towards
we
a y equals to x line. When if we imagine in that way, if we imagine a line passing through the two diagonals which we are stretching,
One
the two
diagonal.
triangle diagonals that we are stretching, then the
what
other vertices will also compress towards that line. I mean, will also tend towards that line. Is
So one thing, like whether it will compress to a line or a plane, because at the first instance, I believe it will be compressed to the plane, the 3D. After that,
No. It will get compressed towards the line. If we are going to think 3D wise, geometrically, what intuition we get is that it will become a plane. But if you see, the pattern, then it will become a line only. A pattern
All the
maybe in the
vertices
no.
which do
If we say what just sir did in NumPy, fine. What will happen that we are going to apply a function to a given matrix, to a given vector. Fine.
Okay. So can somebody
Repeatedly.
yeah,
tell
let's
me?
try for a matrix.
So there will
What
be a distortion, continuous distortion with each
still think it's a plane, but like how do you think it's a line?
That metric. Sorry.
all the points which are not on the line, x is equal to y equal to z, all the vertices, they will tend to come towards x is equal to y equal to z.
still it will be a vector only, the result. See, x is equal to b. Fine. A is the function, x is the variable, and b is the image that we are going to get. So the b will be a vector in 3D, in 3 dimensions. You're
Yeah,
not
guys,
audible,
if we
Maria.
take an example and try it using matrix, and also if
Or is that going to show up in a plane? There is the c thing. X is equal to b, not c. X is equal to b. If b, the image which we are going to get is whether will it be a line or it will be a plane. We must
It will be a line only, vector, because
line passing through 3 different line across R3.
Okay.
yes.
So do you think
Hello? I think it is going to become a line because if we consider
okay,
three,
should we try it on Python? Can we run it and see if on
yeah,
Python?
please. So we can plot on
But
GeoGebra
in
as well.
3D, it's difficult to figure out the equation of the line, right? If we get the metrics,
Yeah,
even
yeah.
if we
So
get to
Not
the
in
metric.
not in Python necessarily. We can also do it in GeoGebra because
okay, okay.
it has we have got freedom up to 3 dimensions. But when we are going to go to the higher dimensions,
Okay,
we'll
okay,
have to rethink. But
just a second.
if we are successful in plotting in getting a pattern in GeoGebra in 3D from 2D 2D and then 3D, then we can generalize it that okay, every time we are going to going to get a line only.
Okay, we have a 3D plane. So what should our matrix look like? That's the first question.
See, there is a function of matrix 1.1 matrix 1 1.1.
Is it the function? Is the name of the function matrix?
I don't know.
It's capital M, right? Maybe most of the things are capital M.
No, it doesn't. So it's matrix rank. Is it the same function?
I
No,
haven't
no,
used
no.
CSM.
It's a different mate.
So
Okay.
matrix rank probably
No,
gives
no,
you the rank.
no.
How
Do
will
it.
you?
Do a column-wise multiplication of variables.
We'll have to save the output of the first time. So.
See, write first column.
Plot the points first and then.
Okay,
No,
okay,
no,
okay. Yeah,
no,
yeah.
no.
Go ahead. So tell me the point. So what should be my first row in the matrix? That is 3.
And do one thing. See, write it down. I'm telling 1.1.1
1, comma 0.1, comma 0.1
into.
Into.
That is to say, I'm multiplying a first element of our vector v.
Okay, just a second. 1, comma 0.1, comma 0.1 multiplied with.
What was that vector? That v was equal to what? Let us take 2, 3, 4.
2, 3, 4.
I didn't understand what we're doing now.
Yeah,
into 2.
Yeah.
Plus. No, not that plus. After 2.
Actually,
Plus.
he's doing like column picture. So each
column.
is.
Okay,
Exactly.
you're doing column picture. Okay. Okay. So you need. Okay. What are the values of?
0.1.
0.1, comma 1.
1, comma
0.1. Okay.
Yep.
Multiplied with 3.
3.
Plus. We want 0.1, comma 0.1, comma 1.
1
multiplied with 4.
4. Yep. No, press enter. We have got a vector.
Yeah, we have a vector now.
So this is a line only, na?
Yeah.
This
Can
is
you
a
also
line.
put 2, 3, 4 here so that we can see how it transforms?
Correct. Write a vector v is equal to.
Will be a line.
V will be line, of course. So how it is transforming, we'll see, no? 1.
Okay, v equals to
2, comma 3, comma 4. Not 1. 2, comma 3, 3, comma 4.
4. This is our vector.
Also now also plot a vector, you know, vector u is v dash or u is equal to 2.7, 3.6, 4.5. 2.7, 3.6 and 4.
Directly equal to a, right? Or not? Because a is having.
Pardon?
A is equal, u is equal to a. You can also do that.
Okay, yeah, let's do that then.
Fine. Change the color.
Okay, then change the color.
Or any color of any one of them. Fine. Cross it from. Fine. Close it. Go ahead.
Right.
So we have transformed this vector to this point. Okay, so earlier it was making an angle of 45 degree point with the x-axis. So what about this vector that we are getting now, 2.7, 3.6, and 4.5? Is it going to make a degree? How much angle going to make with all of the axes?
I think the coordinate which was the least has increased the most. So we can say that they are trying to get equated.
Equated or what? Srivinay wants to say something, I guess.
Yeah, I feel we can do this the same way we did for two dimensions. I have written the piece of code, only 3 lines.
Okay, okay.
What are we trying to do? We are trying to see what if I apply this matrix again and again, where does it lead to, right? So we should just do what Sir did, right? Sir took a matrix 1.1, 0.11, and he applied it. Applying it multiple times is nothing but the composition of it. So that's just powering or multiplying it 100 times, right? So let me just.
Sorry. Yes, we must multiply it multiple times and see for the result, and for that we'll need a program. Correct.
Right. So this is our matrix, which is 1.1.1, 0.11.1, and 0.1.11. And I did it 100 times. So can you see something?
Right.
Same thing, correct.
This thing you can observe.
Multiply column.
We must multiply, we must multiply
with
m
some vector
with the initial vector, that is 2, 3, 4.
Okay.
Multiply it with the column vector.
2, 3, 4.
But I applied this approach of calculating this m to a certain power for the question that we solved yesterday, both the questions. And what I observed was we were getting something of similar, like it was just it was just shifting towards a certain direction that to distribute our money equally. And if I multiplied it by 1,000, and I've just added to that sheet we were working on yesterday. You can check that also.
X is equal to Y is equal to Z.
Yep, 45 degree. With every one of them, because yes, tan theta is equal to 1.
Means no matter the dimension of the matrix, it will always means
they
will all become equal.
It will get aligned if the function matrix is symmetrical. It is going to get aligned along a line which is equally inclined with all of the axes.
Okay. Thank you.
So what happens if we just change that to vector, like instead of 2, 3, 4, 2 minus 3, 4, like only one
Same
by.
thing. Just let us check it now. I guess nothing will happen.
Yeah.
It will the
Values
inclination
are getting changed.
Still the
So,
inclination is
like-
same, I guess. Isn't it?
Yes.
Yes. Just
Values are of course
I'm just
changing.
trying to see whether it will come as a line or as a plane. That's so.
Matrix XYZ, this is a line only, na?
Output will
This
be
is
always a
actually we are
vector only.
Yeah, vector. So that's the thing. Like if we just give a cube or something like that, then we okay. Otherwise, we can do one thing, like for a cube, there would be some 8 end points, right? So likewise, we can give some 4 points or something like that, and we can come to some conclusions.
Okay. I want to ask a question actually. How many such points, how many such vectors do you have to check to find whether it is going to a point, line, or if it's going to a plane?
Maybe because the cube would be having 8 points, right? So
okay, so wait, let me ask this question. When I checked for 2 minus 3 minus 4, if this is going to a plane, then what all can you conclude about 2 minus 3 minus 4? Maybe okay, maybe it's a little
Actually, it
fast.
is not going to plane, right? Because that is also a vector, minus 1.38. That is also a vector.
No, this could be a point on the plane, right?
Yeah. So that's what, like, point on a 3D. That's it.
So the opposite diagonally means if we look at a cube, so if the diagonally opposite points are not coming to the same point, then we can say that it is a line. It is a line and not a plane.
Yeah, then we can say like that. Yes, diagonally opposite points.
But actually, I can say that from here, right? If this is going to a point or plane or the line, this is saying this is okay. What is the first column saying? It's saying where 100 is going. This is telling me where 010 is going. This is telling me where 001 is going. Aren't these three independent vectors? 100, 010, and 001. Oh, they're not going to the same point, is it? So okay. So where is 200 going? If I check for this, it should be enough, right? Do you understand? Okay, maybe I'm wrong, but let me check once. So if I do 200, it should, yeah. So now do you understand that it's not going to a point, but it's going to a line? At least it's not going to a point.
So you are saying it is going to a line, not going to a plane. Is that correct?
No, I don't. I haven't said about plane yet. I'm saying it's not going to a point. Obviously, because I checked it for this. Yeah.
Yes. It's
How do I check something else?
so
How do I
like
check
a
that it's
minus
not
200. So opposite direction point. If you take.
Yeah, but that lies on the same plane as this. So if so,
Oh yeah, diagonally opposite we need, right? Yeah.
I want something that is not in the plane of this, right? Actually, this is
Need to
not in a
come
plane
to
of this.
imaginary things. Imaginary
But
geometry
any
thing,
two
like.
points can lie on the same plane, right?
Yeah, exactly. I have to think of
Okay.
it. Hello?
Okay, good job, guys. Going very good, but then it requires some sort of wisdom that you will get ahead of time. And then we'll revisit this and then see what happens to symmetric n-cross-n matrices. But symmetric matrices are very important. But I don't understand why are we studying symmetric matrices. I just like that a teacher simply comes and says it's important and we all think that, oh, it's important, aage aane wala hai. And aage kuch nahi aata. We all know that. Oh, this is heavily applied, complex numbers, blah, 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 and then you don't see an application. Right? You should hold the teacher by the collar and then ask what is the application. Let me ask you that question. If yesterday's matrix were to be symmetric, what does it denote? Go ahead. Question is complete, right? All of you got the question.
So can you repeat once?
Someone can repeat on my behalf.
So is saying that if yesterday's matrix was symmetric, then what could we observe? Yesterday, as in I presume the MSAB thing, right?
Yep. If
Okay.
Sir is saying that function matrix, if that is yesterday's function matrix, a symmetric, then what different conclusion would we come at than what we came at yesterday?
No, not conclusion. He's just asking it. What does it denote? What does it denote?
Yeah.
Because
four people.
Because then we are
money.
looking at then we are looking at a symmetric matrix. Yeah.
Correct.
Because
Exactly.
What does it mean? If everyone is keeping the same amount of money to themselves, that's what it means, right? Because if I look at SS, which is the first entry, is it okay if I can share my screen?
Sure. We are not talking about the king's problem. We're talking about all of them are equal problem. Some 4 people. Okay.
Yeah. Okay. So S M. Okay, sorry, I should keep. Maybe I should. My bad. S A B M and S A B M. Right. Now, what does it mean for a matrix to be symmetric? Everything over here is equal
Upper
to everything.
triangle and lower triangle values are same, right?
Right. Yeah. Okay. So let's make it equal first. Say this is 0.1. This is also 0.1 then. And this is 0.2. This is also 0.2. If this is 3, this is also 0.3. And if we are doing this, then the value over here has to be anyone? The sum has to be 1, right?
0.4.
0.4.
0.4.
0.4 then.
Okay. And then okay, here A is giving B 0.4 and A is giving M 0.1. If she's giving B 0.4, okay, now I kind of understand. Okay, now I kind of
Giving and getting.
Rows are also becoming equal to 1, sum of rows.
So what does this become?
This should be 0.3, right?
0.4, right?
0.4, sorry.
And it's fine. This is also 0.1. And this is
0.3. 0.3. And this should be 0.5.
0.5.
Okay. Now we're looking at a symmetric matrix. Now, yeah, let's make observations.
Yeah. So whatever A is spending on S is getting from S again. So whatever A is spending on B is getting the same from B.
What is denoting what S is spending? Can you tell me?
Like for example, the first column, first row, like S is 0.4. That means A is retaining back that 0.4.
Okay.
40%. So on the next one, 0.21. So that
This
is
one?
like
The column. Okay. Yeah.
Yeah. So 0.1, one is like for A, S is spending, that is S is giving 0.1, 10%, and another one is like he is getting 10% from A. So he is giving 10%, he is getting 10% from A. So
Let's
it is
not
like
jump
equal.
here. Right? Okay, no. Let's not jump, right? What if A's 0.1 is different than S's 0.1? That can be the case. So let's not jump there. You understand? What if A has 100 rupees, but S has 200 rupees?
If you could do it with a smaller example,
Okay.
I think it will be helpful if we keep it
Okay.
2 close to.
Yeah.
No, 2 cross 2 symmetric. Okay, sir, is it okay if I go with 2 cross 2?
Sure.
Okay, let's start with the 2 cross 2 then. So let's say there are only 2 people. There is your name is.
Copy the first two from there. From that
Okay,
table.
that works. Let's go. S and A. I can't copy it, but because the values has to sum up to 1, right? This is 0.4. This has to be 0.4. Symmetric.
0.6 and 0.6.
6. This has to be 0.6. Why does this have to be 0.6? Can what's your name? I'm sorry. Someone who was asking for this to cross symmetrics.
Because it should be
Yeah.
symmetric. Also because it should add up to 1.
Yeah, add up to 1. Okay, cool. That's why we have to put 0.6 there. Okay. Now what are we saying?
Now you can multiply it with a
No. Okay,
2
you want to
plus
start
1.
multiplying? No. Let's not multiply. Okay. Let's think of it first, and then maybe we can multiply later. But what does this mean? What does it mean? What does this mean?
That A is taking 0.4 from S, right?
Yeah.
And this is for 0.4 he is keeping for himself.
0.6, right?
0.6 is S keeping 0.6 for himself, right? So
Yeah,
it's like the saving for S.
Yeah.
It's like you are giving me 40% of your money, I am giving you 40% of my money.
Yeah, perfect.
If I have lesser money, I'll be giving you less. If you have more money, you are giving me more.
Can you also draw like this thing in Cartesian coordinate? You will see that the rate that this two vectors are shifting from the x and y axis are towards this x is equal to y line, towards that equality line that we saw just a few moments back, that converging in first and third coordinate. That thing
we worked with so okay, I'll tell you what we did. We worked with symmetric matrices. We saw its properties, and now what we're doing is there a application for symmetric matrices? Right? Now we're looking at a symmetric matrices which might have an application. That's all we're doing. So whatever property held before is held now. So we should not forget what we learned before this. Whatever we learned before this now applies to this particular matrix as well. You're right. It'll keep, it's moving towards x is equal to y line. You're right. Anything else?
Maybe we should, focus on happy and stressed matrix. Sir is saying that.
Oh, I didn't check that. Use the happy stress example, draw the diagram and see what happens when it is symmetric. Perfect. Okay, let's do that. So let me even keep this here as happy and stressed. Okay, my bad. Stressed, and the values were 0.3 points. Oh my god, I have ratified this number. What this distribution is. That's very nice. 0.7 and this is 0.5, 0.5. Okay, and the diagram of it will look like.
And you have to keep it symmetric also.
We want to keep it symmetric. I'm sorry, my bad. So if we want to keep it symmetric, let's not use 0.5 here then. Let's just use 0.7 here, and this has to be 0.5. Okay, so this is happy. To happy is 0.3. To stressed is 0.7. And loop to stressed is 0.3.
This is like the same condition that we saw, that when each entity is performing performing well at both the ends. When we have a symmetry.
Just by looking at this diagram, can you say how many people will be stressed and how many people will be happy?
So 50-50, it should return eventually to 50-50%.
Without any math, by only English, can you say how it's 50%?
So
initial things we need to.
Like we can see this matrix, we are multiplying A times A times A, but each time we are multiplying it with we are just when it is the initial x entries, it is being dominated this by S, that is 0.7% value. That is y is being incremented as compared to the x, y has been shifting more towards X.
Very, very less details. Only English, 7th standard English.
Outflow is equal to inflow.
Correct. More Srivina in that direction.
So, I mean, how much ever, I mean, whatever I'm retaining and keeping and getting from the other person, right, is
The
just
sum of input output of both the entities are equal.
sorry. Can you restate that? Sorry, I
I was saying that the sum of input and output of both the entities are equal. Both H and S are equal. Like the intake number of people and out
Right.
number of people for both are equal. So it should eventually be 50-50. Like that.
That thing is same now, that each entity is performing quite well at both the ends. That
Yeah.
is retaining and transferring. That is the same thing, no?
I mean, you defined it in your head good, performing well, but I don't know what performing well means, right? Yeah.
I was
Yeah.
not able to express
Exactly. It's okay. I didn't understand what you meant by performing well. It's okay. Yeah. Anyone else?
So basically, if there are two entities H and S here, right? Initially, if one entity is having less value also, so that 0.7, like 70% of that value initially be less. So one value will be increasing, another value will come on decreasing. Once the values are around equal, so the in absolute terms also that 70%, both the 70% instead of inward and outward, both will be in absolute terms also it will be same. Once that values are fixated, it will be remain at that level only.
Perfect. Yeah. Can everyone see that? That even if the values are different at first, right? The one that has more will be giving more, right? 0.7 is going away, right? While the other person who's giving, the 0.7 of his value is very less, right? So he will be reducing less, but getting more. But this person will be reducing a lot, getting less, right? So it will keep happening until we
They
kind
become
of,
the same.
yeah, kind of become the same. So is that the right intuition we want to get?
Yes, perfect. So imagine this problem is slightly changed into H has milk, S has water.
Right.
At any given time, you're putting 70% this side and 70% this side. Yesterday's discussion, basically. Right? Whatever you had here will go, water mein milk add hoga, milk mein water add hoga. Same proportion. This will converge to half milk, half water in both sides. Okay. So now how if we were to, what if we were to model this as water, milk, and Ruh Afza? Ruh Afza, you all know, right? Or chocolate. Water.
There will be two entities, two inputs for every.
Can someone write down a symmetric matrix involving coffee, tea, and Ruh Afza? What am I saying? Water, milk, and Ruh Afza.
Point 1, point 2, point 3, point 1, point 6.
You can basically write whatever you want and reconfigure it to make it 0.2, and the remaining should be 0.5 there and 0.7 there. 0.7 there. Okay, water, milk, and Ruh Afza. Guys, what's going? Ruh Afza is that rose milk. Okay, R for rose milk. The rose tonic, basically. What will happen eventually?
Sharbat.
everything becomes like
No, I said 7th standard version, not a 3-year-old version.
0.3 point, sorry, like
Yeah,
33%.
0.3, 30%, 33%.
Now, again, I would like to say wisdom in purple and then say you don't have to do anything. You don't have to do anything, you can tell the answer. Don't guess it from the previous answer, that may be wrong.
Yeah.
Write the diagram and then guess it. That will be easy. Write on the diagram. WMR. Anyone who knows the answer can direct message me. With this, we'll walk into factorization.
Can you repeat the question now?
Perfect. Incoming, outgoing arrows will have the same. What does this mean in English? Again, 7th standard syllabus, 7th standard thinking only. All of them are retaining a bigger proportion, you see, different proportion rather. MCA container, milk's container retains 50%. Water container retains 60%. Row of the container retains 70%.
So each container will have equal amount of liquids, equal amount of the 3 liquids.
How do you say that?
So by seeing the previous example, but
And I told you not by seeing the previous example, because here 0.6, 0.5, 0.7. This is different, right?
yeah.
But in several iterations, it will be coming to the equal, right? Like for the first iteration, it will be looks dominant. Like for example, R will retain most of 70% to it, but on several iterations, it will mix up with milk and water, and milk is already mixing up with water. So anyway, maybe at last it has to come to a point where everything is equal.
Not equal, but an equilibrium point. They might not be equal. All 3 might not be equal, but they eventually they will come to a point and become stagnant.
So at that point, the concentration in every container will remain same then after.
Right.
Right. Maybe.
Tell me the first row, matrix first row.
0.6, 0.3, 0.1. Second one is 0.3, 0.5, 0.2.
First one is 0.6,
0.3, 0.1.
0.1. Okay.
Second one is
one moment. Okay. Second one is
0.3, 0.5, 0.2.
okay.
Was the third one 0.1, 0.2, 0.7?
Yeah.
Yeah, 0.1, 0.2, 0.7. Right.
Comma before point.
Correct?
Okay.
Or a good way to do this is multiply this on a matrix, which has
Yeah.
which had 100 rows. It says 100, 100, 100, but it's mixing three beautiful glasses of equal proportions of water, Ruh Afza, and milk. Nothing can be a better illustration of this point as an application of matrices. Why is this happening? What are symmetric matrices to do? We'll discuss. One of the most beautiful properties of symmetric matrices, now I'm going from 7th standard to 17th standard, okay, which is master's degree roughly, is symmetric matrices have orthogonal eigenvectors. That makes it very beautiful. Okay, what am I talking about? Let me give you a small illustration. Okay, now we'll get into some non-trivial matrix discussion. Are you all in for this, guys? In? Anyway, it's 11:25. Only interested people are around, I guess. So if we go something advanced, it shouldn't matter to you people. Sometimes it's important to go a little advanced and then not understand many aspects of it and then backtrack and then slowly understand. In that spirit, I am taking you people at 100 kilometers per hour while we have been going at 30 kilometers per hour, so that on one day when I take you people 100 kilometers per hour, you will feel comfortable going at 60 kilometers per hour tomorrow. Okay, while we have been going at 30 kilometers per hour this way. All right, so here goes my matrix A. A is symmetric. Most of what we discuss holds good for non-symmetric too, or non-symmetric. In general, A is a matrix. Yeah. Okay. I'll write A and multiply it with a vector V, some vector V. Let's say 1, 2, 3, 4. I'm going to multiply it with a vector XY. This will give me what? Can someone? Okay, so let me do this using GeoGebra for a minute. Okay, all of you understood, right? 1, 2, 3, 4, XY. That's all. Let me open GeoGebra and then share the screen with you people. I'm sure you guys are going to have so much fun right now because you're going to observe something really awesome that you may not have understood so far. Okay, I open GeoGebra, I start the calculator, and then I say my matrix M is equal to this is how I think you denote a matrix using GeoGebra. Okay, perfect. 1, 2, 3, 4, and a vector V, which is a column vector, which should be X, comma Y, M times V. Okay. Just give me a second. until I tell you people, don't worry about. There we are. What's happening, guys? V is my vector, right? Okay, perfect. V is my vector. Let me call it blue. Color is some blue. Okay, let me call this vector as red. Right? As I'm varying V, my U, which is M of V, is varying. All right, all of you done? Can someone unmute to tell me what is happening here?
V is getting
When
transformed to you.
When two cars are coming in the opposite direction, they must collide, right? Assuming the road is not spacious enough. They're colliding. You know very well, if you're moving this way, this vector is coming slowly towards you. You have to hit this vector. You hit the vector here. You hit the vector here. Wait a minute. I'm hitting the vector here. I will just write this down in the form of the equation on my iPad now. I will share the screen. Whatever I have done here, you all have seen. I'm going to write this down in the form of a matrix. I'm saying that A of V, there exists a V, so that this is equal to alpha V. बस scale हो रहा है और कुछ नहीं हो रहा. Correct? What was that? What was that? हाँ, बस स्केल हो रहा है और कुछ नहीं हो रहा, राइट? यहां पे भी बस स्केल हो रहा है, यहां पे भी बस स्केल हो रहा है, अल्बर्ट इन द नेगेटिव डायरेक्शन, लेकिन स्केल हो रहा है. ठीक है? सो स्टॉप शेयर, शेयर, शेयर my iPad, share, share. So some vector 1 is becoming alpha times V1 and another vector is becoming alpha 2 times V2. Rest I don't want now. I'm done. I took any random matrix and this is happening, guys. Go to GeoGebra and try the same. Let me share GeoGebra's stuff with you so that you all can try it yourself. Please wait. A lot of magic will happen right now. So many matrix ideas will come right now and then you'll say, oh my God, this is too much to take, but this is still beautiful. Beautiful in the sense that itna sara ho raha hai. 10 minutes mein khatam kar sakte hain. A lot of stuff. Okay, here's your.
So the screen is blurry.
Comment window. No, wait. That's on purpose. Yeah, GeoGebra, go there and play around and detect that vary your matrix 1, 2, 3, 4. Still, you will find two places where it will get scaled. Okay, all of you do it. I will take a minute's break.
Anyone who doesn't have a laptop, maybe. Everyone is on the laptop, they can do it, right? Everyone can. Awesome.
So this suggests that, eventually input vector coincides with the output one.
Yeah, it's just a scaled version of the
Scaled
input
version.
vector. Yeah.
Yeah.
This is happening for any matrix.
Any matrix.
There's always two, for a 2x2 vector matrix at least, there are always two such inputs for which the output is a scaled version.
So the idea behind this is that we are going to repeatedly apply this function matrix, isn't it? And eventually we are going to end up on the input vector. Is this correct to say? I'm not sure about it.
Yeah, I mean, we'll find the scaled version of our input vector like that. Huh?
Here, when we are moving V, you will also note that when we are in first or third quadrant, the U is also in the same quadrant. But for the second and fourth, the vector is moving in just the opposite quadrant, U.
I guess that depends on our matrix, right? If we change the matrix, then it will act accordingly.
No, the area for concern is that what we are going to give that as input. That is, the output is going to coincide with that.
Need my help? Any clarification required? No, right? You write any matrix, there are two places where it simply gets scaled. The transformation is simply scaling in two places only.
Right.
Not in three places.
So even at the matrix you have sent, it is not coinciding at all. So you're on mute.
No, it should coincide. Check it.
1, 2, 3, 4, right?
1 minus 2, 3, 4.
1 minus 1, 1 minus 2, 3, 4.
Yeah. 1, 2, 3, 4. Assume you're taking only positive numbers.
Okay. So
for the time being. There are always exceptional matrices where this doesn't happen. For example, if you put rotation matrix, whatever arrow you get, it keeps rotating only. So, Srivinay, did we discuss this on one of our discussions in the last week? No, right?
No, we haven't discussed this.
Okay, good.
Last time, I mean, what do you mean by last time? Meaning last year?
No. In the recent times.
No, we haven't discussed.
Then you guys will like this. I just was fearing that I'm being repetitive here. Yeah, if you all agree, we'll go ahead. Try this.
Will the coinciding always happen in like different quadrants?
Not necessarily.
I was looking at examples and all of them were coinciding in.
Yeah. You will vary X and Y slightly. They can coincide anywhere actually. But very likely it will happen like this. If all are positive, I'm sorry. Can we continue? Or you guys are exploring? Feel free to explore. All I'm saying is, given any matrix, there are two places where it just scales. They are called the eigenvectors. This is a definition of eigenvectors, no? A of V1 equals lambda 1 V1. No doubts? Why is everyone looking puzzled? Go ahead. Ask me if you have any questions.
So this has got nothing to do with the previous question we were dealing with, that we were multiplying multiple times functions.
Yes, it has everything to do with that. We'll get there slowly.
I tried for dependent vectors in our matrix. Still, it works for that as well. No?
No, it will not work.
It will just scale only. No direction will change if they are dependent columns.
Right? It's only coinciding in one line. There's only one line to coincide at. It's either coinciding here or here. Which is nothing but the first one is just a scale, like
Yeah.
scale is nothing.
Yeah, we are finding that only, right? Where does it coincide?
It's coinciding only at one place.
At the two places, this thing and the.
If you think about it like that, then it coincides in 4 places.
No.
Because no, not. So Ashik is thinking, okay, if it coincides at say 2, 1, right? It will coincide at
-2, -1.
exactly what I'm. Yeah, you understand that point, right? See, that is still coinciding the same point. That is nothing but saying positive. I mean, multiply that. But look at the other. There'll be one more place where it will be coinciding.
When our
Okay,
vectors in the matrix are dependent now, our movement is restricted to a single line. Our second vector does not move at all now.
Yeah, I'm just sharing my screen. So this, right? Here it's coinciding. This is one coinciding. But this is the same as this coinciding. Because this is on the same line.
A line.
Right? But this is also a coinciding. So this is the second coinciding value.
Scaling.
Right? Yeah. And if you take
1, 2, 2, 4.
Sorry.
2, 4. Yeah.
They're lying on a straight line on 4 different location points, right?
Here.
This is one. Yeah, this is. Oh, yeah,
Is
this
this
is.
also one? I'm not sure. This you can.
Yeah, they're on a straight line, right? Both. Okay, no. What?
Because
Yeah,
when
what
the,
I observed is that as we approach towards the 90-degree angle between the two vectors, one of the vector diminishes to 0.
that flip is also one point where it's coinciding, is it?
But then that M1 is same in opposite
Okay,
direction.
I
as-
understood.
Your
I
M1
understood.
Your
I
M1
understood this
goes
one.
only in a straight line, no?
Yeah.
Sir,
Of course,
sir.
it meets. It's the same. There's only one eigenvector.
No, sir, but this okay, but okay, okay. Can I use a term here which might confuse other people? Maybe other people can not say. So this is the null space of that matrix. At the null space, it is coinciding, right, sir? Right, because 0 is part of this vector.
Okay.
So isn't this also one
0
coinciding?
is always an eigenvector. Vacuously. You see, a matrix application on 0 will always give you 0.
Okay, yeah. So okay. Then I could have said that it coincides at every point. You're right.
And there's also another vector which will take it to 0. That's what is happening. Bring that v here. Yeah, that's because given that it's a null space. In fact, now as you vary v, this side, that side, it will still go to 0 only because there's a null space direction. Anyway, so let's not. Null space is something that only me and Sri Vinay discussed. Others did not hear that because you don't have to hear that right now. Don't worry. Now you have two vectors, right? Look at the interesting twist to the story now. It gets extremely interesting. Things become magically beautiful. This looks like it was dropped from heaven, but don't worry, we'll give you the intuition for it eventually. I'm going to share my screen now. So a lot of fun math, magical math, quick math will happen right now. Concentrate. So you're saying that A is a, let's say, 2 cross 2 matrix. When multiplied with V1 will give you lambda alpha 1 times V1. Correct? Similarly, A when multiplied with V2 will give me alpha 2 times V2. You see, this is how matrices behave. You can see this V1, V2. What are V1, V2? This is one column matrix. This is another column matrix. Correct? You can simply stack this V1 here and V2 here, and this becomes a 2 cross 2 matrix. All of you with me? Thumbs up. And this will be equal to alpha 1 times V1 as a matrix. First column ye hoga iska. Alpha 2 times V2 will be the second column. Discuss if you didn't understand this. Right? I'm going to call this matrix as, let's say, M. A times M is equal to this stuff. And this stuff can be written actually as, what can it be written? Let me think. V1, V2 matrix, simple observation, times alpha 1, alpha 2, 0, 0. I'll stop here for a minute. And this became my M matrix, right? M was the same. So AM is equal to M times my alpha matrix, or A is equal to M times my alpha matrix times M inverse. This is like a, oh my God, matrix factorization that keeps coming in your life and makes your life hell. It is simply this. Okay. What is this? Let me write that down once again. A is equal to V1, V2 times alpha 1, alpha 2, 0, 0 times V1, V2, the whole inverse. Can someone tell me what would A square be?
Alpha 1 0
M alpha square M inverse.
That's it. M alpha square M inverse. Similarly, your A to the K is equal to, which just means you just go inside the diagonal and then raise it to the power of K. Don't you think this is an easier way of calculating the power of a matrix? You're not raising a matrix to the power of K by taking all possible dot products of all possible rows with all possible columns some K times. Right? You simply go to the center and then raise the real numbers to the power of K. Wisdom, A to the power of K is very easy if we know A's factorization as M alpha M inverse. Okay, this is wisdom. Second wisdom is, similarly, A inverse is also easy. Why? Because A is M alpha M inverse. A inverse, try this out. कैसे A को invert करें? इसको M डालो, ये identity हो गया. उसके बाद alpha inverse डालो, ये बंदा identity हो गया. उसके बाद M inverse डालो, ये पूरा जो भी है will become identity. So this happens to be the inverse of this. That's all. So A inverse is equal to simply invert alpha. What do you mean by inverting alpha? A inverse is retain M as it is V1, V2, and your alpha 1, alpha 2, 0, 0 matrix. When the matrix is diagonal, all these inverting things become very easy. Simply invert them. That's all. From when did matrix inverse become inverting a small real number? Wherever you know its factorization. Makes it very interesting. And now comes the climax, and we end with this today. The climax is, if A is symmetric, one can verify this. It's some simple 12th standard level math. You just go on manipulating, you will get. If A is symmetric, and if you can write A as M alpha M inverse, you see finding M and its inverse is difficult. But if A is symmetric, transpose is the inverse. If I'm sorry, not symmetric. If A is symmetric, M's are all orthogonal. If M's are orthogonal, M and M inverse is same as M transpose. Oh, a lot of talking. Slowly watch what I've done. Go very slowly. I've given everything. I've shared the link with you also. Go very, very slowly. I purposefully was a little fast here. Can someone share the link of my note on chat? I would say linear algebra is over if you have learned this much. There's nothing much. All these things will now feed whatever we have learned. That matrix of 0.99, 0.01, happy stress, the king's rule, All those things, we'll see it in a brand new light now. Revise this completely. Go ahead. Take your time. I was a little fast at the end. If the eigenvectors are perpendicular to each other, which by the way happens if A is symmetric, eigenvectors are always perpendicular to each other if A is symmetric. Very easy, assume that. Then your transpose will be your inverse. Why? That's easy to observe. When two vectors are orthogonal, you multiply them, you'll get 0. If you multiply the vector with itself, you'll get its norm. Right? So when you multiply those such vectors on the diagonal, you'll get the norm. In the rest of the places, you will have 0. Simple observation, that's all. If you're unable to observe, take your time, write it down, and you will observe. Go ahead, discuss, finish this.
In a way, everything boils down to finding eigenvalues, and then our task becomes easy to find inverse.
Few days back, we was stuck on this transpose things, and here this thing of a inverse and the transpose thing, like when they are orthogonal.
Let's try to work with what, okay, that's what we've, the information that we got now is a lot of information. Let's try to process that first and then try to connect to what we tried a few days back. Let's try to connect, like, what has been given to us. Let's try to read it, comprehend it, discuss whether our understandings are clear, ask any doubts if we have, and then we'll try to connect. Is that okay?
Okay.
Yeah.
Yep.
Scaling or reaching one. What's this nature of alpha one? But I was I was late. I just joined around when most of the today's session. I might be missing a gap. What is the property of alpha one itself?
Just scale.
Scale.
Just scaling.
Yeah,
Just
either
be-
it
could
or
be
power,
any.
or it is simply that it denotes simply that it is a scaled version of V1, nothing else.
Scaled, by scaled, we mean just by the magnitude?
Yeah. It is the magnitude by which our vector V1 is scaled.
Okay. If we consider that.
Yeah, I'm sharing my screen just to talk about what you thought you might be missing, right? So there is some input for this. So the matrix is 1, 2, 3, 4. And V is the input to that matrix. You can see it here, M times V. And there is some input V for which the product is just a scaled version of itself. So that is alpha. The scaling factor is alpha 1. And there is
when they are when they are coinciding, na, at that time.
Yeah, and there is one other place here where they are going
opposite to each other.
Yeah, yeah. So here, this vector is just being scaled in a negative direction and scaled down also, right? Those are the two things. So alpha 2 happens to be some negative value which is less than 1. Right? You can, I mean, so though we are trying to generalize it, it's also nice to see that, okay, alpha 2 is a scalar which is maybe negative. It has to be negative because it is
scaling it down, right? We are scaling it down.
It's flipping. Yeah, it's going into the opposite direction, all the way from here to 0 and the other way, so minus. And it's also scaling it down, which is the magnet. This length is smaller than this length. Yeah. In this case, it is scaling it up and the same direction, right? So alpha 1 happens to be some positive number which is greater than 1. So this is some observation I'm just making, just to understand what alpha 1 and alpha 2 might be.
Alpha 1, alpha 2.
What if I do?
Okay, means we are considering these things when these vectors are coinciding or are just simply the scaled versions of input to output. At that time, we are considering this alpha 1 and alpha 2.
Maybe we should, start from the today's lecture where Sir has mentioned 7th October. Fine. Let us go step by step from there. Maybe we can, connect the dots.
No, let's not connect dots. That's what I'm trying to say. First of all, what is given here, let's try to understand it because this is not something, I mean, it's a lot of information, first of all. What Sir says here, what does this mean? What is the meaning of a matrix multiplied by matrix here? And what is this matrix? What is this matrix? How is it equal to this?
One second, please repeat it again. I was seeing my own screen.
Yeah. So this is a matrix A, and this is a matrix V1, V2.
Fine.
Right, with columns V1 and V2. What does it mean? Okay, when we did A square, right? We did A square before, right? When we did for this, we took the matrix and we did M into M, right? Which is M square.
Fine.
We said that was applying M 2 times.
Fine.
So what does it mean here to take a matrix A and a different matrix with different columns V1, V2? What does this mean? I mean, I'm just posing questions now. Let's not jump here. Let's go step by step itself. I mean, there are a lot of questions that we want to clear over here before we try to connect to concepts we learned in the beginning, right?
What we used to call a column image thing. Fine. Try to go by that. What Sir said at that point of time was that we have got.
Is not this thing quite easy to get? What we essentially are writing in this VM thing is simply AV1 gives column 1 and AV2 gives us column 2.
Exactly. What does it mean to take a product of two matrices? We saw product of a matrix and a vector, which means it's just taking the vector and transforming it, right?
That just means that the matrix times single vector will give column of that vector only.
Yeah.
A single column.
But what does it? Yeah, but what does it mean if I think about it like this? See, this particular part of the equation is telling me if I apply the matrix A on V2, which is a vector, right? What it's
Yeah.
doing is scaling that vector, right?
Yeah.
I understand it because it's a vector, it's scaling it.
Fine.
But what does it mean to take products of two matrices itself?
See, prima facie, A, we are what it means is that there is a matrix A and there is another matrix V1, V2, and
M,
then
let's call it M. Yeah,
let
M.
us call it M, and it is going to yield alpha V1 and alpha 2, alpha 1 V1 and alpha 2 V2. What does this mean? If we were doing it individually, that it was yielding alpha 1 V1 only. If we were multiplying A to V1, find matrix A to vector V1, it was yielding alpha 1 V1. Now what it is now what it is yielding is that we are now multiplying A to M, which has yet another column, V2 column, which is yielding alpha to V2, which was earlier yielding alpha to V2 separately, is now accommodated in the same matrix. So we are looking at the image of, we are giving multiple inputs, we are giving multiple vectors as inputs, and we are getting multiple vectors as output.
Isn't this also multiple vectors? So
this is a function A.
Yeah. So why is it okay? So this
So you are
matrix
saying-
is a function. Why is M not a function then? Is M not a function?
No.
Why are you thinking of it as two vectors?
Look like when we are writing A times V1 is equal to alpha 1 V1. Here we were also having one's view that when we do this thing, we can also see it as this linear combination. But here what we are saying is that from the GeoGebra thing, that there are 2 points when it is just scaling up. So I think there is a slight patch from this understanding, from this linear combination, when we were just scale a linear combining the this columns of vector A, to treating that A itself as a scaling factor to the vector.
It depends, the thing you just asked is that why do not we consider V1, V2 to be the function matrix? Fine. Or vice versa, how do we know which one is the function matrix and which one is the combination of vectors?
Yeah, what is different between the matrix A and matrix M?
That will, I guess, depend upon the given situation. Okay, I
Okay,
guess
the output is a matrix. What does that mean? The output is a
matrix means a combination of different vectors. This is that what is we call, what we are studying, in our context. Matrix is basically a representative of multiple vectors.
No. Okay, what does the representation mean? What does the representation mean? I wish I could. Okay, I shouldn't write in this. Maybe. What does that representation mean? That representation means a function, which is
at end of the day, yes.
Right. That representation is, say,
a
A,
function.
B, C, D, right?
That is a function.
This might be a vector. This might be a vector, but this matrix is representing a function. What is it representing? Can someone tell me? What is this representing and what is this representing?
The I cap and J cap, right? The vectors.
Exactly. This is saying where I hat is going, and this is saying where J hat is going.
Okay. The unit things I was talking about, isn't it?
Yes.
One thing. Wait. That thing. Can you treat it as I and J means okay? They are individual vectors, but why treat them I and J individually? But that should be treated as A and B association as in the space of IJ, na? Individually. But why name the column vector IJ itself? That is a different point, no?
Can you answer this for me?
See, there are vectors and there is a matrix which is combination of vectors, which whose columns are representative vectors, and there are functions which are representative of I and j, I guess.
So 1 0.
The unit thing.
Your 1 0 represents your I cap, right? And
Yes.
you're scaling
Yeah,
it. So what are you getting? Aren't you getting A, comma B?
Yeah, only AP we will get.
Yeah.
Right?
Yeah.
What does that mean? So your column A, comma B represents your I cap, right? Yeah, that
Okay.
we are
In the
scaling
scale.
it. Scale of it.
Okay.
After
I get it.
performing this matrix function on I hat,
Yeah, I, comma J. I,
this is representing where it takes it in the transformed
right.
output space.
Correct.
The scaled
Right.
version of it.
Right.
Yep.
And the same thing goes for 0 1. This will tell you, this will give you CD. So you are actually representing a function using just two informations, which is where is I hat going, where is
cap and
J
J.
hat going. I am storing it as, so let me say the function is phi, right? So where is phi of I hat going, and where is function of J hat going? This is what is stored in a matrix.
Right.
Right?
Yeah,
Right? Now we understand this view. So we look at a matrix as a function, right? Which is telling us where I hat and J hat is going. Now, what does it mean to take the product of or composition of, however you want to say it, matrix? Let's make it simpler. Let's take examples. Okay. Should I take V1, V2? I mean, should I take the ones that satisfy that property, or do you want to go with general first? I can do this two-step. One is explain it for this, which is general case. Oh my God, sorry. My bad. Oh my God. I don't know. Is it possible to move this Zoom's what is the thing, that options list somewhere else, because I'm not able to.
Okay, do
Yeah,
Control Alt Shift H. Control Alt Shift H.
Alt Shift H. Oh, thank you. Thanks for that. I'm not able to access my
tabs.
Tabs.
If you want that back, just press escape.
Escape. Okay. Thanks. So where was I? Okay. I'm sorry, I'm a bit messy with all the tabs. Yeah. So what? Okay, let's just take another matrix here. 3, 4, 7, 9. Right? I'm talking about a general case. What does it mean to take the product of A and B? What is the output, first of all? What is the output?
So that's 3 plus 14. So that's
No. What is the shape? What is the dimension of the output? What is the output?
Right?
2 by 2 matrix.
Sorry, 2 cross 2.
Exactly. It's a matrix.
Right.
Right? And it is 2 cross 2. Okay. You understood this. If this is a matrix, what does it mean?
Here, cannot we see it like the column 1 of M will be given by the multiplication of A and column 1?
No. Okay. But okay, you're going to the definition and trying to move to this, right?
Yeah.
Let's not use the definition. Let's not use what we know. I want to use very simply what a matrix is, the property of a matrix is, and I want to use that to identify what does it mean to take the product of two matrices. Right? Now, if the output is a matrix, then what will this column mean? What will this column mean?
Space.
How much
Should we
the
consider
individual
that
vectors
space
have been
thing, the
scaled?
span thing? Should we consider that?
No, not span. No, I'm asking you the same thing that I asked you 2 minutes ago. What does the column of a matrix mean?
Vectors.
What does that vector
Scaled
mean?
version of vectors.
That is
Scaled.
final version.
Exactly. So this is also a matrix. This is also a function,
Correct.
right?
Correct.
And this function is telling you where if I apply this function, where will I hat go and where will j hat go?
Fine.
So a product of a matrix with another matrix is giving you
Function, a new matrix. A unit matrix. Sorry, a unit function.
What is a unit function here?
Sorry.
Function unit.
Just
unit.
we use unit for determining the scale. Anyways, it's also giving us a function.
It is also giving us a function. Awesome.
Yeah.
Okay, that's the first thing we want to know. So the output is a matrix, and the matrix, as we know, is a function which will tell us where I hat will go, where j hat will go.
Fine.
So if you are able to represent it in one matrix, why are there two matrices on the left hand side? I mean, see, this is equal, right? So if I apply this, it should be the same as applying AB into V, right? If V is a vector. If V is a vector, M times V vector should be the same as AB times V vector, right? Do you people agree or not?
Can you please
Yes.
repeat that?
Yeah. Okay, let's go step by step. Does anyone else want to explain this maybe? If you have understood? Anyone? No? Okay, fine. So I am saying this matrix on the right hand side, right? Remember a matrix that is nothing but A times B is equal to M. All of these are matrices.
Fine.
Then let me give more space. A times B is equal to M. If I apply M on vector V, then it's the same as applying AB on vector B.
Right. Same thing.
Agreed?
Right.
So this matrix is able to tell you what these two matrices are able to do.
Right.
Correct.
Right? So now let's think about what it means to multiply two matrices.
Now, can we relate if they have been a number, if A and B would have been a number, then there are two views to see the multiplication. One is like adding A B times will give us AB, and the second thing was the area of rectangle. But when we go come in the matrix operation itself, then addition somehow can we translate like in similar basic terms like we do with the numbers itself, this operation of multiplication?
So you're asking if I can multiply A. Okay, so you were saying if I do
I'm saying
A plus A, B times, is it?
I'm not saying. I'm saying like if they would have been a number, then we would have this type of things. Can we break our understanding of A times B matrix in something of similar pattern or something of similar idea?
Oh, that is actually, I think we're asking like matrix property. So one matrix is a function that basically transforms the given input. Okay, so that's one understanding. And the other thing is like we consider 1, 2, 3, 4 as a function, sorry, 3, 3, 7, 4, 9 as a function and 1, 2, 3, 4 as an input. Then this function is about to transform this matrix. So transformation in the sense like whether it may scale up or it may share it up. So how it was doing it for vectors.
Should we
We just visualize it from GeoGebra, right?
should we
So
try to draw this
yeah.
matrices at column vectors of all the three matrices A, B, and M? We might see something.
What do you want to do?
You want to see these things here?
No, I am saying like why don't we draw the columns of this all the three matrices A, B, and M? We might see something.
How would you draw it?
Like vector in GeoGebra itself. 1, 3, 2, 4. Then yeah.
3, 4, 7, 9, and the product of them, isn't it?
Yeah.
Maybe we can do it.
Okay, but I mean, but how will that help you understand what the see? It'll tell you where this multiplication will take you. That it'll tell you, but it will not tell you what does it mean to take the multiplication of these two matrices. See, you can get an answer. I can get an answer. We know the mathematics way to do answer this, answer this, answer this, answer this. Now you know the answer. That's not the point,
What is
right?
it geometrically meaning?
Geometrically, it just means yeah, that's a good question. Yeah, Anamika, go ahead. What does it mean, I mean,
Actually,
geometrically
if we consider matrix as a transformative function, if someone want to see what does the rotation plus sharing would do to a given vector, then we can consider like A as a rotation matrix and B as a sharing matrix. If we take 1, 0 as the input matrix, what would be the resultant matrix? Maybe like if we do rotation plus rotation, then what would be the resultant? What would be the result on the given matrix? Like if we do first rotation and then also rotation, then the transformation will also be a rotation. But if we take deflection plus rotation, like if we consider it as a transformative function, then it will give a resultant.
Okay, actually, yeah, I think, okay. What she's trying to say is she's able to see, she's able to understand that A might be, what if A was a rotation matrix, which rotates all of space, right? That's what it does, linear transformation. It transforms the space, right? It does a transformation. And B is doing a transformation on its own. Now we're doing it one after the other. First of all, first question, what transformation will occur first? Does the order matter?
Can we first point out what does matrix itself represent? Geometrically, algebraically, we know that it's column space, the linear combination, and so on. Is there any view that specifies that we can see matrix in such a way, and
can someone send him the link of, remember this left hand side R2 space and right hand side R2 space?
I have that. Just a second.
Ankit, do you remember that maybe? If you've already seen that, right? What it means geometrically?
Just let me see the link because I joined late.
Maybe. No, not today. We discussed it a few days back also, and we revisited also. What does it mean? What does a matrix mean? What is the question again? What does it mean? What does a matrix mean?
Function, right?
This thing we explored. Yeah, I remember that.
So what is it saying? If I change the values of the matrix, right?
Yeah.
The transformation on the right is being changed, right? And I am instead of trying to say where exactly every point on the right hand side goes, I am saying I will only look at two things. If I know where 1, 0 goes, and if I know where 0, 1 goes, I will be able to say where everything on the other right hand side goes. if 1 0 is going to 1 3 and 0 1 is going to 2 4, I represent it like this. If I take any input, what does it mean to take? Okay, right? Okay, maybe let's visit that, right?
That
One.
Joe thing that sir was saying, no? Closing Joes.
No. You're connecting different things. No.
That was a different thing.
That was something where we repeatedly applied a symmetric function on an input. Don't think about that now.
You just said that if there was a point and if we saw that where it is taking 0 1, and one times we are seeing where it is taking that is 1 0.
Yeah, this part.
It's like we are seeing the transformation of the unit vectors in the XY direction where they are being shifted. So,
actually, why does it help you? Why does it? I mean, how are you able to show an entire? So, how are you able to show an entire transformation with just 4 numbers? How are you able to show it? I mean, we know this is showing that it's taking I hat to this and J hat to this, but how is it able to represent the entire space on the right hand side? Let's take an example and think about it. If I give a point,
we were able to represent the complete space because its linear combination fills the complete space, no? Whatever the input is, we can definitely attain that.
Matrices are very nice functions, right? I'll tell you why. I'll tell you why very soon. So, what is 1 2? This is 1 times I hat plus 2 times J hat, right?
Yeah.
This is going to, can you tell me the answer where it is going to?
Yeah, it's 1 plus 4, it is 5.
5, 11.
It's going to 5, 11.
Yeah.
Now, see this. I'm going to take 1 3. Actually, okay. 1 and 1 2 3. So this point, I know this is the transformed I hat, right? This is 1 3, right? And
Yeah.
2 4. So 2 and 4. Let me zoom in also, maybe. 2 4 would be here, right? Okay, maybe it's better to move to GeoGebra, but let me finish this point. I know this is where J hat goes. Can you tell me where 1 2 will go with just this information?
Can you zoom out? I want to see the matrix.
No, I won't let it. I don't want you to see the matrix. I want you to tell me, can you tell me where 1 2, if I input it as, so if this was XY, which is the input, where will this get transformed here with just this? Can you or can you not? If you think you cannot, you tell me. Okay, we cannot do it with just this.
Okay, it's J. J means.
Remember what 1 2 means? 1 2 means 1 times I hat in the input world. I'm not talking about output world. And 2 times J hat. I'm just reminding you this.
Yeah, only with the J hat we cannot. We need both I and J hat. So
yeah, okay. You have the transform version of I hat. You have the transform version of I hat and you have the transform version of J hat. Is this enough to tell you where 1 2 goes to?
1, 2. Yeah, it should be, but
I want confidence in the answer. Either it should be no way it can happen, or two, it can be yes, it can definitely happen. One of them, choose.
Okay. It needs ing for this thing. Then it can happen.
So you're saying yes, I know where 1, 2 will go with just these two information. Is it?
Yeah.
Can you all raise your hands if you agree with Ankit that you can represent where the transform version of 1, 2 will go with just this two information? Now someone has to tell me, someone from the people other than Ankit has to tell me why. I think the fastest to raise their hand, Janendra, I think you're very confident. Why don't you go ahead?
Yeah, so basically it is 1 times the first vector that we have, which is 1, 3.
1 times. So you're saying 1 times transform version of I hat
plus
okay
twice of the other vector that we have.
Right.
So basically the
Transform
triangular
version of
form that we have now, like keeping the tail on the mouth of the other one, like that. So like that we can
Exactly.
also add simply.
Like that, right?
Yeah, so the once we have this and the twice of that, so basically yeah, this kind of that thing we can do.
My bad. This will go to the right hand side. My bad.
But the only point that I was getting confused was when we were using this hat notation now, but that would represent a unit vector. But
now our unit vectors are changed, like that 1, 0 is changed to this 1 3. So instead of simply 1 0, now we have this the new transformed axis.
Yeah, so it was not no longer having a unit this.
Yeah. So these are new.
That's why I was getting confused earlier.
Yeah.
So do you agree that if I have the transform version of I hat here, okay, I don't need the matrix now. Okay, if I have if I know where the transform version of I hat goes, right, and where the transform version of J hat goes,
I can point the.
I can pinpoint any point, any input I give, I can pinpoint where it will transform to, right?
Yeah.
So this this made easy is a matrix. It is just representing the two main points that you just want to know. You want to keep. You just want to know, okay, where did I hat go? Where did J hat go? If I know that information, I can give any input X, Y, and I can find out where that went in the transformed world. That is what it means. Right?
Right.
So everyone understood that part, right?
In another words, you can see like this: if we want to give two inputs, then that M cross and the things that the matrix order should be of in a particular order if you want to multiply them. So because of that also we can say that we need two things in the earlier matrix if you want to multiply that.
Okay, now in this one, we scaled the I cap and J cap. Now, what if we have 2 cross 2 instead of 2 cross 1? Now that was the question, right? That what if we multiply two matrices? What happens then?
What I am saying, like if you want to multiply by M by N matrix, then the second matrix should be of order
N by something.
N J, yeah. That thing because of this how we are writing this phi as I hat and J hat, this thing also becomes clear, because if you want to give input that is that has two elements, then the phi should also have two elements, means I hat and J hat. I don't know if I was able to
Not
explain.
necessarily. It should have the same number of rows, right?
But that is I and J hat, na? because that is
Huh,
what
you can take that. You can take that.
Like for example, it's for 2 by 2 and 2 by 1. Like for example, if the A was this 2 by 2 matrix and B was 2 by 1 matrix, then that would have resulted is us in 2 by 1 matrix. And if
Right.
we wanted to give it input an X, Y, say another C,
That would be
that,
2 by 2
that,
plus
that yeah.
Anyone else maybe who wants to join the discussion? What does it mean to take the product of two matrices? Your idea or your $1 million insight, anything? Come on. Think about it. What does it
And
mean
there are
to take?
19 people here.
Yeah, there are a lot of people today. I'm very happy.
It's,
Maria, maybe?
It's simply transforming this phi I and phi j, na?
Sorry, can you repeat that?
It's just simply transforming our phi I and phi j. Phi I cap and phi j cap.
What is phi here?
Means after multiplication, we are still getting a function. And that function has some different I cap and some different j cap as compared to the what we were having before the product happened.
So we're still going to get two vectors, right? Ik cap and j cap,
Yeah.
but they will be scaled by some value.
Yeah.
Right. So
Yeah, but some sort of mapping here and there. For the point of scaling, we saw in the GeoGebra only at 2 points this scaling is occurring. That is in first and third quadrant and in the second and fourth quadrant.
Correct.
That's not always true also. It's okay, maybe.
Yeah, but rest of
for the
on
matrices
rest of the-
which have positive numbers, right?
Yeah, but for rest of the regions, it was not just scaling. For this 4 points, it was scaling, but not for the rest.
Okay, why? Okay.
So what are you coming at here?
Yeah. What are you trying to? I don't know why you want to connect that to this. I don't think.
We know that it is producing a function. It is having a phi I cap and phi j cap.
What is phi here? That's what I want to know.
Yeah,
See,
exactly.
what is the phi? Is the first matrix the phi? The second matrix the phi? What is phi?
No, I'm talking about the resultant one, no? What
Okay, okay. I called it M. Let's keep it M. Let's not call it phi then. I called it M. Okay.
Yeah.
This
so,
is A. This is A. This is B. This is M.
Yeah. So,
Ashik, are you there? Maria, Anurag, Raja, anyone? Janendra, you can also go. Yeah.
Yeah. So what is happening here is basically this first A matrix, which is that this is our main transformation matrix basically. So in that, what we are having is this particular A matrix is like the first, all the columns 1, 3, and 2, 4. These are our new I hat and J hat. Like initially we had I hat, J hat, simple ones, 1, 0, 0, 1. Now these are our new fundamental vectors, unit vectors of the transformed plane.
So he's saying 1001 became A.
Became 1001 became A.
Okay.
So our normal plane which was there earlier now is this transformed plane. And this function, this matrix, what it does is whenever we are trying to multiply this B matrix. So in B matrix, whichever vectors we are having, for example, we are having two vectors, column vectors here, 3, 4, and 7, 9. This 3, 4 is one vector. If we just see 3, 4, like simply 3, 4 in the simple IJ plane, it will be a point at 3 and 4, right? Now we want to see where this particular vector is in our new transformed plane. So that is why we do that multiplication thing. So if we multiply this B matrix, what we will get is we'll get these two vectors 3, 4 and 7, 9 in the transformed plane.
Awesome. You understood. I'm very happy.
Yeah.
That's awesome. Okay. Anyone who understood his explanation? Anyone who wants to,
Can you
if they've
repeat
understood?
once again?
No, I don't think. Okay. I mean, I have maybe I will explain it once. Maybe if you don't understand my explanation also, you can ask him to explain it. Is that okay?
Yeah, go ahead. Sure.
No, I'm not going to explain now yet. I want to see other people's point of view as well.
Sure.
Anyone else? Chetan, why don't you try? What do you think is happening here? Also, okay, Janendra. Okay, everyone. When you have two functions, right? What is happening? Okay. What function will you apply first? Where will the input come? Will the input come here, or in between, or will it come here?
Right side, basically, mostly. The right side.
Will it matter?
Yeah, if it does matter, because order of multiplication in order means A, B into C is different from A, Z into B in
Right.
matter.
Sorry.
It does matter. But what we are doing is we are taking input and transforming as output, and we are always write AX is equal to B.
So in the right side,
in
we
the
will
right
have
side.
the input, right?
Yeah.
So any input that will we will take, say we have an input called say V, that is 2 cross 1. So that will be on the right side, right? And that will so our what we were earlier discussing, that it A cross B say is M. So that is M cross V, right?
Okay. So you're saying since this is not possible, you're saying this, right? Okay, agreed. You want
But my doubt still remains. So what is the significance of matrix multiplication? We know when we are multiplying a matrix with a 2 cross 1 column vector, we know that it's getting scaled, right? But now here we are not multiplying it with a 2 cross 1 column vector. We are multiplying it with another matrix, another function.
The second one is not a function. We can see that as a packaging of multiple inputs. Maybe.
Yeah, you can say that as well. But it's another matrix, right? It's like when Ankit was saying that you're multiplying I cap j cap with another I cap j cap. He was basically saying the same thing, that he was considering it as a function.
He was considering. But I asked why can't B be a function? I mean, why can't you just consider?
Exactly. So
okay, if the input is here, what happens?
If input would have been here, then B can also first act as a function for transforming V, and their output can be transformed using A as a function.
A as a function.
Awesome. Understood. Very good. Very well said. Very crisp. Very light. So what does that mean? How do you do f of g of x? What do you do first?
So we okay. I get it now. So the output of say output of g of x is the input of f of g f of x, right? So you're getting some output after that. So here, when we are saying that A cross B cross some vector V, what we are saying is we are scaling the function B with that input V. We are getting some output, and with that output, we know that it's going to be a 2 cross 1 output, a vector. We are scaling A with that vector.
Okay, scaling is not the right term, obviously. You're applying the function. You're
So
applying B on
transformation,
vector.
right?
Yeah, you're applying the linear transformation.
Yeah.
Right. Linear transformation is not only scaling, it is sharing and rotation and scaling, right? So
So
we can't.
scaling of the I cap and J cap of A matrix. That's what I was saying.
Scaling and combination, right? So that's a linear combination. It's
linear
a scale
combination.
plus, I mean, scale plus scale. So it's like a linear combination. Okay. So just like how you read functions, you will first apply function B on the input vector, and then that will give you an output vector. Let's call it V hat, okay, V cap, right? And you will just input that to A, right? Right. So in just like how you do, you apply function G first, and I mean function G first, and then you apply function F. You always apply matrix. You always apply matrices as functions from right to left, right?
Understood.
So we understood that. Okay. Right. So multiplying two matrices is nothing but saying first apply function B, then apply function A.
So we are not actually multiplying two functions. We are first taking the linear combination of one function with the input, and then with the another function. Now it makes sense. Yeah.
Okay, but what if
it remains same, right?
Yes.
A, B, that also remains same.
Exactly. Think about this. What if I remove here? Now what does it mean? You said, now I had an input, I applied function B on the input, and I inputted that as the next, I inputted that output into function A.
Yeah, we can see still that A is transforming B and forming something new. Because now
A
we can
transforming
consider-
B or B transforming A?
No, see, how we write A, B, V in a similar analogy, what B essentially itself is having two vectors.
Two vectors?
So,
okay.
yeah,
So B,
yeah,
okay,
two column
B.
vector. Here, it is still having two column vectors. And if we were treating this M will also be having two column vector. What essentially we were doing with the V, that is BV. The similar thing is happening with the column vectors of B if we were treated as V.
Awesome. Okay, Ankit, you also understood. You can also listen after this. Anyone else? Do they want to explain what is happening? Ishan is very quiet. Is he?
He's asleep. He's asleep.
Oh, I'm so sorry.
Ankit, can you repeat what you said?
What I said was like the thing that we were doing with BV. We were essentially taking V as an input and B was transforming it and producing some output.
Correct.
If we treat B is having certain number of column vectors. So what A is doing, A is taking one column vector of B at a time and transforming it to produce something.
Okay.
And this processing being done with all the column vectors of B.
One by one.
Yeah, one by one.
Okay.
And that results in production of M.
My bad. Okay. I like that explanation, but let's think of it step by step in the sense that function B is being applied first. How do I say function B is being applied first? how do I somehow encapsulate function B is applied first, and function A is being applied on function B, right? And that in itself is creating a function which is equal to doing B first and then doing A first, right? M is a function that is telling me if I applied B first and then I applied A next. That is what M is. Right? So I hope he doesn't start sleepwalking or something. I'll get shit scared.
He's moving.
Oh, he's awake.
Yeah, I guess.
Okay.
FOG equivalent, isn't it? No, I just took a quick nap.
It would have been better if you removed your headphones and took a nap. Why would you want to hear my voice and sleep? Oh my god.
No. Very meaningful discussion was going on.
What if I think of it like this? Or let's
Three matrices. Okay. So now we are scaling or taking the linear combination of B with each column of I, then of A with that matrix that we're getting.
You're going in the right direction. Yes. See, I can represent this matrix. I can represent this function as a multiplication of these two. Agreed?
Correct.
A cross I is equal to A, right? Why? Because my starting point was 1, 0, and I am transforming to 1, 3.
Right.
My starting point is 0, 1. I
Right.
am transforming to 2, 4.
Correct.
Right? True?
Correct.
Now, the same thing I can do for this. So you agree that I can write it like this, right? First?
Yeah, right.
Perfect. So what I can think of, right? First, my I hat is being transformed to 3, 4. My
And
J hat is being transformed to 7, 9.
And same is happening with A.
Then my I hat, or let me call it B of I hat,
Is
right? Is
transformed
this,
into
and this is B of J hat. This is being transformed with this.
right.
Note, from here to here, it was very simple. It is just 3, 4.
Right.
But from here to here, there is something involved, which is nothing but all you've been doing all this while. Think of this as your first input vector, think of this as your second input vector, and do your multiplication.
So
It's
scaling.
just like Ankit said.
But here, if you will look at the B, how A is transforming B, then A does not just involve its first vector. It's both I and I cap and J cap both are responsible for transforming the.
Oh, that was the same
Yeah.
in I as well. So when we were taking, we are not doing something special here. We are just repeating what we did with B and I.
No,
So
no, but I is a special thing now because I saying take.
forget about that special thing. Forget about one
It
and
is
two.
just,
You
here
are
it's just
doing.
a 0. It's okay. I mean, you were doing
How
the
does that
multiplication.
matter if it's zero? You are essentially doing the same thing. What you are doing is you're taking the matrix 3, 3, 7, 4, 9, and you're taking a column vector from I. You're scaling that I cap and J cap of B with that column vector. Then you're taking the next column vector 0, I, scaling that matrix B with that. And again, you're doing the same thing with A. You're taking a column vector from this transformed B matrix and scaling A with that, and then the next column transformed column vector from B and scaling A with that. So you
Okay,
essentially you are doing the same thing. You're
Yeah,
not.
Chetan has understood.
we are essentially doing the same thing now.
Yeah.
But the way we can you scroll up a bit?
Sure, sorry.
The same thing.
The only
Like,
special
look,
thing about
look,
one.
when we are multiplying, this is a valid statement.
Mhm.
We have tested it. When we are multiplying a vector, means a matrix to a vector, whatever that vector is, then the result is some sort of linear combination of that vector.
Correct.
First thing. Now, when we are multiplying B with I, what essentially the I cap is saying, just take the complete first column of B and take none of Bj. Means take complete of Bi, but take none of Bj. Now, but when you are on Bi, what essentially you are saying is take thrice of Ai cap and take 4 times of Aj cap. And
Yes.
what
Yes.
this transform version is the linear combination of this thing. That
Yeah,
I was
see, here also it was a linear combination.
Right.
See, just because there's a 0 here doesn't make it special. The 0 was being multiplied. So the scaling factor here was a 4, but the scaling factor here was a 4. Sorry, 0. That's all.
That's it.
Yeah,
Obviously,
but
that output is going to be different.
that's
Output,
why when producing the output for when transforming B, both the vectors of A are responsible.
yes, that is
Yeah.
true. That is true.
And
Right.
that
You are
only-
right. Obviously, it depends on 1, 3 and 2, 4 when you're thinking about where 3, 4 will land. You're right. But that is true for 1, 0 also. Just that the 0 is telling you scale this to 0. That's all.
Yeah, I fail to understand why I is special. I is not special. I is just another matrix.
Okay, well, means from perspective you are seeing from the function point of view, not the input point of view.
Yeah, the function is doing the same thing. I mean, function will
Yeah.
always do the same thing.
If we are looking from that point of view, then I completely agree with you.
Yeah, exactly.
Because
But yeah, obviously,
I was
yeah.
looking from the input side, and
Understood.
both point of view are different.
Yeah, understood. So this writing I here is redundant, right? Because
Right.
we know this is the starting point, because this was the starting point. We
Correct.
know anything multiplied with I is just B itself. So this is not even required over here.
Yeah,
Okay, so I'm
but
removing-
it helped us understand what actually is
Exactly.
helping, right?
Exactly.
So
It
in
helped
that
us
regard, it was
understand.
very important. It wasn't
True.
redundant in that regard.
Now can you tell me the right hand side? What is the right hand side?
So yeah, so it will be 3 plus 11. Okay.
No. I wanted to do it in the sense of how are you going to do it now? Like,
Right.
how are
Right.
you going to apply this function?
So it will be just a second. So it will
Let's
be
break it step by step.
7 into.
No, let's break it step by step. First, I'm going to apply A on the vector 3, 4. Do you agree?
Right. So it will be so you are scaling 1, 3 with 3 and 2, 4 with 4. Then you're scaling that with 7. Okay. Can you write?
Maybe wait, I don't have enough space.
Just zoom out. Just zoom out.
Is it? Yeah.
Yeah.
Sorry. Yeah.
So
okay. Sorry. What were you saying?
So I was saying write a matrix.
Another matrix. Okay.
Yeah. Not another matrix. Just equals. So equals another matrix. So 3 multiplied with column vector 1, 3.
You don't need that. Plus
4 multiplied with column vector 2, 4. Right.
This is right.
Once you have this, now our next matrix is this 7 comma sorry, our next vector is 7 comma 9, right?
Yeah, so
that would
first
be
let me finish this side. This side, it's incomplete, right? This equation is incomplete right now. So what I want to say is, I will apply the function, right, on this side, and this input I will put in the first column, right? Let's say, how do I write this? Okay, I get this thing and I get this thing. 1, 2, 3, 4. And I will do that with what? What will I do this? Okay, I've done this with 3, 4. What will I do it with?
7, 9, 7, 9, right?
7, 9. And whatever output I get, that will be my
second column vector.
This will be my first column vector. This will be my second column vector. Now you can break it as you said. I'll break this entire thing into how you said. Right? You said 3 times 1, 3, which is nothing but the column view,
plus
4 times
2, 4.
2, 4. And this also I can do in the same way.
Correct.
Can someone help me?
7
So 7 times 1 comma 3 and
9 times
9 times
2 comma 4.
Correct.
And let's finish with the output.
So
What is the output?
Yeah, so it will be
3, 9 plus
3 plus
11.
4 into 2, 8.
and
Right?
9 plus
3
plus 9
3 plus 4 times 2. That's what I did over there.
So
For
that is
anyone.
11 comma
Okay.
11 comma 9 plus 16. So that's 25.
Yeah, I'll do it step by step. So 3 plus 4 times 2, which is 8. 3
9.
times 3, 9 plus 4 times 4, 16. And
Then
on
we
the
will-
right hand side, I'll get
Yeah, so we'll have
7 plus
7 plus
18.
and 21 plus
21 plus
36.
This is your matrix multiplication.
Correct. So 11 25 and
25.
yeah 25 and
57.
7
57.
557. Right. Perfect.
Now this is M.
Correct.
Right? So if I apply B, right, always read right to left, right? If I apply B and then apply A to a vector, that is the same as applying M to the vector.
Correct.
Is what this is saying. If you want to check that out, we can check that out with GeoGebra for a second if you guys are okay.
That's fine.
Yeah, that will always be true. You guys understand. Oh wait, what did you say that was? Control Alt Shift. Control Alt Shift what?
Control Shift Alt Control Alt Shift H.
H. Okay, thanks.
H for
hide. Okay.
Hide.
My bad.
Okay.
Yeah, where am I? Okay, yeah. So this is what matrix multiplication means. So let's go back to our question. What was our question? Oh, our question is here. My bad.
Still after going through all the things, we are still back at that thing now. I mean, when I was saying that A times vector V1 will give first column vector of M and
Yes.
A column
But did you
vector
understand it in the sense that you're first applying function M and then applying function A? Yeah.
The idea of f of g of x in the matrix was not earlier clear that way, but I applied something similar to that.
True. What you applied is right. right? Because I mean, I know the right hand side. I can deduce what happens on the left. See, it's like saying 36 is the output, right? It's like saying,
Just hear me out. What I was saying, I did the same things. Like I merged this to 8, multiplied itself with 1,000 times on yesterday questions, and I checked this both the things doing individual others using Python, and I just means I just made a single matrix after multiplying 8,000 times, and that was producing the same result when I was having this A times A times A and ultimately the vector B in the yesterday's question, and the same distributions were occurring. That I'm saying.
Okay, I'm very confused. Why are we talking about that?
But that's same now. Like, yeah, we are treating A, B equals M. So
okay, but
yeah, means you are like in a sense what you are doing is we are giving f of g of x, and you are writing an equivalent function to f that produces the same that transforms in the same manner as f of g of x would have done. You are writing that as equivalence now, means ab is equal to m.
Yeah. Okay. AM is equal to AM is equal to alpha.
Yeah. If we would have been applied f of g of h of I of x anything, that we can always calculate an equivalent function, a matrix function that would give the same result if we would have done this things.
Yeah, but you saw that with the same matrix again and again, right? You did A into A into A into A into A into A.
I did for the same matrix.
You didn't do A times B times C, right? Yeah. Okay. So yeah, at least we all know now that if I take two, I mean, product of two matrices, it's just saying do the the one on the right hand side first. Do the first. Apply the first function which is on the right hand side, which is B or here M, and then apply A, right?
Right.
And you realize that doing that is also a matrix, which is saying there is an equivalent single matrix of only 4 values instead of 8 values. There's a single matrix of 4 values, which can tell what it means to do both of them together, one after the other, right?
In a nutshell, M stands for FOG of V.
Exactly. Awesome. So, okay, we've understood.
Here I just have one thing, like in this scaling thing, we saw that it is having scaling at certain angle in I of first coordinate, certain angle in this rest of the coordinates in this 4 points. If A would have been different, will the scaling point or the scaling thing would
Yes.
Of course.
Yeah. So what essentially we are saying is we are just saying that at certain point but means a short view also there, no? It is just occurring at 4 instances on all the complete Cartesian coordinate system.
Collect your thoughts. Collect your thoughts. Take it slow. It's okay. Think about what you want to say and then say it's okay.
Like in the Cartesian coordinate system, what scaling is occurring only at 4 places in means 2 places only, essentially. But on the rest of the places in the Cartesian coordinate system, this pure scaling is not occurring.
Okay.
Having V.
That is what it means. That is what it means that it's only occurring. If it's only occurring at those 2 places, then yeah, other places it's not occurring. It's right.
Yeah.
You're just stating the fact, right? It's okay. So see, let's go step by step again. Okay. We want to look at a matrix, any matrix. We're not thinking about a symmetric or non-symmetric. We're looking at a general matrix. And when we took a general matrix, right, unless they had dependent columns, we said we were able to find two vectors or two specific directions, or like two specific vectors that are on some line where the output is just a scaled version of that vector. So that is V1 and V2. There are two specific vectors, V1. V1 is being scaled by alpha 1 and V2 is being scaled by alpha 2. Alpha 1 is different than alpha 2. V1 is different from V2. We all agree on that, right?
Yeah.
Awesome. This is the matrix notation of that. Matrix A, when the input is V1 vector, gives us alpha 1 times V1. This is the matrix representation. This is the matrix representation for the second equation. Now we are able to represent that, since we know that if we take the V1 and V2 as a matrix, right? It is telling first I am going to input V1 to function A and V2 to function A, and I'm going to get obviously the outputs the same as this, right? Which Ankit has been saying for so long, which is alpha 1 V1 and alpha 2 V2. Perfect. We got that right. I just want to know if everyone understood this, right?
I got
If
it.
you've not, if you've not understood this, then we have to revisit a few things.
Okay, this is so beautiful, you know.
Agreed.
This is really beautiful thing.
Yeah.
Because we have found M and we are going to apply M to A again.
Vishal, any Ghalib's couplet today?
I'll have to think out. You have woken me up. Now I get it. When sir said it has got everything to do with that repeated multiplication. Okay. Let me find a Ghalib couplets as well. Eventually, I'll find out.
Can we go to the next step?
Yeah. Please.
Even this particular expansion. Okay, what is happening here? We are representing V1, V2, the matrix V1, V2 as M. So we can write the left-hand side as AM. So the left-hand side is sorted. And the right-hand side,
It only says the scale just vector V1 and scale just vector V2, and you are returned with that previous step.
exactly. Remember when 1001 was here, what happens? It is just equal to V1, V2. But we want to represent this matrix, this function, as a product of two matrices such that the first vector is only scaled by alpha 1 and alpha 1, and second vector is only scaled by alpha 2. Right? So you can now say, if I input alpha 1 0 to V1, that is nothing but saying take alpha 1 times V1. That is nothing but the first column that we're representing, and alpha 2 0 times V1. So we don't want any part of V1, but we want alpha 2 times the V2. We can understand this through, again, column representation. Right?
But alpha 1 and alpha 2 must be known, na?
Well, they are scaling factor. We can just
we don't know any of this, right? We don't know what is V1, V2. We're just generalizing it. I'm saying any given any matrix, there exists. Okay, there might not be, they're not for all matrices, but most matrices, there exists some V1, which is alpha 1 V1 in the transform space, and some V2, which is alpha 2 V2 in the transform space. So we are
For what?
continuing with the generalization. Yeah.
For what you said these two conditions?
Given a matrix, which is symmetric or non-symmetric.
Okay.
Right? We were able to see
Given
that
a function.
Given a function, we were able to see that. Given a function from R2 to R2, we were able to see that a vector, or actually
There will be there is a scaled version of the vector in vector itself.
Exactly.
Given a function, there will always be.
Yeah.
Not always. There will be a scaled version of itself.
Exactly. And we will have two such vectors in the R2 space, right? If our function is 2 cross 2, which is nothing but saying in the R2 dimension, R2, R2 to R2, then there'll be two such vectors, right? That's what we saw through the GeoGebra annotation, right? Now we've come to this part, right? We've come to AM is equal to, and this is nothing but M, right? V1, V2 is M. So let's put it down to M. And we're representing the right hand side matrix alpha 1, alpha 2, which is alpha 1, 0, 0, alpha 2 as alpha itself, right? So AM is equal to M alpha. Now we want to know what we want to represent A. So we're taking.
Just can we go one step back for a
Sure,
second?
sure,
Not for tomorrow. Let me soak it.
Sure.
E times M. Okay. Is equal to V1, V2, fine, which is M times alpha. Now AM is equal to M alpha. Fine. Okay. Let us move ahead.
Okay. You want to move forward?
Mm-hmm. Yeah.
Okay. So now we're able to represent AM as M alpha. There's not much here, right? We're just representing this M as M, and we're representing this particular matrix as alpha. Okay. Now, how did I move from here to here?
Simply took inverse of M.
You took inverse of M on both sides, right? AM M inverse is equal to M alpha M inverse. M inverse becomes identity, and AI is nothing but A.
Fine.
So A is equal to M alpha M inverse. That is okay.
Fine.
Now, okay, what is A square?
A square is simply M alpha M inverse times M alpha M inverse.
Exactly. Let's write that down. Awesome. We are in a very, very nice point. So we know we can write let me write one step before also. AM is equal to M alpha, taking M inverse on both sides.
A is equal to M alpha A alpha M inverse.
M inverse.
Fine.
Okay.
Fine.
Now what is A square? What is A times A?
M alpha M inverse
into M
alpha M inverse
into
M alpha
M
M
inverse.
inverse.
Fine.
M inverse M
is identity.
Identity. Alpha into alpha is
alpha square.
Alpha squared.
So we get
M alpha is alpha square.
Alpha square.
M inverse.
M inverse.
Correct. So we generalize this as M into alpha raised to
A raised to power n is equal to M
alpha raised to power n into M inverse.
M inverse.
K power K
M inverse.
M inverse. I'm using K because sir used K in this, right? Just to keep it equal.
Yeah.
And this is the matrix form of it, right?
Correct.
Yeah.
Now I'll ask you all a question. Why is it guaranteed that M will have an inverse? I mean, okay. I took M inverse.
Square matrix, right?
Yeah, okay. Square matrix, okay. I took M inverse on both sides.
Correct.
But nobody told me that M has an inverse to begin with. How did I take M inverse on themselves?
Because it's a
How
function.
do I know? Do I know M is invertible or not? Have I proved that M is invertible? This is very important. How do I take M inverse randomly? What if M inverse doesn't exist? This will fail, right? This entire thing will fall apart, right? Agreed?
Right.
Are we going towards dependency?
I think it can only like the whole
Yes, Maria.
You go ahead first.
Yes, Maria, go ahead. Go ahead.
yeah okay, I don't know if this is correct, like unless the rows of A are independent, you can't actually get to the first equation, right? That's what I think. Because no, AM equal to M alpha.
This one is it. AM is equal to M alpha, which we've written here. Okay. They're saying we cannot reach this. Why? When? Sorry, what?
Okay, that's not a condition on A. That's condition on A, not M. Okay, that was wrong. Okay.
What I was saying is, like, you have already initially we have already defined two instances that are different from each another. That is AV1 is equal to alpha 1 V1 and AV2 is equal to alpha 2 V2. That ensures that V1 and V2 are independent of each another. That we see like in GeoGebra.
And there's no dependency.
Yeah, because there is no dependency, that ensures their inverse exists.
Ankit is basically saying that we have assumed that.
Okay, let's take it as an assumption right now.
Let's say
Okay.
V1 and V2 are not collinear or in the same direction, right?
What if, okay, we saw, yeah, we didn't generalize it yet because there were some places where one V1, V2 didn't exist. We gave a few examples. I'm just telling it out now because this is not true for all matrices, right? Because there were some matrices where V1 and V2 were not even defined. Was it not defined? I mean, at least in the sense we understood it, right? When we took 1, 2, 2, 4, 1, 2, 1 minus 2, 3, 4, is it? Some rotation, okay, any rotation matrix, this thing you take, right? It will never coincide. Am I not making sense? Wait.
No, but you are making sense. Just a rotation matrix just tilted the input to a certain degrees. Like for this dimension, you can just write like cos theta, sin theta, and that matrix. No? 0 unit vectors in theta form.
Yeah.
If
Okay.
you multiply it with that, you will never coincide with that input. Never.
Exactly. Right. This is an example of a matrix. It will never coincide, right? Because this is a rotation, right? Something else also is there. Yeah, something else is. Here it coincides once. And this is the same coinciding. Obviously, there's only one line to coincide at. So
in this case, M inverse will not exist.
Okay, understood. Awesome. You guys have. Okay, so let's go ahead with the assumption that V1 and V2 are different. Okay, does alpha 1 and alpha 2 have to be different? I understand V1 and V2 are different. Alpha 1, alpha 2, are they different or not? Let's leave that. What do we need right now? We just need this matrix to be invertible, right? We just need M inverse to exist, right? For M inverse to exist, what is the condition?
The column vectors should be independent.
Perfect. Awesome. That's it. And that is proved here, right? If V1 and V2 are different, they are not on the same line. So it's okay. Awesome.
independent. Muffled.
Yeah, a little muffled.
Sorry.
Yeah, okay, let's say that if V1 cannot be expressed as alpha times V2, then we are
Okay.
assuming that, yeah, we are assuming that V1 is not equal to alpha times V2.
Go ahead, Maria.
Yeah, if A is the identity matrix, then we won't get unique alphas.
Good
And
observation. So our assumption, let's state our assumption. Assumption is V1 cannot be expressed as a scaled version of V2 or vice versa, right? Alpha can be 1 by something also. So this will say that these two vectors are independent. This is basically saying V1 and V2 are independent, right? Awesome. Okay. And why are we making this? Why did we need to make this assumption?
So that they aren't dependent, and we can have an inverse, right?
Exact reason for our equations to work, M inverse has to exist. Right? This is the reason bubble. This is the assumption bubble. This is the assumption bubble. Okay. Now let's go back. So now we know M inverse exists, so we don't have to question anything. So we can write A is equal to M alpha M inverse, and we understood that we can find A power K very, very easily. We just have to find alpha 1, alpha 2, and now we just have to scale. I mean, you have to find V1, V2, alpha 1, alpha 2. We don't know how to do that yet. I mean, GeoGebra can help us, but maybe we don't know a structured way of doing that yet. So A power K is very easy if we know A is equal to M alpha M inverse.
Right.
Now, A inverse is also easy. Why? Let's do it by ourselves. Let's go step by step. Right? This is
so
A power K is easy. Now we want to do A inverse is easy. Sorry guys, I'll get a Wacom tablet soon so that I'm able to. I'm not able to use this mouse for too long. And then I can easily write on this much better. A inverse is easy. And now we want to prove that. Let's start our proof. Yes. What is A equal to?
M into alpha into M inverse.
M alpha M inverse. What is A inverse equal to?
So that would be
M inverse, the whole inverse.
You want to take it step by step, maybe? M alpha M inverse, the whole inverse. And then how does inverse apply on?
I don't know, with alphas also.
So it's again M inverse alpha inverse M. So that's M into alpha inverse M inverse.
So you're saying M inverse
alpha inverse M
inverse M.
We can rewrite it as M into alpha inverse into M inverse. Right?
No, it will
It's
be like
actually M inverse, whole inverse comes first, right? So I think it's M alpha inverse, M inverse.
No, the order changes when we do these things, inverses.
Exactly. So
Yeah.
So first we take the inverse of this, which is M inverse of inverse, which is M. Or you want me to write it step by step? I can do that. M inverse, the whole inverse. Okay, then you do alpha inverse.
Just one clarification. We whatever we are discussing, it has nothing to do with eigenvalues, right? It's a different discussion altogether. That was a separate discussion.
Yeah, guide just
What is
adjust it.
alpha? Okay, maybe I can't. Okay, I don't. Yeah, sorry. Let me not. Okay, there is a relation.
Okay, there is a relation. Okay.
Because we use the fact that A is equal to M alpha M inverse. There somewhere we use the fact that there were two particular vectors. What is M? There are two particular vectors. And what is the property? What is the unique property of that vector?
They're independent of each other, right?
That is our assumption. What is the main property of the vector?
Which vector?
that it is going to get scaled up.
Yeah.
Exactly.
Right.
When inputted to matrix A, right, it is only going to get scaled.
Right.
It's going to be alpha times some alpha 1 times itself.
The vector.
That property we're still maintaining here.
Right.
And that property has something to do with eigenvectors and eigenvalues. Actually, the vectors that it's, I mean, you can easily find out now, right? Whatever is inside M are two vectors, and those are called our eigenvectors. Whatever is in alpha are our eigenvalues.
Got it.
Okay, that is what Sir also has said here. I will come back to that as soon as we finish this. We don't want to jump anything. So M inverse, whole inverse, alpha inverse, and M inverse. Right? And this is nothing but
he said for every vector there, for every matrix or vector exists a unique, not unique, an eigenvalue and an eigenvector.
Eigenvalue, yeah, I also wanted to ask this. Eigenvalue is actually associated with the
Coincidence.
system of equations, right? Like when you write, or is it associated, like you can only associate with both the metrics and the thing, right? What thing here?
Have
Sorry.
you guys already discussed this eigenvalue stuff?
No. See.
No, we haven't discussed any of it. Maybe we'll take it step by step. Let's finish this. After, I mean, this is only 2-3
Yeah,
more
sure,
steps done,
sure.
and then we'll be done
Okay,
with
sure.
today's entire whatever has been discussed today. We would have finished it, right?
Okay, so M alpha inverse, M inverse.
Inverse, and this is nothing but
A.
This is
Sorry,
A
not A,
inverse.
not A.
One second. Why would you change places of M inverse and M?
Oh, wait, there is a property. So it's not just A raised. Okay, we got A raised to K as M alpha raised to K M inverse. We also got M inverse as M alpha inverse M inverse.
Okay,
So
let
you
me
can even
answer
treat
the
my
first. Let me answer the first question. Why is AB inverse equal to A inverse B? Sorry, B inverse A inverse. Right?
inverse A inverse.
My bad. Why is it B inverse A inverse?
Because you have to multiply on the right side with B inverse, like just
No.
you can
I
form
know the mathematical. I know why it's happening. Okay. Does anyone want the mathematical reasoning, or do they want the
logical will be
logical
better.
reasoning? Does everyone know the mathematical?
Because
Simple,
you have
simple.
to multiply
Yeah.
the right side and then the
Multiply
it
something on
has
the
to
right
come
side.
out to be I,
Yeah.
right?
Exactly.
I
Multiply
think
something on the.
we haven't still also discussed this significance of this inverses and what does it do in the matrix.
What does an inverse of a What does an inverse of a function do actually? What does an inverse of a function mean?
It means just if it was take input to output, then inverse will take us from output to input.
That's
The
all.
same thing should happen to the matrix also.
That's all. Yeah.
Okay, I just wanted
But
to ask this since he mentioned that. Say you're associating A to a function, like that's where we started our discussion with. So
Exactly.
if that function is say F, then can we associate the matrix A inverse to F inverse?
It is
Because it's
exactly F inverse.
okay.
We are not trying to do anything new by taking matrix inverse. We are just trying to say, right? Given this output, what was the input? That's all.
More of a, like an undo
intuitively,
operation.
I don't know why this order is different now when we are taking the own complete inverse.
Sorry, let me write that. Let me think of that again. What are you trying to say? You don't understand what it means to take an inverse.
Intuitively, I don't know why the order is order changes.
I haven't explained it. That's why.
Okay.
What about transposes? The same thing happens with transposes, right?
Transposes is a little complicated. Let's do this first. Let's finish our inverse topic and we'll jump to transposes later. And transpose is very okay. Transpose is better, fun. Okay, so AB the whole inverse. Maybe the whole inverse is only B inverse A inverse, right? Not A B inverse is equal. Sorry, I was wrong all this while. AB the whole inverse is B inverse A inverse. Okay. Let me try to understand this.
Yeah, I just got it now.
Awesome. I'm very happy that you took your time, looked at the question, and tried to understand what it means by yourself. If you all can do that for 1-2 minutes, even I'll take a break. Okay, I'll just be back in 2 minutes. If you guys want to discuss something also, please go ahead.
No. It's just like when we are doing A, B, X, just consider X to be input. What BX was doing was taking X and making something. Then A was taking something and making something. If we wanted to reverse, the first reverse, we would have to unwind what A did first on that X. Then what B did on that. So the order.
Isn't that the mathematical way rather than the intuitive way? Like if you just think, yeah, the way what you said, like it can be from what I understood, it's the same as saying X into something like AB is going to give you I. So to reverse that, you need to multiply B inverse A inverse.
But I didn't.
Isn't that
I didn't consider this function. Means visually I get like it's input, it's been transformed, then it is again being transformed. If we want to this means reverse this step, then we will have to go in that reverse order in which the transformation took place.
Yep, what Ankit is trying to say is that AB inverse means we want to know the input of AB. Fine. To know the input, we must go in the reverse direction. That is, we must first know the input of B so that we can apply that on A.
okay?
That is what we learned by matrix multiplication, isn't it?
Mm-mm.
The second matrix is the food for the first matrix, isn't it?
Yeah.
So that's why we are supposed to find inverse of AB, that is input of AB. So first what we do, we find out B, input of B, and then find out input of A, something like that, Ankit.
Yeah, but it's easy to, I don't know, but graph, I'm a graph type of guy. So visually I catch things, but I don't know how to express many times. Visually, I just take that I am stepping here and a function means I just transform to the function am something else. Then again a transformation took place. If I wanted to revert to my original state, then in which order should I process? So that thing would just came that the order should be reversed.
To multiply AB, we must know B. And A becomes the primary function, fine. That is what we mean by FOG.
Here, one thing that we didn't discuss, but it's essential to know. When we are discussing, when we are considering a matrix in a multiplication as a primary function, like you're saying A, we can always treat B as also primary function. The thing is this order means how they operate based on whether a matrix is multiplied on the right or it is multiplied on the left. Both perspectives are different. For a matrix, if we are multiplying a vector ahead of it, like V is a vector and A is a matrix, if we are multiplying VA, then what V essentially is doing, V is taking the combination of rows of A. But if we are doing AV, then what A is doing is we are taking linear combination of columns. So
Yeah. When you're
here
right
exists all these
multiplying,
perspectives.
what you're trying to say is when you're right multiplying, it is the okay, knew this, but can you repeat that once?
When we are multiplying right, you can directly understand it as a linear
Row
combination.
transformation, right?
No. When we are saying like AV, okay, as a vector, because a matrix is nothing but just a combination of vectors. You can always break it down. Say A is the vector and A is your matrix and V is a vector. If you are writing AV, what essentially here is occurring is you can easily say it as linear combination of vectors of A. But
Yeah, linear combination of
column vectors of A.
Yeah, column vectors of A. And when you're right multiplying it in the right, it's the rows, right?
Yeah, then it is a rows. These two perspectives are there. I just studied yesterday from a book, and I also was not aware that this thing was there. So considering
Yes, I heard of this, yeah.
Yeah,
Can we just go through the steps of what he solved and how we came to it again, if it's not too much trouble? Okay, but he only has access to the board. Okay, we can't do that.
I'm back.
Yeah.
Sorry, do you guys
Can we
want
go
to
through those
revisit
steps
something?
again if it's not too much trouble?
Which steps? This steps?
Like from you got from where you got we made like we started with trying to understand matrix multiplication as
Identity matrix.
Yeah. This step?
No, identity matrix. She's saying that we started with assuming A into I is equal to A. That stands deleted, I guess. Because that was only meant for understanding.
What do you guys want to discuss? Sorry.
I think yeah, sorry.
So it is you just want to discuss A times I, is it?
A times B, and B you
Just a short
B into
summary of
I.
what
ABI.
No. Make me understand the question. What is the doubt?
No, it was not.
She wants to
Uh,
go through it back again, the ABI thing. How this matrix multiplication is basically working. Which one is the food for which one?
Okay. So I have 1, 2, 3, 4. A. And I have B, 7. Okay. Now you want to do what?
Multiply it with I.
You want me to multiply this with I, is it?
Yep.
Okay.
Okay, why are we doing that?
Okay, what do you want to do then?
This is how multiplication was working, no?
How does multiplication work?
That was just
Column
to
wise,
understand what it was.
do you want to understand that thing that what I said? That column and row multiplication means considering.
No, that's something I sort of I have some idea about.
Okay.
Not
Can you
that.
explain that? Can you explain that once? Ankit, can you explain that once?
Okay, yeah, sure.
Yeah,
Just
if you
let's
yeah,
go
okay,
through an
Ankit, you can go
example then.
ahead.
Let's go with an example then. A the same. Can you erase B, please?
You want to erase B?
Yeah, complete B.
Okay.
Now write a different column vector only, V, named V. Say it simple like 1, 2 only. It will be easy on mind. Now, what one picture, what I can write it as is 1 times 1, 3.
Sorry.
Yeah,
Column view.
Just write it as
Yeah, I
linear
think this is
combination of
something everyone
column.
knows. When you write it, when you write it as AV equal to, and you try to decompose, it's column wise.
Yeah.
And when you write it as VA, it's row wise.
Yeah. And
What? Wait. What? VA is
now,
row-wise?
I
What
don't
is
know.
VA row-wise?
you will get it. Just write it.
No. See, if you are going to no, they are saying that if you are going to multiply a 2 by 2 matrix with 2 by 1 matrix, you will eventually get
Now on the right side,
2
write
by 1
times
matrix,
A.
and vice versa.
Don't make it equal to, just independently write V times A. Vector V times A.
You want me to write 1, 2 times this, which is not possible?
Why is it not possible? It's
Not possible at all. 2 times 1
no.
multiplied with a
Sorry,
1
it should
cross.
be V
That should be
transpose. Yeah,
transpose.
it should be V.
So
Yeah,
rows and columns should be equal. No?
Yeah, 1 to transpose. Sorry, yeah. V transpose.
V transpose.
Okay, again, that means the same thing.
Yeah.
Yeah,
Okay.
they are essentially same things. But now what you can write it as a linear combination of rows. 1, 3, 2, 4. Now just write it like 1 times row of
1, 2.
Yeah.
Then 2 times 3, 4.
Yeah, that will give you first row, and similarly that.
Wait, how do you want to write this? Sorry.
That is first, it is 1 by 2 matrix, and that is 2 by 2 matrix. So result will be 2 by 2 matrix, no? No.
1 by 2 matrix.
1 by 2, 1 by 2 by 2, 1 by 2 will be there. So what essentially it is saying is take 1 times of row 1, that is 1 times 1, 2.
Okay.
And add 2 times row 2, that is 3, 4.
Yeah, that's all this was. This is a sort of the same thing, but yeah.
Yeah. So essentially, what now we were having V as a short only 1 by 2 matrix. That is having only two elements. If it would have been a matrix, then also this approach works.
Shivan, can you scroll up once? Just a second.
1 second. Yeah, sorry. I was just.
just multiply and check.
So
You
this
will.
is six.
I want to ask a very basic
Seven.
question. I was asking it yesterday, a couple of days back also. What does transforming a matrix brings to our table?
Yeah. We'll discuss that. We'll discuss
So
that.
this gives me a row. So this
Like, I wanted to ask, like
this
we
gives me a just a second. This give me a column vector that is 7 comma
No,
10,
this will
right?
give you a row vector.
7
right?
comma 10. Yeah, row vector 7 comma 10, right?
Yeah.
Yep.
Isn't that the case?
Yeah.
And what will this give me?
And this would give us 5 comma 11, right?
Yeah.
So how is the multiplication same?
Not
No,
seven.
it's just
No.
that the way it's transformed is different. That's the only thing I meant. I mean,
We never
but
said
it's
that
just
A
a way.
B
It's
is
a way
equal
to
to
look
B.
at it. That's all.
We are saying just
I
the point, the what we are multiplying it, what we are considering as transformation function. We can see that if it is we are multiplying it as a right or we are multiplying in a left, then way of understanding both the perspective is a bit different. That you can see here.
okay. So you were explaining that, but okay.
Yeah, only
Sure.
only this point.
Okay,
Nothing.
yeah. Then it works, right.
Now I got my answer for transpose, at least one part of it.
Yeah.
What I have oftenly seen that okay, it is not able. We are not able to multiply two matrices. Take a transpose, now multiply. Both of them are going to give two different results. I know this at least. Thank you,
Right.
Chetan.
Guys, you are saying about transpose, right?
No,
That
no,
was a
no,
different thing.
that is an off-topic thing.
This is like saying the row space is this. Okay, maybe not go there. Not yet.
No, I
let's
don't
not
have
digress.
any idea about row space.
Let us not go there. Let us
He
not
is
go.
not gone there yet.
But
Vishal and
talking
Nagesh,
about
this,
this.
Let us
this,
let
No,
us go to
can you
Keshav,
just like what I was actually asking is like, and why we came to this was the like Ankita actually asked me if this was the part I didn't understand. Actually, wasn't. Yeah, there was some steps in the derivation that seemed a bit off, so I just wanted to check it off again so that I can just clarify if I understood everything.
No, she wanted to ask that thing only, that what I suggested, write the identity matrix beside AB, fine. And then tell how this chain thing is working, how we are going from left to right. This is
Yeah. What is your question? Let Maria ask the question. If I don't understand, someone else can explain it to me.
Like, yeah. Okay. Can I just
You tell me what to do also, that also works. So tell me what to write on the board. Will that help you?
No, I think I'll check. Like, this is fine. I think I'll check out the recording once it comes out. Like, I think because there are a lot of people in the meet, so might be a bit of an inconvenience.
that is
No,
not
no.
an issue, Maria. That is not an issue.
Revision is always good.
That has never been an issue
it
in
was
this group.
discussed today, Maria.
That is
Then
never an issue.
I joined around
I
the
can't believe.
11,
Yeah.
so it will be huge advantage for me if they are revising something that I just missed.
Yeah.
Yeah, I can't believe you said this. You cannot say this. You can always ask the same question 100 times. It's okay.
Exactly.
Okay. Can you
Like,
give
I
a
didn't
length of
want to
whatever
say
I
this,
missed
but
today?
I fell asleep in between, so I didn't want to talk.
It's okay. Even Nishant,
Nisha,
Because of your
Nisha,
boring voice or anything, because I did this yesterday too. Like, I was in the bed, so and I'm now also in the bed. So when I'm in the bed, there's like a tendency to lie down and then I fall asleep. So
your
yesterday
camera was off, right? Maria, your camera was off. Nisha, he fell
his
asleep
mic was
in front
on.
of
He was
everyone.
listening to us. He's listening to us, and he was sleeping.
We were being careful that we might wake him up, but yeah. So he was sleeping in front of us.
Maria, the best part is that you woke up to come back and join the discussion. If I was you, I would have left. I'd be like, good night, guys. I'm sleepy. I'll go and I'll sleep. I can't believe you came back energetic and want to continue discussion.
Chetan, I have got a couplet for you at the end ready.
Praneeth is still here, is it? Hi, Praneeth. I didn't realize.
Yeah.
You're so silent today.
Oh, he
That was like
can't.
one day me, Praneeth and Srivinay kind of discussed that
It was on
question,
previous
and that
Sunday.
was really nice. Like that was a really nice discussion.
Was that that sub?
Yeah, maximum contiguous
Yeah,
triangle.
you're right. Sub-array equation, right?
Yeah.
That was the only discussion I missed.
Is
When
anyone
you guys
having
wrote the code.
PDS or
I
DBMS
have
this
also
time?
missed that, I guess.
Yeah, I guess only they three were there. No one else was there.
Is
I think
anyone
someone
having
else was there to
PDSA and
record it.
DBMS this term?
Pardon?
No, I don't have
Is
PDS.
anyone having PDSA or DBMS this term?
Ashik, you?
Done.
No.
A friend of mine is having that, but not me.
I am having DBMs.
Which level you are all in, Chetan?
I'm in the last term. I'm in the last term, so I have 2 courses this term.
It's
Starts
diploma,
from maths.
So
Yeah,
why
foundation.
Acha, foundation.
I thought that you are crossing degree, but you are submitting assignment of stats.
Pardon?
Yeah, we saw his
They got
stats
it.
submission, assignment
They got
submission, no,
it.
one day.
Yeah, when he
Right.
shared the
Yesterday.
screen, yes.
Yesterday. It was yesterday. So I was asking someone about that. Is everything okay with that? And when I shared the screen, that was the first page that opened up. Yeah.
Guys, I hope all of you are getting up once in a while and like walking. My legs are hurting every time. I mean, yesterday I think I was sitting for a long time. I didn't even move. My legs were like cramped when I was getting up. So it was very bad. So today I made sure to go walk around, drink some water, make sure I'm hydrating
Yeah,
myself.
go ahead, Anurag. Go ahead.
Yeah, Anurag.
I think this is an off-topic discussion now, like for the past 5 minutes. Yeah.
No, we'll come to that. We'll come back to the topic.
It
Don't worry.
started when he said he slept off. Yeah.
Could
Kind of.
anyone please give a brief info about what topics are discussed today?
Yeah, we'll do that.
I was in some function and it was only around 11 that I was able to join.
No issues. We'll come to that. Yeah, Anurag, go ahead. Go ahead with your question.
That is not what I was expecting.
That's
Okay. From what I understood, it's basically like placement that happened in the first batch was not really great, so they
Right.
wanted to introduce some other thing like other certifications that we have to do to make us more industry ready.
the reviews that the people in this placement council got was that the students lacked the practical knowledge, the practical application part. So and it was really bad. It wasn't something that they were expecting the placement. So what ended up happening was they finishing degree level this time. Who is finishing degree level?
I think Srivani is in the degree level.
That's great. So did you appear for the placements, Srivani?
No. I don't have another degree. This is my sole degree, right? So
right.
Even for internships, I got internship at IIT MBS. I was the TA for PDSA one term.
Right.
And
Okay.
I was after that I was offered a internship at NPTEL for data analyst role, which I did for 4 months. So 1 term. So I did 2 terms of internships till now.
That's nice.
Yeah, next time I have to start thinking about apprenticeship. Yeah, because I want to do the 4-year degree. I want to complete.
Right. So you were in the first quarter side. Okay. Yeah. It's been 3 years now. Right. Okay.
Actually, the activity points are great, but yeah, we have to work a lot on this. But yeah,
So coming to the activity point, so they thought, okay, that since this is the complaint, so they introduced this system of these certificates that you can get, and for those certificates you're going to get some points, and you can only appear for the placements if you have some minimum number of points, these activity points. So that's the only motivation for these activity points.
So that's why we are getting free Google Cloud and Azure.
So
No,
that
that
was
was
the thing
that's
the ones who had completed it in that time period, only those get the certifications for free. As of
And
now,
also, it's a 1 year thing. So those activity points are valid for only 1 year. So
there's
if
many parameters to that. We have to read it carefully.
Okay, so I've got some Google Cloud
That
certifications. So how
Google
to make that count in my this activity thing?
just have to share the certificates with them. They'll do the thing. But
Okay,
for
I
the
have to send the certificates with them.
yeah,
Okay.
they'll share a form for collecting all the activity points data once in a while. But yeah,
So
so
what other than this Azure and Google Cloud? I don't
there
know.
is Eat Code ka programming, SQL programming,
I think for PDSC there are a lot of stuff for activity points. Like you have to do a lot of questions on lead code, HackerRank, and all those
So
sort
this
of
competitive
platforms.
programming component is a good amount of component, as in for database and PDS as well. For MLP,
Yeah,
they,
yeah.
they use MLP, MLT, they use these workshops. I'm yet to do that.
No, MLP, I think it's a Kaggle competition.
Also,
Like you have to do something on Kaggle.
yeah. So for MLT, it is the workshop. This time they kept the OPP for the workshop, right? So the one who
No, I'm only doing MLT this term, so I don't have any idea about that. But I heard there's a like optional OPP you
optional
can appear.
OPP, right? Yeah.
it
Yeah,
is
it's an
optional,
optional
but the
OPP.
workshop will be considered as your activity points. So in a sense, it is better to do this workshop. They'll release this workshop every single in every single term break, right? So it is
Yeah, I heard that. Yeah.
so in a sense we should do this because it is counted in the activity point, but they don't force, of course.
I did one workshop on deep learning
This time.
this time. Yeah.
Okay,
Was there any exam?
No exam. But we had to like
Project.
follow along. Yeah, it was like a mini project in itself. Just make sure like you work with the data, the ImageNet data. You have to make some simple
So
neural
what do you
networks
use
and
for image processing?
forward.
Srivani, you must be in the first batch, right? That enrolled because that's what Bharti ma'am said. Like when there was a need for diploma, that the first batch of people are getting
Getting what?
Degrees, right?
finishing the BSc by the finishing the BS by this time. Okay, that might be a bit.
Very less people are finishing BS itself.
Okay,
Lot of
you
people
completed
are
your both the diplomas in 1 year, right?
No, 1 year and 4 terms.
Okay, you took okay.
Yeah, so I did foundation for 2 terms, diploma for 4 terms, and degree.
Right.
This is my 3rd term. I'll finish it in the 3rd term, and next I will finish the next BS degree completely in 3 terms. So I'll finish by December of
24.
next year. Yeah.
So for degree,
Is there any reason you chose a slower pace when you reached degree? Because was it getting really
Yeah.
hectic?
I mean, if you want to make the best out of the course, it is better to. I mean, taking 4 is very difficult in degree. Very difficult. And each course
is
is.
limited to stay in 3 terms, right? For degree.
Sorry. Yeah. I did it in 3 terms also because I did an internship along with it.
Right. So
I did 2 internships along with it, right? That is also important. You have to have some real world experience also. So it's
So
better.
what about any internship? Like after you finish one diploma, you're qualified for internships, right?
Yeah.
Then that diploma must be completed along with the projects.
All the projects of that diploma.
Right. Okay. I hope that answered your question, Anurag, right?
Yeah. Like there were parts of the step like where I wasn't. Yeah, I don't want to say the word sleep because it makes me sound weird. Yeah, but can you guys explain some parts of it?
Sure. What part of it? Exactly.
Okay, like why did we actually start with like I understood the steps for a raised to k is equal to m alpha raised to k m inverse, but why did we start with that actually?
No. Okay. You understood the motivation behind multiplying 2 matrices and what it means?
What it means? No.
Okay. So we'll start from here. Here is the right spot. Okay. What does, looking at this matrix ABCD, where does it take 1, 0, and 0, 1?
Oh yeah. This is, you can think of it as 1 times the first column alone.
Yeah, right. So essentially, what are you representing in this matrix? You are actually representing, in the first column, you're representing where 1, 0 is going to. Right? And what is 1, 0 actually?
I grab.
1, 0 can be thought of a unit vector in the xy
X
plane, right?
direction.
Exactly, in
Yeah.
the x direction. And that is termed as I hat. Right? And I think yesterday when we were discussing this, Nishant, Chetan and I, we realized, oh, why is there a I hat? Why are we not using X itself? It was fun. Anyways,
Right.
that is it's just a new notation to it. For now, let's think of it like that. I hat is telling me 1 unit in X direction. J hat is telling me 1 unit in
1 unit in Y direction. Yeah.
exactly. So what is this? What is a matrix actually representing? It is representing a function, and the first column of that function is telling you where I hat is going. And the second column is telling you where J hat is going. You know this. I know that you know this. I'm just reiterating it, right?
Yeah, but that I didn't know it that way. Okay.
Okay. Yeah, you knew it that it was taking 1, 0 to the column place, right?
Yeah, but this is a different way. Yeah.
Exactly. Thinking of a matrix itself, why is there AB over here, right? And why is there CD here? I am storing the information, this function, this brackets can be thought of the function, and I'm storing two particular information in these columns. One information is about where 1, 0 is going to. Second information is about where 0, 1 is going to. How is that going to help me? How is it going to help me just thinking of where I hat is being transformed to and where J hat is being transformed to? Why does it help me?
Because when we did the other question too, this was the way we actually, like, when sir actually like the crocodile mouth thing actually came because of that, right?
Because of what?
Like that sort of shape came because we were mapping X and Y to two different lines. I'm not sure.
Okay. So given you know where 1, 0 is going to, and given you know where 0, 1 is going to, can you tell me where 1, 2 is going to?
Okay, where 1, 2 is going to. 1, 2 will go to 8 times 1, 2 plus
Let's take an example to
8
make this
times 1.
Yeah, sorry. Maybe this is a little confusing. A times 2c plus A times
Okay,
2c
just
and
take
B
normal
times.
numerical values.
Yeah. Numerical values are easier. Where is
You're going
that?
correctly 8 times.
Yeah, she's going correctly. It is better if we look at it with examples. Sorry if I stopped you in your thought process. Let me take an example. Have I not taken an example here? Okay, that is confusing. Okay, let me just take a new example. Okay. I'm looking at a matrix. A particular matrix which we're very, very used to. 1, 2, 3, 4. Oh, we use 1, 2, 3, 4. Yeah, 1, 2, 3, 4. Okay, it's just another matrix, right? Now, what is the first column telling you?
Places where I cap is mapped to, and the second column is where J goes to. Yeah.
Exactly. Now, what is the use of storing this information?
Use.
If,
Okay.
right? Now, if
Hmm.
I tell you, can you tell me where 1, 2 is going to? This is neither I cap, this is neither j cap, right?
Yeah, the other vector that we took was 1, 0 and 0, 1. Okay.
Exactly. This is a random vector v, and I want you to tell me where v will go to.
Where we will go to. You can compute this using the column picture, but I guess that's not the answer you're looking for.
Yeah, what am I using? What the column picture is denoting what? It is just storing information about where I cap went and where j cap went. Right? So just okay. Now, can I generalize this in the sense that if I'm given any xy, right? If I'm given any xy, which is a vector v, random vector v, which, or let's take it as x itself. X is better, right? This is the matrix A. This is the input x. Can you tell me where it goes?
X plus 2y, 3x plus 4y.
Think about it. I am giving you any point in R2. No. What you said is exactly right. What you said is right. I'm telling you about what the significance of the matrix means. What does it mean? Do you have an idea?
Significance, okay.
I am giving you literally any point in R2, and you're telling me the output for it with just the information of where I hat went and where j hat went. This is very, very important. Very. I am telling you I hat was here, j hat was here. I am telling you I hat went here, j hat went here. Now you can tell me if I take any point, random point xy, you can tell me where that xy went to, which is nothing but saying, let me denote it as a of x, y, which is nothing but the transformed version of xy. Let me make it more clear, maybe. Right? So this is xy. You're giving me, okay, you're giving me a vector, which is xy, any vector on the plane, and you're able to tell me where a of xy is. Isn't that beautiful?
To make it easy on mind, you can go with the perspective of column picture also.
X times
that's what it goes.
Just listen a sec.
Mhm.
What column picture says is you are taking two vector and combining them. Now, in a matrix, what does this two column, this vector becomes? They are essentially I and J. Now,
That's what, we are going there. Yeah, you're right. Yeah.
In that sense, what essentially you are saying is the transformation from I and J is simply the column picture itself, a linear combination of columns itself. So they are not a different thing. Just we are just seeing, like from one in we see from the I original Cartesian coordinate system. Now our reference point changed from the now we have vectors, and now we are finding if we are linearly combining them, then where are we?
Too many terms. Slow. It's okay. See.
No. See, on the first day we saw, there was a distortion in that image. We were carrying on some sort of operations, and afterwards, the image was just getting distorted in many ways. Fine, sharing, rotating, X, Y, Z. Today we are getting to know why that distortion was happening. Do you get that? The reason behind distortion.
Oh yeah, it's because I cap is being mapped to a different vector,
No,
right?
no, no, no,
And
no, no, no. We are getting to know the I cap and J cap, the direction of I cap and J cap, where they are leading us to. The problem is that the image in our mind is that I cap will always lead in X direction and J cap will always lead in Y direction. But here, this I cap and J cap means unit vector, and unit vector may necessarily do not direct in X or Y direction. Ultimately, we draw a multiple of unit vector to know. See, unit vector gives us the direction. We we kind of scalar multiply it and just form a vector, isn't it? So what we have got in our hand here is that I cap and J cap as first column and second column of a R2 space. And then we are getting to multiply X and Y and know where it will lead us eventually. Why that distortion was happening? Earlier, I cap and J cap was along X axis and Y axis, that is to say 1, 1. And now we have got a new function, and it will lead us to a completely new direction.
And that is actually
Discuss.
Say, Maria, whatever you.
no, I was sneezing. That's why I just muted. Yeah.
So
Okay.
do you
Yeah.
get?
So yeah. So like so I kind of understood this notation where you wrote AM01. So just like you said, I think what I understood what Nishant says is we can't actually always associate I cap and J cap to the direction of X axis and Y axis. So in this case, what happens is that the first column vector of our transformation is where I cap is getting converted to, and the second column is where J cap is getting converted to. Okay.
Awesome. What is the next connection?
You have two vectors now.
Then I guess the linear combination is also no. Okay, no. Is the resultant vector, right? No, that's not a. What do you do when you get 2 cross 2 and 2?
See,
initially the construction vectors were I cap and J cap, that is 1, 0 and 0, 1 in the simple Cartesian coordinate system. But now the vectors through which you are constructing becomes different, because initially you can reach anywhere in Cartesian coordinate system just using 1, 0 and 0, 1 anywhere you want to go. But now the construction, the base vector itself are changing, that we are representing in a matrix.
The guiding force is changing.
Yeah.
So whenever we do, what we did now is, okay. Is this somewhat like what we did now is actually share? Okay, I don't know if we'll come to use those terms yet.
Yeah, we don't need to. Okay, we don't need to see. Let's go step by step again.
Yeah.
Right. See now. Okay, let me finish this topic, and then you guys can input. She can also start making her conclusions like you guys are making. See, what points you guys are making are conclusions after you know the fact. Okay, so realize that she has to understand why it's true, and then she can understand your conclusions, right? So try to, maybe when you're telling her, try to tell her why it is true rather than telling, can you see it's true? That's not going to help her. You have to guide her saying, okay, what is this then? What is this and this now? What do you think this means? Right? Don't try to So what you're trying to do is what you have understood, you're trying to tell her, right? But what you should do is make her understand the same way you have understood it. That's the best way to teach anyone, right? So let me just finish this slowly. Yeah. Yeah. It's okay. I mean, oh, he's talking to someone else. Okay, sorry, my bad. Thanks for muting him. Yeah. Maria, let's get back to the topic. What do we know right now? Can you make can you state the facts that you understand right now? And the facts have to be, your mind should be completely clear about it. There should be no doubt when you're stating those facts. Can you state those facts right now? What you know?
Okay. Yeah.
I can't hear you
First
properly.
column.
Yeah. Okay. Yeah. Continue.
Yeah. Actually, got that when you wrote it down. Yeah, but other than that, how
So
does it?
state the facts so that even I know what you are clear about. Exactly what you are clear about.
Yeah, the I cap vector gets mapped to the first column of our transformation, and the j cap vector is the second column.
Exactly. So you're what you're essentially doing is storing the information about where I cap is being transformed to and where j cap is being transformed to, right?
Mm-hmm.
And now, since you have worked with matrices before, I am asking you now, given this information that you know where I hat is going to and where j hat is going to, if I give you any point here on R2 as an input, can you compute this? It's a yes or no question. Who's Soumya Katos?
Yeah, allowed her. At 2 o'clock, I'm surprised.
Yeah, even I'm very confused. Hi, Soumya. Maybe it's someone else who's inside this meeting who joining from some other account.
No. She left.
She left. She was
Yeah.
just checking out if this meeting
Yeah.
is going on or not.
Oh, maybe it's sir. I don't know. Maybe not. Sir is already there, is it?
Sir must have messaged in the group or something. That the meeting is still going on.
Check out, huh?
Yeah.
Let me check it.
Anyway, let's come back to the topic at hand. So, did you understand this point, Maria?
No. There's no point. Yeah. What? Yeah. So, given any input, are you able to tell me where the transformed version of that input is?
Maria?
So, like, wouldn't the resultant vector actually be a of 01 plus a of 10? No.
Awesome. You have almost understood it. Okay. So you're able to make the conclusion by yourself, but it's not complete yet. A of 10 plus a of 01, right? By what factor will you plus it? In what factor will you add it?
Because like even when you write down a vector, like in the normal sense in the xy direction itself, when we take unit vectors along the x-axis and y-axis, when you add them, you're supposed to get the resultant, right? So in a similar way, even when you
Exactly. So if I take xy as 1, 2, let me take this as 1, 2. This is nothing but telling me, this is nothing but 1 times I hat and 2 times j hat. Do you agree? Right? What is the significance of this? Because it is a linear transformation, right? There is a property of this function which you will soon understand. If I want to find out where the transformed value of 1, 2 is, I don't have to do anything other than I have to scale I by 1, scale the transformed version of I by 1 and add it to what?
We have 2 times A of 0 1.
My bad, let me not write. Exactly. So this 2 times A of 0 1. This is what you said, right?
Mm-hmm.
Is this is always true? Is this always true?
This is always true. Okay.
Always. Okay. Is this true for this matrix?
Okay. When the rows are dependent, you will get both the components to lie along the
Even then it is true
same.
actually. Even then it is true. Even if A of 1 0 happens to be 1 2 and A of 0 1 happens to be 2 4, you will still take 1 times 1 2 and 2 times 2 4 and add it up and you will get A of 1 2. Which means you are able to represent the input as a linear combination of I hat and J hat. So it is X times I hat plus Y times J hat. You can represent the output after the matrix multiplication as
A times A X times A of I cap plus I cap of 1 0. Yeah. Plus Y times
Y times
A of J cap.
exactly. This is why you need to only store this 2 vital information. That's all you need to store. You just need to know where I hat is transforming to, where J hat is transforming to. With any input of XY, I can find it.
So in the end, okay. That's nice.
And after discussing this, we expanded this idea to multiplication of two matrices. Okay, we expanded the same idea to the multiplication of two matrices. So here you had the input as a column vector x comma y, right? So what happens when you have two matrices? What happens then? So that was the next question.
What does it mean to multiply two matrices?
But first, tell me, you've understood the previous part, right? You've understood what multiplication of a matrix with a column vector or input x comma y means, right? You understood that part.
Yeah, so when we do a linear transformation, the idea that you guys are trying to say is that you only need to know what the unit vector transformations actually map to. So
Right.
yeah.
Correct. So if you know that part, then you can easily calculate the resultant vector, right? So you can know where the point is going to be mapped to. So now that you've understood, we are coming to the part where we are multiplying two matrices. Okay. Now, what do you think will happen when we multiply two matrices? What does it actually mean to say when we say that we are going to multiply two matrices? What does that mean? So you understood the meaning of the previous thing, right? That you yourself explained what that meant. But what does matrix multiplication means? So now,
So in that case, like, okay. Okay, we have two, if we try it in that way, we have two column vectors as inputs here.
right.
Is that the way to go about it?
Yeah, you're in the right direction.
But why, what is special, what is different in B from A that you're thinking of this as two column vectors as input, but not thinking about it as a function itself?
Correct.
I mean, you're thinking of A as a function, right?
Yeah.
If I'm not wrong, you're thinking
Yeah,
of 3, 4, the first column of B as the first input for function A, and 7, 9 as a second input for function B, right? But isn't a matrix a function? And isn't B a matrix just like A? Why? I mean, what allows me to think that it's
Input, not a matrix, not a function. Right.
Is multiplying A by B giving you something like the composite function? It's the thing that comes to my head, and I don't think so, no.
I mean, that's a different part. We're going to come to that part too. But right now, we're just asking that what did tell you, or how did you assume that the B is the input and not a function? Because we know that the matrices are functions, right? So why take A as function and not B as function? Why not take A as input, and why not take both as functions?
Okay, I guess the reason I came to that conclusion was only that because we were doing AX equal to B, and in the right side it should be input. But that was just because we were doing that. There wasn't any
Right. That's the idea.
reasoning.
So we take our input on the right side, right? Go ahead.
Going by the pattern,
That's
the
it.
food that is fed for a function is always on the right side.
Right.
And function does what it has to do with that food.
Right. Just that idea. Yeah.
But B does not have a input, is it? B does not have, so B is a function, but it does not have anything to its right. So what does it mean for B?
Okay, so you can think of
What
B
is
does
the
not have any
output?
input. What is the output?
What is the output of A into B first?
Yeah, come to that part, right?
Using your high school math, using your 11th, 12th,
Yeah,
what is the output?
Yeah, it's one time, like the first element would be 1
No,
times 3
I
plus
don't
2.
want that. What is the nature of the output? Let's say this is a 2 cross 2
2 cross 2
matrix.
into 2 cross 2 is a 2 cross 2. Yeah.
Correct.
So the output is a, let me zoom out a little.
2 cross.
Okay, it's not here, is it? My bad. Okay, the output is a 2 cross 2 matrix.
Okay, on the left side, you can. Okay, maybe
No,
maybe
left
somewhere
will
else.
become,
Maybe somewhere else. Let's take write it somewhere else.
Isn't this where I taught her this? Okay. I'll go ahead with this. So we have A, 1, 2, 3, 4, and we have
another matrix.
B, which is 3, 7.
Anything.
4, 9. Yeah. 4, 9. I want it to be same so that we can check the. I mean, it's always same example every.
Same
3, 7, 4. Awesome.
Okay, go ahead, Maria.
Okay.
So you told that the resultant matrix should be a 2 cross 2, right?
Okay, maybe we can find the first column of the resultant matrix first, because we know that it's going to be 2 cross 2, right? So
See,
just the
okay.
first,
Yeah,
yeah,
go
yeah.
ahead, go ahead. Complete. Yeah.
Sorry, go
Go
ahead.
ahead.
We can find the. I mean, I wanted to write it down here. Yeah, go ahead.
So just think of them individually as like anyway, both the columns individually will be 2 into 1. So you can just think of it as independently applying A to the first column, and then putting that in the first column of the resultant, and then applying A to the second column, putting that in the.
That is our formula, right? To the right and to the bottom. High school formula, right?
Right.
Yeah, this is the same as the high school formula.
Okay, but what do you okay? What does it help you understand about A into B? Does it help you understand something? Okay, you got the output. Output is a
Like
what is the output?
2 cross 2, yeah.
2 cross 2 what?
2 cross
Cross
2
2
matrix.
matrix, and matrix is a what are matrices?
Collection of column vectors or vectors.
Yeah, but what does that information of collection of those vectors mean?
The functions, right?
Oh, you're
matrix
getting
is a-
another function when you, yeah, okay.
That's how I wanted to think about it. M in itself is a
function.
Now it gets more interesting. I am multiplying a function with a function and I'm getting a function. What does this mean?
So that's how you came to the, okay.
No, don't forget about what you want to connect with what you know or what we discussed before. I wanted to go ahead with this with a clean plate so that you can understand what multiplication of two matrices mean. And once you understand it completely, you can make a lot of very simple, quickly, you will be able to make a lot of conclusions. You'll be able to finish off equations, stuff like that. So I mean, even though I can get the answer by doing write down, write down. I mean, it's not telling me anything. It's just telling me.
But you've understood the previous concept, right? Can't you think of this in terms of that?
Before that jump, wait, what is very surprising? Right? There is a function here. There is a function here.
And resultant is a function.
I am multiplying two functions and I'm getting a function. That means I'm able to represent this
as
just one function. I am able to represent 8 values as just 4 values.
Yes.
What does it mean what does the representation of this A, B, C, D mean?
Function, a new function.
This is another function.
You can probe her into getting the right answer.
Now that we've reached this conclusion, right? That we have two functions. We are multiplying those two functions, getting a new function. Now try to go back to the concept we were discussing before. That there was a matrix. We gave it an input, and with that matrix, we could tell what the resultant output was going to be, right? We could reduce that from that. So now try to link this, try to see what you can take from that and apply here, or can you even apply that here? Can you even do that?
What you did there was you. So
Does it even
AB
make
is
sense? Yeah, does it even make sense?
okay.
I'll again come back to the main question. So what does it actually mean to multiply two matrices? Right.
Chetan, before this,
So
what you asked? I missed it.
Pardon?
Before this question, what you asked?
Before this question,
No, you said that what two matrix multiplication means, right?
right,
Before this,
right.
you asked something. I missed that. That is it.
I have forgotten what I said.
Okay, no worries. No worries.
Probably it wasn't something important. If
No,
it was
no.
something important, we'll come to that
Yeah,
again.
yeah. Maybe I'll put it down. Can you all hear me?
Yeah, sure. Go
Yeah.
ahead.
Maybe I'll
Yeah,
put
yeah,
it
anyway, I
down.
guess there's a meeting summary generated, so you won't miss out, I guess, on the main stuff we discussed, right? Yeah, because there's something Zoom automatically does, right?
What?
There's a meeting summary being generated based on what we
Yeah,
say, I guess.
actually, I'm recording as well. So
Yeah.
the recording of this will be available. Don't worry.
Yeah, we just have to, yeah, maybe Ashik can go that, yeah.
Both Ashik and
Okay.
Maria.
I'm pretty sure it wasn't something important. If it was something important, we'll come to it again. Don't worry.
Okay, I'll
No, I
back to
was
the
following
question.
completely this statement. There was some net issue. Yeah, Shrivina, you were
Yeah,
saying.
yeah. So what Chetan is trying to say is think from first principles.
Right.
What does a matrix mean? What does multiplication of two matrices then mean?
What would
does
it
the
signify? What would it even signify?
Exactly. That's all.
Yeah, got it.
So you're reducing 8 values to 4 values.
Yeah, right. But before we even come to that, what does matrix multiplication even mean? What's the crux of it? That is just the observation part that we're reducing the eight values to 4 values. Yeah, we know that. But what does that? So you knew in the when we were taking a matrix and an input, and we could judge that okay, we have a I cap vector, we have a j cap vector, we are scaling them, we're transforming them, and we were taking the resultant of it. That was that multiplication giving us, right?
Yeah.
So what does multiplying two functions, two matrices would signify in this case?
Okay. Nothing. Okay, I think I need a bit more hints so that I can
Okay.
come to it.
Okay. So we have resultant is our two vectors, right? We are getting two vectors as a resultant, right? So you must be doing something to get those two vectors, right? Something like in the previous discussion, we knew that we had two vectors. We were scaling them, and we were getting two vectors on in the output, and the resultant of that was the mapping, or was the transformation, right? So we are getting two vectors here as well. What are we doing to get those two vectors? That is the part. Yeah. Just look at this
This is what
and
you
see.
meant, right?
Yeah.
This is what you meant, right? You were talking
Right.
about this. Okay.
Right. So your A is your matrix, right? You have two vectors. You're doing something to those two vectors. As a result, you're getting a transformed version of those two vectors.
Okay, each of the columns would be one of a transformation
Right.
that's applied.
Right. They're in the right direction. Right. So how are you going to get that transformation? You've understood that it's some sort of transformation, right? You've understood you're doing something to that vector to get a new transformed vector. So what are you doing that? Just look at this. See, what is your A times V2 is, and what is your A times V1 comma V2 is? Can you relate it? Can you think of something with this?
Sorry. Okay. Maybe we'll take it a little slower. Maybe. Okay. Let me just take a few seconds here. Okay. Look at A alone, Maria. What does the first column of A signify? What does the second column of A signify?
First column was
Yeah, whatever you're thinking is right. You can just say.
When we took a matrix,
It's the same thing as. It's the same thing that we discussed in the previous concept as well. Same thing. It hasn't changed. That remains constant. So what is your first column and what is your second column in matrix?
first column is the I cap part, right?
Right.
And second column is the
Correct.
Okay, so I will think of it as where A is taking I cap and where A is taking J cap.
Correct.
Yes.
Always. So this is the first principle of a matrix. This is why I would say this is thinking from first principles, because what does a matrix even signify? The matrix is signifying, the first column is signifying where does I cap go, second column is signifying where J cap goes. It's literally it's literally the defining term of the matrix. That is the first principle of the matrix, right? Okay. The same happens for B, right?
And let me add one thing to this.
Sure.
See, we have got 1, 3 and 2, 4. Fine. Now we are saying repeatedly that the first column signifies the I cap and the second column signifies the J cap.
Right.
Fine. But at the same time, we are also seeing a matrix seated right to it. Just forget for a second that there is a matrix right to it. Fine. In order to visualize 1, 3, 2, 4 as a function, multiply it with 1, 0, 0, 1. Why I'm saying multiply it with 1, 0 and 0, 1? Multiply it with 1, 0 and 0, 1 because doing that will ensure that I cap gets added to the first column and j cap gets added to the second column. Now you see, now you see that the direction of I cap and j cap has changed. Do you see that? Earlier it was 1 unit to the x-axis, 1 unit to the y-axis. Now the I cap is directed in the direction of 1, 3. The j cap is
Direction
directed.
remains the same. Direction remains the same. Direction hasn't changed. It's just that you are transforming it. You are
You can say
scaling.
you can say transforming it or scaling it. You can say that. Just
Why
imagine.
Why do you say direction hasn't changed?
Why would the direction change if my inputs are 1 and 3? Right? I'm not scaling it down, right?
No, he's saying Chetan is saying that why use the word direction, rather say use the word linear combination.
Right.
Saying 1 and 3.
When you say scaling, it will include scaling up and scaling down. When you're saying linear transformation, you're including those parts, right?
Yeah.
When you say that direction has changed, you mean that you have scaled it down and the direction has reversed somehow, right?
No. See, I can think of direction change from. I can move. So 1, 0 to 1.10 is also a direction change for that vector.
Yeah. I mean, yeah. If you want to think it like that, yeah. But what I meant was that you can, instead of going talking about that in that way, you can simply say that you have scaled it, and you have, or you can simply call it a linear transformation of that vector, right?
Anyways,
I also thought of it like you can take each of the individual columns as input and then just add them to your output vector.
No. Let us go step by step. Fine. The very important thing is to understand why this first column is I cap and why this second column is j cap. Are you getting my point? If I am going to multiply it with the matrix 1, 0 and 0, 1, it starts signifying I cap, first column, that is 1, 3.
It signifies that even before.
I'm just for the sake of understanding. 1, 0, 0, 1 was a kind of hidden there. I'm just trying to imply that to add a direction to it, to add a I cap to it, to add j cap to it.
Right.
Fine. So 1, 3 is the new I cap direction. The vector 1, 3, just put 1, 3 on R2 plane, draw a vector from 0, draw a vector to it. Fine. That direction is the direction of I cap now. It's not direction. It's not directed in x towards x axis.
So
now take 2, 4 and direct draw from 0 to 2, 4. That is the direction of j cap, new direction.
Right. So you have a resultant matrix, right, Maria? You have a resultant matrix of this. When you say that I have multiplied 1, 2, 3, 4 with 1, 0 and 0, 1, you have a resultant matrix, something, right?
Yeah.
Now that you've understood that part, now you can go ahead. You've understood everything.
You multiplied it 1, 0 and 0, 1, you got a direction.
Wait.
Okay. So
Okay, yeah. If you got something,
in this
go ahead.
case, our direction is.
Wait. I want her to continue her thought. If she's saying something, I want her to finish her thought process, please. Yeah. Whenever she's saying something, we'll be quiet. Yeah. Yes, Maria. Please.
Okay. So if our unit vector is in the direction of 3, 4, is that the way I should think of it? And then when I multiply it, the direction gets changed again.
Okay. Shrivana, can you scroll down? Can you write that 1, 2, 3, 4 and 1, 0, 0, 1? 1, 2, 3, 4, and 1, 0, 0, 1.
No, I don't want to. I don't want to. Okay, wait.
Next is the scaling part. Once you get the direction, you just scale it.
See, the thing is, one second. You guys, okay, when you introduce Nishan, when you introduce 1001 as a matrix here, it was being transformed to 1, 2, 3, 4. I understand.
Don't do it. That's not what I'm saying. So I am saying, write the matrix 1, 2, 3, 4. I'm coming to the concept that she has already understood. So can you scroll down and write 1, 2, 3, 4, and in front of that, write 1, 2, 3, 4. In front of that, you write 1, 0, and but in below that again the matrix 1, 2, 3, 4, and in front of that 0, 0, 1.
Yeah.
Right. So tell me, Maria, what would be the resultant of these? So you
1,
understood
2.
this part, right?
Yeah. 1, 2, and second one would be 3, 4.
How?
Oh no, sorry, 1, 3, 1, 3, and 2, 4.
Go to the basics. Go to the basics. How?
Because it's 1 times the first column.
Right.
Or you can think of it as you're taking the first
Go ahead.
Yes, you said it right. 1, 3, and 2, 4. It's simple, isn't it?
No, go ahead, Maria. You were telling us how to go ahead. What would be the resultant of this?
1,
Forget
3.
about other things. The resultant of this from the basics. Suppose, imagine that I don't know anything. How would you explain this to me?
Okay, how would I explain this to you?
How do
So you can
write it?
think of 1, 0 as a unit vector in the I direction. So what you're doing is you're taking the first column to the you're okay, you can't use a word. You're taking that to 1, 3. Okay.
What would okay? Yeah. Go ahead.
Oh yeah, and then the next one is because it's 0, 1, you can think of 0, 1 as a direction along the y, like a unit vector along the j direction.
J cap.
Yeah, j cap. And you're taking that unit vector to 2, 4.
Scaling, right?
Not scaling it, right? Is scaling the right term to use here?
Linear transformation.
Linearly transforming it in that action.
Yeah, linearly transforming it.
Right?
But because Chetan said I have to explain to someone who doesn't know, like that's why I didn't want to use the term.
No, yeah. So now that you've come to this part, you have a matrix 1, 2, 3, 4, another matrix 1, 0, 0, 1.
So what happened afterwards? If we have
So
multiplied
when
these
it
two
is
matrices.
3, 4, what do you do is
So
within the
again, I
matrix.
don't know anything about it. I'm just telling you that I have two things, 1, 2, 3, 4, and 1, 0, 0, 1. That's it.
This is so beautiful.
Just look at what you did. Okay,
Yeah,
so
I
can you tell
mean, I
me
know.
what is this 1 0 and 0 1? Can you tell me this? What is this 1 0 and 0 1? What is this 1 3 and 2 4? Can you tell me? Break this down to me. I don't understand this. This is a very complicated notation for me. What is this? I don't understand all of this. Just tell me what is this. Or just break down what is 1 0 0 1. What is that? What is that? Just break down that part. What is
The
this 1 0?
blue, I cap and J cap.
I cap and J cap, right?
Hmm.
Right. Now that you have figured this part out, can you just look up and then look down and tell me if you see something? If you see something.
Yeah, you can think of the output as you're applying the transformation to the, I
I
mean, the
don't
first
understand. I don't know what factorization is. But yeah, go ahead.
Not factorization, he said transformation.
Okay, sorry. Yeah, go ahead. Go ahead.
You're shifting the direction of I cap to 1 3, and you're shifting the direction of J cap to 2 4.
But how did you come to that? So I have something. What is that? Right? What is that? You're right to that part, but how should I write it here? Like how you can write that 1 3 as 1 times 1 3 and 0 times 2 4, right? On top, when we are talking about
Yeah.
1 2 3 4 times 1 0, you can break it down to 1 times 1 3 and 0 times 2 4, correct?
Yeah.
Plus 0 times
And the
2 4
next one you can write it as 0 times 1 3 plus 1 times 2 4.
correct, right? So how would I write the same thing here?
Okay, same thing here.
Mhm.
1 3 times 1 0 as a row vector plus 2 4 times.
No, I don't understand it. I don't understand it. Hard for me. Just look up and look down. Just look up and look down. That's all you have to do. You have everything. So you figure out what is 2 plus 2. You have figured out what is 4 plus 4. I'm just asking you what the end result is.
The first part would be a first column, and the second thing that we would be a second column, right?
Yeah, so I will have 2 columns. That is understood. That part is understood. Look at the arrows. Look at the arrows. I know that I will have 2 columns. It's the resultant matrix is a 2 by 2 cross 2 matrix. It will have 2 columns. What are those 2 columns? Shrivina has drawn some arrows. I don't understand those arrows. Can you tell me what those arrows mean? Okay, it's not that complicated. You just intuitively what comes to your head is the right thing. Your voice is muffled.
Yeah, am I audible now?
Perfect.
Okay, so I have
Intuitively,
to
what comes to your
express
head?
what I wrote on the top into this matrix, right? No,
I'm just asking you, what should I write as the columns? That's it. That's the only part I'm asking. And Shrivina has told you the mm, the 2 plus 2 and 4 plus 4 part.
Hey, it's yeah, it's 1, 3, 2, 4, obviously, but uh,
But how, isn't it?
yeah,
You figured out. I'm telling you, you figured out everything. Everything you need is actually on this whiteboard.
yeah.
And even Shrivina has even told you that what to do. That much I can tell you. Just look at those arrows. Where do they start from and where do they end? Just tell me that part. What is this first arrow doing? Where is it coming from? Where is it its tail? Where is its head? Tell me that part. That's the only thing I know. First arrow on the left
1
side,
times 1, 3.
1 times
1, 3.
okay, okay.
Let me
But
break it
is
down
that
for
the only thing? Is that the only thing? Is this the
no,
only
no,
thing?
no, no, no.
Is the tail
Let me break it down for her. Just you know, at times we must do things. Let us write it down. You know, as she said, the answer would be 1, 3, 2, 4. Just write it down for a
Yeah.
second. 1, 3, 2, 4.
Correct, Maria?
We agree on this, Maria?
Yeah.
Fine. Do not just, you know, look at the possible permutation and combinations. This is a fact, we know this. But what we want you to look at is that from where this 1, 3 has come and from where this 2, 4 has come.
See, the answer is the tail of those arrows and the head of those arrows. That's it.
Huh.
Bring the tails to the head.
Huh. That is the question. Do not just think why, you know, just tell me from where this has come here.
That's it.
That's it.
Where has it? Oh,
From where has it come here? And do not stop looking at the left hand side of that equation. Rather look
Yeah,
at
forget about that. Forget about that.
rather look at the tail of the arrows.
Tail of the arrows.
Okay, if Maria,
okay. You're applying the okay, no, this is correct.
No, no,
Okay,
just say it. It's right. It's right.
yeah, you're applying okay, you're applying the just like yeah, you're applying A of I cap to the first column and if they kept to the I okay, maybe it's a time, yeah, I don't know.
No, you are right. You are right.
just explained it, right? This
Just-
is A of I cap, this is A of J cap. That's what you have to do in the columns. You're right.
And that is the motivation behind why it exists. That's why we have been saying it. This is I.
Okay, so what happens in that was because it was identity, but in our case it's
See. Let me. Can you write in front of that?
That is the purpose of identity matrix or anywhere identity. For example,
But before we move on, how to break it down? So this is 1, 2, 3, 4. Can I write it as 1, 2, 3, 4 times a column vector 1, 0? Whatever it was written there, can I simply drag it down?
times 1, 0. Yes, you can do that.
And what would be
Okay,
then
that's
my
what you meant exactly. Okay. Just write what's on the left side and then yeah, okay. 1, 2, 3, 4 times 1, 0 plus 1, 2, 3, 4 times 0, 1.
Right.
Okay.
Right.
Yeah, that felt, yeah, okay.
Okay. So this times 1 0 and times 0 1. I have my two columns now of this matrix. I have broken down how to get those columns. And you, as you have already told me, that the answer of this is 1 3 2 4, right? This is 1 3 and 2 4, right? We figured out this answer on the top, right? I just copied the answer from that. So 1 2 3 4 times 1 0 is 1 3, and 1 2 3 4 times 0 1 is 2 4. I have just copied down that same thing, right?
Yeah.
So now, do you understand what we did here? Just tell me in your own words what we did here. I don't understand anything.
So basically we did yeah, we applied the I cap transformation to the first column and the J cap transformation to the second column. No, not that. Okay.
Did we apply
Where
only on
did
one
we
column?
did we apply it to a column? Did we apply it to a column? That's my question to you.
Okay, we applied it to the entire.
Uh-huh. Go ahead. Go ahead.
To the matrix. No.
Uh-huh.
I'm just guessing now. Like
No,
I don't.
that's right. See, you have written 1 2 3 4 times 1 0, right?
But
I'm
when
just
we
asking.
write that, usually it means that your input is 1 0, right? Not 1 2 3 4.
Yeah. It doesn't matter. I mean, see, we started from the basic. We understood what a multiplication of a matrix with a column vector means, right? We have just used that here. We have not introduced any new idea here, right? You yourself told me that the matrix 1001 has two columns, two column vectors. One represents the I cap, one represents the J cap, right? And on top of that, you have already told me what happens when I multiply 1 2 3 4 with the I cap vector, and what happens when I multiply 1 2 3 4 with the J cap vector. You yourself wrote that. I didn't write that, right?
Yeah.
So I just summed all of that up to get the multiplication of 1 2 3 4 with 1 0 0 1. And you told me how to do it.
Yeah, but normally when we do, you said that you're applying 1 0 to 1 2 3 4, right?
Correct.
But normally when we do it, 1 0 is our input, right?
Right. Exactly. That's our input. But in this case, we have two functions. You broke down that function. You yourself broke down that function by saying that my first column is my I vector, my second column is my J vector. In the top, when we said 1 2 3 4 times 1 0, you did not ask me whether this is an input or not. You told me that this is an I cap. You told me that. You didn't ask me whether it's that input or not, right? Can you scroll up a bit, Shona? Just a bit. I want to, yeah. So you wrote I cap on top of a 1 0, right? You did not say that whether it's an input I am getting or not, correct?
Yeah.
You just took a unit vector, you scaled it. What are you doing in the matrix multiplication? Are you doing anything different? Just look at it. You got two column vectors, two unit vectors. As you were getting earlier, you did something to them.
Okay, I'll intervene from now. Maria, how is this? Okay, I'll just ask you one question. If your answer has improved, Chetan can continue. If your answer has not improved, I'll take over. Okay. When you previously saw matrix multiplication, how did you see the multiplication? And now after all this, how are you seeing the multiplication? Is there a difference, or do you feel, I just feel like I'm doing the same thing? Honest answer. I just want an honest answer.
We just want to know what you have understood till this point.
Like the idea that I got was you're taking the two column vectors as inputs and then just applying that matrix independently, like, and creating the two columns. Like, yeah,
That was your idea at first, right? That was your first idea as well, right?
yeah.
Okay. Okay. So, Chetan, let me take over from here,
Yeah.
and I'll keep it crisp and short. Okay. I'll keep it very, very crisp. Okay. First, if Chetan, I wanted to note a few things which I am saying, which I feel you have missed out. I just want to point a few things. Obviously, you've done a good job, but I wanted to understand there were some points that you missed out that maybe didn't help her look at it as two functions, right? She's still looking at the second matrix as inputs, which is not great, right? She still has to look at the second matrix as a function itself. Because matrices are functions, right? In the end,
right?
Right? Okay, let's do this. Now, what if I want to find out, right? We saw A is a function, B is a function, and M is a function. And we are equating the two, which means if I apply whatever this means, A into B, I don't know what the multiplication of two matrices mean. I don't know the logical meaning of it, but I know if I apply this function, which is I am getting, if I apply this on vector V, and if I apply M on vector V, what will happen, Maria?
You get the same thing.
You get the same output. That means, what does it say about matrix M?
M is also a function.
Yes.
Correct.
And what can you say about the function? How can you relate it to A and B?
Function is same as AB.
Exactly. So you are able to, when two functions when multiplied with each other, two matrices, these two matrices when multiplied with each other, you're actually able to represent it as one matrix itself. Right? Which is nothing but saying, if I apply this matrix on V vector, or if I apply whatever this means, if I apply this, let me include that, right? Let me include V vector, right? What does V vector mean? If I include V vector, it means I'm inputting something to this, right? Oh, I've also added a few points. Okay. Okay. Where would the input lie? Can I input it here?
No, you can only input it to the right side.
Awesome. You already know that, which is good. That will make things faster. So you will put the V vector here, right? So this is V vector, right? So this is A into V, sorry, A into B, and you're transforming the vector V, right? Awesome. That is the same as doing M, right? M is a 2 cross 2 matrix, right? And this is vector V, right? These two sides are equal, completely equal,
Yeah.
right? Now, if I want to think of this side, okay, what am I looking at? I'm thinking, okay, if I had an input for this A into B, right, it would end up being here. The input will always end up being here. I cannot input it here, right? I cannot input it here. It will mess up the entire, the cardinality of matrices or whatever that is, right? Whatever you think that is, right?
Yeah.
But we know we put it here, right? Input goes here. So what will happen to vector V?
It's going to be transformed to another line.
Awesome. Awesome. Line or vector, right? One more vector. It's going to be transformed to another
It's
vector.
going to
Right?
another vector, yeah.
And what is the transformation? Let's break the transformation. Let's try to break the transformation. If I see a matrix and I see a vector, we've done this before, right? We have not seen this before. We've not seen a matrix with a matrix, but we've seen this before, right?
Yes.
So what will this give me?
Another vector.
Awesome. And if I have, okay, this entire thing becomes, so this entire thing becomes just another vector we had. Now can I do this? Have we seen this before? Matrix and a vector,
Yeah, I can do that, yeah.
right? So what have you done essentially?
Think of it in terms of composition of functions. What happens there is happening here.
Okay, you're giving the output of one as the input to the other.
Awesome, awesome, awesome. So this is very similar to f of g of x, right? If we think about in, right? Here x happens to be the v vector, g happens to be
The second thing, G happens to be another function.
what is that function in our left
Case
hand side?
3479.
Yeah, which is B, which is a matrix, right?
Yeah, B, yeah.
B. And what is F?
F is also another matrix.
Which is A, right? Awesome. So you can think of multiplication of two matrices if given an input such that first input this to
B and then
yeah.
input it to A. Okay.
Awesome. Awesome. So you're saying right, but this doesn't work in matrix denotation. The denotation of that happens, okay, right?
Only for functions, yeah.
Right. Now, actually, that actually can happen. Why not? Actually, that can happen. Whatever I wrote actually can happen. Let me see actually what I wrote. I said, yeah, apply B on V. Sorry, apply B on the vector V, and then whatever output you get, apply A on it. This is right. This is not wrong.
Yeah.
It's not wrong at all, right? I mean, I don't know if
Yeah, it's
matrix.
right.
Yeah,
It's right.
Yeah, exactly. This is right. Okay, but let's not. Okay, let's not go there because when I think about, okay, now you've understood what it means for. Now you're looking at A also as a function, B also as a function, right?
Yes. Oh,
Now
yeah.
you can see that okay, A is a function, B is also a function just like A, right? And the function hierarchy is such that you go from left to right. You apply the left function first, right function first, and then apply the left. I'm so directionally disabled. I'm so sorry.
You are reading it like Urdu.
Yeah, you're reading it from right to left, right? Which is similar to how you read f of g of x. Okay, let's go to the next thing. So you understood this, right? I can be sure that you understood this. Awesome, you understood this. Now, let's say we don't have an input vector. Now, what does it mean to multiply two matrices?
So when there's no input vector, you can take that as the unit. No, you can't. Okay, that's only if it's as a matrix. There's no idea of identity as to cross. Okay.
You are going right, Maria.
Okay, so now I will go to what Chetan has explained to you now. I would do that. So that's what I would have done. I would have explained her this part, which makes her think of A and B both as functions, and
As
then I would
functions.
go to this.
Got it.
Right?
Got it.
Awesome. Now I can write any matrix.
One caveat.
Sure.
Matrix is an array of number. Fine.
Mm.
What makes it that function? Forget we know anything.
Mm.
But we know this as a fact that it is a function. How does it become a function? This thing we are dealing with makes it function. We write an array of number, multiply it with unit vectors, means identity matrix, and give it a direction. By giving it a direction, what happens? We scale it, put any scale to it.
And then we add it, yeah.
Put any scale to it. Once you have given it a direction, scale it to your need.
Liking. Yeah.
Scale it to your liking. It will act as a function. Isn't it?
Mm.
But you will have to understand them. Why first column is I cap and second column is J cap in that case.
Yeah. And you have understood that, right?
And you have understood that. You yourself told us, how that is very obvious thing. Identity matrix is hidden. We do not write identity matrix every
Exactly. We don't always write it, but it is always there.
Always there. With every matrix, it is there.
Exactly.
Okay.
Now we've thought of two matrices as two functions, right? So what does this function do?
This function takes the unit vector along I direction to 1, 3.
No. Look at where the arrow is. I'm looking at this. What does this matrix do? What does this function do?
It gives you the
like you're thinking, however you've been thinking of all matrices you've seen till now. I want you to think of this also just like that matrix. Don't treat it any differently.
Right.
Okay, so this is also a function. Yeah, so this function will give you the same thing like that you gave as input. You'll get it as output.
Awesome. So I cap is being mapped to I cap, J cap is being mapped to J cap. That's what it means, right? This function is telling you 1, 0 is going to 1, 0, 0, 1 is going to 0, 1. Good. And we know that if I know where I and J are going, I know what the entire plane looks like. Very simple. Now, this matrix is telling me, now if I look at this matrix as a function, it is telling me, if I put any input, take it to that input. If I take Any input, take it to that place, same place, right? Okay, sorry, let me not repeat myself again. Let me get my thoughts together.
Yeah.
Okay. Now, what we saw up was, now I'm thinking this also, I mean, I'm looking at A as a function, and I'm looking I as a function, and I'm taking the multiplication of A and I.
Hmm.
And I want to know what this equals to, right? Logically, what does it equal to?
So when you multiply two, okay, that doesn't make sense either. What happens when you multiply two functions?
Can you think of the second matrix as
No. One second. When we multiply two matrices, it gives us a matrix, and that is a function. You know that, isn't it?
Yeah.
Yep. This is all why I wanted to say. This is a function that you are getting.
True.
When you multiply anything else to this function, it will yield something else. And this chain will go on. We gave you example of this unit matrix because you were very much familiar with this, and this was easier to imagine.
Yes.
So,
but there is nothing special about this matrix. It's just a matrix, just like any other matrix. So if you understand this, you understand others as well.
all matrices behave in the same way.
Right.
All matrices are functions, and eventually it will lead you to a particular place.
Okay.
See, the two things are always constant about a matrix, right? That you can break it down to two column vectors, I cap and j cap, and the matrix is a function. Correct? That
Yes.
remains true for this as well. And you also know what happens when you multiply a matrix with a vector, what it signifies. You also know that part. What does that signify?
Let me just finish this up, okay? Yeah. Okay, Maria. This function is telling me take I cap to 1, 0, j cap to 1, 0. This function is telling me it will take I cap to 1, 3, and it will take j cap to 1, 2, 4. So I cap is initially 1, 0. And now I want to go to
1, 3.
Right? Okay. So that is what I don't want you to miss. I want to think of this, right? And I'm looking at 1, 0. Okay. This entire function is going to act on this because I want to know, I want to take this. If I take this as my, I don't want to take it as I want to take it as some vector v1 and some vector v2, right? This is telling where I cap and j cap will go. But if sorry, not that alone. This entire matrix is telling me where I cap and j cap will go, right?
Yeah.
So I'll have to apply that on any other v1 and v2 to understand where it will take that v1 and v2. So that is why you did this entire elaboration of, right? You understood where it is taking the first column. It is taking this. It is saying, okay, where is the I cap currently? Where am I right now in space? And I want to transform it in this fashion. I want to transform it in this fashion, in this fashion, in the entire A, right? I want to take the second vector, whatever is there, I want to transform it with this fashion. Right? Maybe I'm using these terms because it's 1, 0 and 0, 1. I don't. Okay. Let's just play it out, right? We already played it out. And we saw we'll get 1, 2, 3, 4. You understood this? And why are we getting 1, 2, 3, 4? You understood that here?
Yeah.
You're applying the function on the first column and you're applying the function on the second column, right?
Yeah.
Now, what if it is A times B, right? What happens when it is this? This function B is telling me first take 1001, which is, let's say this is imaginary. This is not, it's not visible to, it's not visible to human, right? It's there over there. This B is telling me take 10 to 34 and take 01 to 79. Correct?
Yep.
And what is this A going to do?
It's going to take the output of that and put the map take that to 1, 3.
It is not going to take it to 1, 3. It only takes 10 to 1, 3. Remember that.
Yeah,
So
it
if
will apply that to the output of what you
so
get there.
it will apply the entire function on this to see where it goes, right? See, if you want to know where this point is going, you have to apply the entire thing. While applying, it so happens to be that this is being scaled by 0. Correct?
Yeah, yeah.
Right? So the second, when in this case, I have to be careful. I have to say, okay, I have moved from 10 to 34 and I have moved from 01 to 79. Now I want to apply another function on this function, right? Then I have to apply the entire function on the first column and I have to apply the entire function on the second column. That's what we were trying to show you here, that if you apply the function on the first column and you apply the function on the second column, you will get your result. What we would have usually done is, what did I learn in high school? I said 1, 2 into 3, 4, 1, 2 into 7, 9, 3, 4 into 3, 4,
Yeah.
3, 4 into 7, 9. What does that mean? Actually, 1, 2 into 3, 4 even doesn't even give me a good idea. What I would have better understood is take this and actually, yeah, it's giving the correct idea. Sorry. It is applying 1, 2 to 3, 4 along with 3, 4 to 3, 4. So it's applying this entire function on 3, 4. And it's applying this entire function on 7, 9. So that is the intuition behind matrix multiplication, right? When you said the output of this function is being used as input for this function, you already understood the entire concept. So you just have to take time to,
Stoke it in.
Exactly. Right?
Yeah.
So if I take two functions and I get another function, let's do the entire thing now. Right? I will do it separately here. I have 1, 2, 3, 4. And I want to apply, before. I want, and B is 3. What is it? What is B? 3749. Right? I want to know what does the composition of this function mean, right? So what will it be? First I've applied I've applied this and I've reached, so you can always add this 1001 if you
Identity.
exactly
if
you can
it's
always
confused.
hide it. Yeah. But I'll remove it now because you know that 10 is being mapped to 34 and you know that 01 is just being mapped to 79. So go ahead.
1, 2, 3, 4 times 3, 4. And 1, 2, 3, 4.
So first column will be 1, 2, 3, 4 times 3, 4. And the second column will be
1, 2, 3, 4 times 7, 9.
and you have understood matrix multiplication. And you've also understood
They are functions. That's
what
also
its
an important.
meaning exactly. What its meaning is. Awesome. Done. You just do this and you'll get the answer that you know how to do.
Yeah.
Right? This is nothing but linear combination of 3 times 1, 3 plus 4 times 2, 4, blah, blah, blah. If you want to see that entire thing, I can show it to you here. You can verify what you. Where is it, man? Oh my god, you've done so much, sir. Yeah, here is it. No. Where is it? Here. 3 times 1, 3 plus 4 times 2, 4. Why? Because you're applying this function on 3, 4 first. That is shown as this. And then you're applying this function on 7, 9 next.
Mm-hmm.
And this is the output. Okay. So that is one, I mean, it's a very important, I mean, once you understand matrix multiplication like that, you won't see A into B scary anymore. You'll just be like, oh, it's just applying B first and then it's applying A next. That's all. So when you look at this, what does this mean?
What does this mean? What is alpha here?
Alpha is also a matrix. Just think of it as a matrix. That's all. It's not a, it might have some special property inside, but we still are thinking about it as a matrix. So what does this mean over here?
You're applying the output of M inverse times I to alpha, and then the output of whatever you get from there to M.
Awesome.
Yeah.
You can think of it as that. Perfect. Output of M inverse times I is nothing but M inverse. So
Yeah.
yeah, awesome. Okay, are we done for today? It's 3:41.
Yeah, I guess we have.
Yeah, thank you guys. Like, I think you guys took 1 hour to explain it to me. That was really sweet. Yeah.
Okay, do we have to save all of this somewhere?
How do we do that?
I don't know.
It's fine.
It is very important to save it. So this is
Try that menu on the left hand side. Is there an option there, Shiva? Yeah, is there an option export
save board.
as?
Save
Export
board.
as.
Okay.
Export as.
PDF. Log into export.
PDF. Yeah. Oh no. Is it
PDF.
required?
Oh, okay.
So you need to sign up.
This is factorization also, right? Yeah, we did I mean, whatever sir gave us was factorization. Right? It's M alpha M inverse is nothing but factorization of a matrix.
Okay.
Won't these both be saved into your account? Yeah. No.
You can download it, right? Or you can you can share the link as well.
Yeah, that's better. On Zoom call is fine, is it? Someone keep it at least. I've shared it on the Zoom call.
Oh,
I always have access to it. So even if someone wants, I can give it.
I mean, it remains in the summary of the meeting. So every message that is sent on sent to everyone remains in
Okay.
there.
Thanks for telling me that. I'll be careful with what I do.
Oh my God. Yesterday I was telling couplets. Okay, no, there was no mention, but that was recorded.
I think we stopped the recording before we started.
No,
It's still going on. And
Good,
Rishabh
now-
is here as well. So, my God, I am sorry, Rishabh.
Sir starts it, and sir, if somebody else is going
Okay,
to end it,
let me stop
it
it.
is
Let
gone.
me stop it now.
How will you rejoin?